Hey guys, good morning and welcome back again to your Unacademy NEET English channel. I hope all of you are doing amazing, all of you are doing great. So people, quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly, let me know in the chats. Everyone. Good morning, people. Good morning. Good morning, guys. Good morning. Good morning and welcome back. Good morning and welcome back. So what's up? How are you all doing? I'm all good, guys. Thank you so much. I'm all good. Perfect. So I hope I'm perfectly audible, visible to everyone. So my dear students, you all must be knowing today it's going to be the mega marathon of your class 11th physical chemistry, right? And let me exactly show you the chapters which are there in class 11th physical chemistry. Please have a look. Mole concept, redox reactions, atomic structure, thermodynamics, chemical equilibrium, ionic equilibrium, right? So these are in total some 6 chapters, right? These are in total some 6 chapters. And let me first of all tell you how many marks you guys are going to get from each chapter. My dear students, mole concept, you can expect 2 questions. Redox reactions, you can expect 2 questions. Atomic structure, you can expect 2 questions. Thermodynamics, you can expect 3 questions. Chemical equilibrium, you can expect 1 question. Ionic equilibrium, you can expect 2 questions, right? So in total, 2, 4, 6, 9, 10, 11, 12. So 12 questions you will be getting from your class 11th physical chemistry, right? Perfect. Well, people, to cover all these 6 chapters, since these are big chapters basically, I would require 2 marathons. And the first marathon is today, which will be there for 10 to 12 hours. Perfect. I've already given you the schedule. I've told you class 11th physical chemistry will be done in 2 marathons because I want to cover each and everything. I do not want to skip anything among these chapters. Perfect. That is the reason why I have dedicated 2 marathons for all these 6 chapters. Perfect. Perfect, guys. So can you let me know, have you studied these chapters before? I just want to know. Have you studied these chapters before? See, I'm going to teach every single thing. That too from the basics only. Right? That too from the basics only. You need not to worry about anything. You need not to worry about anything. And once we are done with the marathons, once we are done with the 2 marathons of your class 11 physical chemistry, after that, there'll be extra problem practice session as well. And I believe all of you have already seen the schedule, which I gave you earlier in the, before 2 days. Perfect. I gave you the schedule till 30th of April. Yeah? Perfect. So are you all ready? Are you all ready to be with me till the end? Are you all ready to be with me till the end? Whatever I'm going to teach you today, it is going to be more than sufficient when it comes to your class 11th physical chemistry. Whatever I'll be teaching you, apart from that, nothing is going to be asked when it comes to your NEET examination from these chapters. Okay? Perfect. Perfect, people. Exactly. Practical chemistry will be also done. There'll be a separate 1-2 hour session for that. Right? That's not something huge. Practical chemistry will be also done. Well, while I'll be teaching, you can make the short notes with me, right? You can make the short notes with me. You need not write everything, but be ready with your pen and paper, right? And take a note of all the important things, whatever I'll be mentioning on the screen. Perfect. And whatever questions I'll be giving you, try to solve them with me. Okay. And at the end of the session, right, I'll be sharing the session PDF with you. Well, I could not share the inorganic PDF with you, right? You know what is the reason. Perfect. That got deleted because of the electricity cut, right? Okay. But right after today's session, I'll be sharing this PDF with you for sure because I've already saved this. So should we start? I would want some fire in the chats. Smoke in there. Yeah? I would want some fire in the chats. Before starting the session. Let the Josh be high. Because this is not going to be the session for 1 hour, 2 hours. This is the session for complete 10, 12 hours. Right? So I want you guys to stay with me till the end with the same Josh the way you're starting right now. And in between, I'll be giving you the breaks as well. You know it, right? After every 2 to 3 hours, I'll be giving you like 15 to 20 minutes breaks for sure. Perfect, guys. So without wasting any sort of a time, let's get going and let's get started with the first chapter of your class 11th physical chemistry. That is the mole concept. This particular chapter, it forms the foundation of your physical chemistry. If this particular chapter is clear, then and then your complete physical chemistry can get clear. Otherwise, if there are issues in this particular chapter, there'll be issues in your physical chemistry throughout. So make sure whatever I'll be teaching you in the mole concept, you understand each and everything in detail, because this chapter means, if this chapter is strong, that actually means your physical chemistry automatically is getting stronger. Okay? Perfect. All right, guys. So let's get going. Let's get started. Let's get started, guys. Let's get started. Just give me a second. Let's get started. Just a second. Perfect. My dear students, over here I'm writing a term. That is 1 AMU. That is 1 AMU. Which is also what I call as 1U, which is also what I call as 1D. Now, what this AMU stands for, what this U stands for, and what this D stands for. Let me tell you, this AMU, which I wrote over here, it stands for the atomic mass unit. U stands for the unified mass. And this D over here, which I wrote, it stands for Dalton. It stands for Dalton. Now, what this 1 AMU exactly means? Let me tell you, this 1 AMU, which is what you call as 1U, which is what you call as 1D, it is defined as 1/12 of the mass of carbon-12 atom. It is defined as 1/12 of the mass of carbon-12 atom. Imagine you have taken the carbon-12 atom. You have divided the carbon-12 atom into 12 equal parts. After dividing the carbon-12 atom into 12 equal parts, the smaller part which you take, right? Whatever is the mass of that smaller part, that is something which you call as 1 AMU. 1 AMU is basically defined as 1/12 of the mass of whole carbon-12 atom. 1/12 of the mass of whole carbon-12 atom. Let me tell you, the mass of one carbon-12 atom, the mass of one whole carbon-12 atom. How much is that? That is 1.99 into 10 raised power minus 23 grams. If you know the mass of one whole carbon-12 atom, if you divide that number by 12, you'll be getting the value exactly as 1.66 into 10 raised power minus 24 grams. Okay, so what exactly we did? We took a carbon-12 atom, right? Mass of whole carbon-12 atom is how much? 1.99 into 10 raised power minus 23 grams. And I divided that carbon-12 atom into 12 equal parts. And then I took one smaller part. The mass of that smaller part, the mass of 1/12 part of the carbon is how much? 1.66 into 10 raised power minus 24 grams. And my dear students, I can write it as 1 divided by Avogadro's number as well. Because when you divide 1 by the Avogadro's number, when you divide 1 by 6.022 into 10 raised power 23, you'll be getting the value exactly as how much? 1.66 into 10 raised power minus 24. This is the first statement which I would want every one of you to remember. This is the first statement which I would want every one of you to remember. Okay? 1 AMU, which is what you call as 1U, which is what you call as 1D. It is defined as 1/12 of the mass of carbon-12 atom. Mass of whole carbon-12 atom is this much. If you divide this number by 12, you'll be getting the value exactly this much, which can be written as 1 divided by Na as well, where Na is something which you call as your Avogadro's number. Perfect. Now guys, what this 1 AMU is? Let me tell you this 1 AMU over here, which is what you call as 1U, which is called as 1D. It is basically a standard. 1 AMU, it is basically a standard. It is basically the reference. It is a standard, it is a reference with which we shall be comparing the masses of different atoms or molecules. 1 AMU or 1U or 1D, it is nothing but, it is a standard, it is a reference. It is a standard, it's a reference with which we shall be comparing the masses of different atoms or molecules. Right? With which we shall be comparing the masses of different atoms or molecules. Now, how exactly? For that, have a look. Try to understand exactly what I'm going to say. My dear students, try to understand carefully what exactly I'm going to say. Over here, I'm dividing this board into 3 parts. Try to understand exactly what I'm going to say. I'm going to define certain terminologies here. One is called as atomic mass. One more term is what you call as molecular mass. And one more term will be called as the molar mass. These are the 3 basic terminologies which I'm defining with all of you in the beginning itself. Try to understand what these terms are. This forms the basics of the mole concept. First thing, how do we define the atomic mass? Atomic mass is nothing. It is defined as the mass of, atomic mass is defined as the mass of one atom of an element. Atomic mass is defined as the mass of one atom of an element. For example, I'm asking you, what is the atomic mass of oxygen? What does that mean? That means I'm asking you, what is the mass of one atom of oxygen? Let's say I'm asking you, what is the atomic mass of fluorine? That means I'm asking you, what is the mass of one atom of fluorine? So in short, if I want to define the term atomic mass, it simply means the mass of one atom of an element. Now, my dear students, for example, if I talk about oxygen, you know, what is the atomic mass of oxygen? You know, it is 16 AMU. It is 16 AMU. What does it mean? What does it mean? I can divide this 16 AMU into 2 parts. I can write it as 16 multiplied by 1 AMU. I can do that. And you know, this 1 AMU is nothing. It is 1/12 of the mass of carbon-12 atom. Yes? 1 AMU is also equal to 1.66 into 10 raised power minus 24 grams. This 1 AMU is also equal to 1 divided by Na grams. Now, why did I do all these things? I just took an element oxygen, right? And I'm telling you, the atomic mass of oxygen is 16 AMU. What does it mean? It means one atom of oxygen is 16 times. One atom of oxygen is 16 times heavier than 1 AMU. One atom of oxygen is 16 times heavier than 1/12 of the mass of carbon-12 atom. This is the mass of one atom of oxygen in grams. Even this is the mass of one atom of oxygen in grams. As simple as that. As simple as that. For example, you're defining, I'm asking you, what is the atomic mass of nitrogen? You will say atomic mass of nitrogen is 14 AMU. What does that mean? That means one atom of nitrogen is 14 times heavier than 1 AMU. one atom of nitrogen is 14 times heavier than 1/12 of the mass of carbon-12 atom, right? If I ask you, what is the mass of one nitrogen atom in grams? You will say 14 multiplied by 1.66 into 10 raised power minus 24 grams. Or you will say 14 multiplied by 1 divided by Avogadro's number in grams. Yes, as simple as that. As simple as that. Perfect. So, what is atomic mass? It is nothing but mass of one atom of an element. My dear students, did you understand one thing? I told you in the beginning, 1 AMU is the standard. 1 AMU is the reference with which we compare the masses of different atoms. Did you see? I told you, one atom of oxygen is 16 times heavier than 1 AMU. So this 1 AMU over here is the reference. It is the standard with which I'm comparing the masses of different atoms. As simple as that. Yes? I believe this is clear. I believe this is clear. Right? Now, if I talk about the term molecular mass, look at the name, molecular mass. Molecular mass simply means mass of one molecule, right? Mass of one molecule. Right? Mass of one molecule. How do you calculate it? You know it already. How do you calculate it? It is calculated as the sum of atomic masses. The sum of atomic masses of all the elements present in a molecular compound, right? For example, I'm taking water. I'm asking you, what is the molecular mass of water? I'm asking you, what is the molecular mass of water? How do you calculate it? How do you calculate it? Sum of atomic masses. Hydrogen, its atomic mass is 1, multiplied by how many hydrogen atoms? 2. Plus oxygen, its atomic mass is 16 AMU. How many oxygen atoms? 1. When you solve this term, what is the value which you will get? You'll get the value exactly as 18. Now, in case of molecules, preferably, we write U in place of AMU. Meaning is same. AMU, UD, they are same, right? But in case of molecules, right, we prefer the term U instead of what? Instead of AMU. Now, my dear students, if I ask you what it means, we got the molecular mass of water as 18U. What does that mean? We got the molecular mass of water as 18U. Can I break this 18U as 18 multiplied by 1U? I can do that. Instead of 1U, can I write 1/12 of the mass of carbon-12 atom? Absolutely, I can do that. Instead of 1U, can I write 1.66 into 10 raised power minus 24 grams? Absolutely, I can do that. Instead of 1U, can I write 1 divided by Avogadro's number in grams? Absolutely, I can do that. Perfect. So what did we get? Try to understand. We got the molecular mass of water. It means that one molecule of water, one water molecule is 18 times heavier than 1U. One molecule of water is 18 times heavier than 1/12 of the mass of carbon-12 atom. This is the mass of one water molecule in grams. Even this is the mass of one water molecule in grams. I believe this is super clear to everyone. Now, my dear students, the third terminology which we have. What do we have? The third terminology. It is the molar mass. Molar mass. What is molar mass? Molar mass is simply defined as the mass of one mole of a substance. The mass of one mole of a substance. The mass of one mole of a substance. Or I can write it like this. Mass of 6.022 into 10 raised power 23 particles of the substance. Right? Mass of 6.022 into 10 raised power 23 particles of the substance. Or I can write it like this. Mass of one particle of a substance. Mass of one particle of the substance multiplied by Avogadro's number. Simple. Right? Molar mass. Mass of one mole of the substance. You know, 1 mole of the substance contains 6.022 into 10 raised power 23 particles. So instead of mass of 1 mole of the substance, I can write mass of 6.022 into 10 raised power 23 particles of the substance. I can write it as mass of one particle of a substance multiplied by Avogadro's number. All these things are absolutely the same, right? For example, I want to define the molar mass of marker. What is meant by the term molar mass of marker? It means I am asking you to calculate the mass of 1 mole marker. 1 mole marker means 6.022 into 10 raised power 23 markers. So indirectly, I'm asking you, calculate the mass of 6.022 into 10 raised power 23 markers. How do I get that? If I just calculate the mass of 1 marker and multiply that term with Avogadro's number, I'll be getting the mass of 6.022 into 10 raised power 23 markers, which is what I'll be calling as molar mass of marker. Am I clear with this? Am I clear with this? Say yes or no in the chats quickly. Say yes or no in the chats quickly. Understand, people? Let's say I want to calculate molar mass of, for example, oxygen. Oxygen I've taken in atomic form. O. I've not written O2. What is meant by molar mass of oxygen? Molar mass of oxygen. It means mass of one oxygen atom multiplied by Avogadro's number. What is the mass of one oxygen atom? Mass of one oxygen atom is 16 AMU. Mass of one oxygen atom is 16 AMU. And I'm multiplying it with what? Avogadro's number. My dear students, you already know 1 AMU I can write as 1 divided by Na grams. Right? Multiplied by this Na. So Na cancel, the value came out to be 16 grams. So what is the 16 grams? What is the 16 grams? It is the molar mass of oxygen. This is the mass of 1 mole of oxygen. This is the mass of 6.022 into 10 raised power 23 oxygen atoms. Yes? Right, people? If you look carefully, what was the atomic mass of oxygen? 16 AMU. What is the molar mass of oxygen? 16 grams. So magnitude-wise, they are same, right? 16, 16, same. It is just units are different. It is just units are different. Perfect? For example, sodium. Its atomic mass is 23 AMU. That means mass of one atom of sodium is 23 AMU. Now, if I'm asking you, what is the molar mass of sodium? Instead of AMU, you just have to write grams. That is the molar mass of sodium. That is the mass of 1 mole of sodium. That is the mass of 6.022 into 10 raised power 23 sodium atoms. Right? Right, people? So, in short, what do you have to remember? Atomic mass, molar mass. Difference is in the units. Here, the unit is AMU. Here, the unit is grams. Right? Okay, one more thing. Water. Its molecular mass is 18U. Its molecular mass is 18U. That means mass of 1 molecule of water is 18U. Now, if I ask you, what is the molar mass of water? Instead of U, you'll write grams. That's it. 18 grams will be the molar mass of water. As simple as that. Right? Right, people? I hope I'm clear with all these things. Yeah? Now, to quickly summarize all these things, try to understand what exactly I'm going to say. Try to understand what exactly I'm going to say. I'm quickly summarizing all these things, which is super important. My dear students, here I'm writing O, oxygen in the atomic form. Oxygen is in the atomic form. Here I'm writing O2. So oxygen here is in molecular form. Oxygen here is in the molecular form. Now try to understand perfectly. I'm writing few terminologies related to this O. One, I'm writing 16 AMU. Another terminology, only and only I'm writing 16 without the units. Third terminology, instead of 1 AMU, I'm writing 1.66 into 10 raised power minus 24 grams, right? And at the end, I'm just writing 16 grams. I'm just writing 16 grams. Try to understand carefully what I say. Similarly, O2. First of all, I'm writing 32U. Then I'm only writing 32. Then I'm writing 32 multiplied by 1.66 into 10 raised power minus 24 grams. At the end, I'm just writing 32 grams. 32 grams. Now, let me tell you the meaning of all these things, right? Perfect? Perfect. Try to understand, guys. Try to understand carefully. First of all, oxygen here I've taken in atomic form. So, this is what I call as atomic mass of oxygen. Right? This is what I call as atomic mass of oxygen. Only 16. This is what I call as a relative atomic mass of oxygen. This is what I call as a relative atomic mass of oxygen. Right? This particular term, this I call as actual mass of O. This is what you call as actual mass of O. And this particular term, you call this as molar mass of O. You call this as molar mass of O. Right? Or instead of the term molar mass, you can write one more thing. See, oxygen here is in atomic form. So instead of molar mass, you can write gram atomic mass. You can write gram atomic mass of oxygen as well. This is what you call as gram atomic mass of oxygen as well. But you should know the meaning. You should know the meaning of all these things. This is the mass of one oxygen atom, right? Perfect. This is the atomic mass of oxygen. Perfect. This 16 grams. This is not the mass of one atom of oxygen. This is the mass of 1 mole of oxygen. This is the mass of 6.022 into 10 raised power 23 oxygen atoms. As simple as that. Right? Now, look at all these terminologies. Oxygen here is in molecular form. So this particular term I'll be calling as molecular mass of oxygen. Molecular mass of oxygen. This particular term, without the units, you'll be calling it as relative molecular mass of oxygen. You'll be calling it as relative molecular mass of oxygen. This particular term, you'll be calling this particular term as the actual mass of O2. Actual mass of O2. And this particular term, first of all, you'll be calling it as molar mass of O2. Molar mass of O2 or since oxygen is in molecular form, you can call it as gram molecular mass of oxygen as well. You can call it as the gram molecular mass of oxygen as well. Am I clear with all these things? Say yes or no in the chats. Quickly. Quickly, guys. Everyone. I want everyone to say it. Are all these things clear to you? Are all these things clear to you? Say it in the chats quickly. Yes. Perfect. One statement which I would want every one of you to remember from now onwards. I'm taking a note of that statement. I'm taking the note of that particular statement. What is the standard which I've chosen? I've chosen 1 AMU as the standard, and which we defined as 1/12 of the mass of carbon 12 atom. Which we defined as 1/12 of the mass of carbon 12 atom. My dear students, remember and directly remember. No need of explanation, etc., etc. Remember it directly. On changing the standard, on changing the reference, on changing the standard, on changing the reference, on changing the standard, on changing the reference. For example, if I'm not defining AMU as 1/12 of mass of carbon 12, if I'm defining it as 1/6 of mass of something, 1/24 of mass of something, that means I'm changing the standard. When you change the standard, remember directly, actual mass of the substance does not change. Actual mass of the substance remains unchanged. Remains unchanged. Remains unchanged. Do remember this particular point from now onwards. Right? Perfect. Perfect. Now, my dear students, the things which I've told you till now, let's see what kind of question can be asked out of these things. The first type of the question which can be asked is on your screen. Look at the question carefully and let's try to solve this. The question is saying if 1U means 1 AMU, if 1U is defined as 1/24 of the mass of carbon 12 atom, that means we are changing the standard. We are changing the standard. Calculate the molecular mass of carbon dioxide on new scale. Understand how exactly you'll be approaching to these sort of questions. Remember them directly. My dear students, if you remember, we had defined 1U as 1/12 of the mass of carbon 12 atom. 1/12 of the mass of carbon 12 atom. This is how we had defined 1U, right? As per the question, how you are defining 1U, which I'm calling as 1U dash. As per the question, 1U is defined as 1/24th of the mass of carbon 12 atom. Right? Yes. Now people understand. This scale which I've chosen over here, this is the old scale, conventional scale, which we have defined. And this particular scale is the new scale that is given to us as per the question. That is given to us as per the question. What are we supposed to calculate? We are supposed to calculate the molecular mass. We are supposed to calculate the molecular mass of carbon dioxide on new scale. We have to calculate molecular mass of carbon dioxide on new scale. My dear students, the first thing which I'll be doing, always, I'll be dividing these two equations. Why do I need to divide these two equations? I just need to get the relation between U and U dash. I just need to get the relation between U and U dash. Perfect. I'll be dividing these two equations. Equation 1 divided by equation 2. So it becomes U divided by U dash. U divided by U dash is equal. Mass of carbon 12, mass of carbon 12 cancel. So 1 by 12 divided by 1 by 24. The value comes out to be 2. So U is nothing but 2 times U dash. U is nothing but U times 2 times U dash. Guys, these are the standard questions. These are the standard questions that can be asked. The first thing, I got the relation between U and U dash. I got the relation between old scale and new scale. Perfect. Number one. Number two. If I ask you, what is the molecular mass of carbon dioxide on old scale? Molecular mass of carbon dioxide, which we know, 12 multiplied by 1 plus 16 multiplied by 2. That is 44U. This is something which we know. But do we have to get the answer in terms of U? No, we have to get the answer in terms of U dash. So I can write it as 44 multiplied by 1U, and 1U already is equal to what? It's equal to 2 times U dash. The value comes out to be 88 U dash. So what is this 88 U dash? This is the molecular mass of carbon dioxide on new scale. This is the molecular mass of carbon dioxide on new scale. Right? This is something which we were supposed to calculate. Done and dusted. Right? Now, if I ask you one thing, can you tell me the actual mass of carbon dioxide on new scale? I'm just asking you this question directly. Can you tell me the actual mass of carbon dioxide on new scale? Quickly. Actual mass of carbon dioxide on new scale. I told you already. Actual mass does not change when you change the standard. Actual mass will still remain the same. What was the actual mass? Actual mass was 44 multiplied by 1.66 into 10 raised power minus 24 grams. This was the actual mass of carbon dioxide on old scale. On new scale, it will be the same. You need not to check anything. It remains unchanged. My dear students, quickly tell me the answer of this particular question. Quickly. We don't have a lot of time. Quickly tell me the answer of this particular question. Be very quick. Be very quick. Be very quick. Be very quick, and I'm damn sure you can easily solve this now. Be very quick. You also solve it, I'll also solve it. As per the question, first of all, we know already 1U is nothing but 1/12 of the mass of carbon 12. This is something which we already know. This is our old scale. Now, as per the question, the new scale 1U dash is defined as 1/6 of the mass of carbon 12 atom. 1/6 of the mass of carbon 12 atom. This is your new scale. First of all, I need to divide them up. So U divided by U dash, this divided by this will be equal to 1 divided by 2, or U will be equal to U dash divided by 2. This is the relation which I got between U and U dash. Done and dusted. Now after this, calculate the molecular mass of NH3. Molecular mass of NH3 on old scale is what? 17U. But I do not need to write the answer in terms of U. I have to write the answer in terms of U dash. So 17 multiplied by. Instead of U, I can write U dash divided by 2. So this is 8.5 U dash. This is the molecular mass of NH3 on the new scale. Is it done and dusted? Yes. Is it done and dusted, people? Say it in the chats. Say it in the chats. Perfectly done. Moving ahead. Can you let me know the answer of this simple question which is on your screen? The mass of one atom of X. We are given with the mass of one atom of some element X. Mass of one atom is given. Calculate its molar mass. Can't you solve it? I told you already. Molar mass of the substance. Molar mass of the substance. And substance here is X. Molar mass of X can be written as, if you remember, I told you, mass of one atom of X, multiplied by Avogadro's number. Which I'm roughly writing as 6 into 10 raised power 22. 6.022 into 10 raised power 23. Right? I told you that already. Molar mass of substance is equal to mass of one atom of substance multiplied by Avogadro's number. Now, what is the mass of one atom of X? It's given to me as 4 into 10 raised power. This minus 23 here, by the way. 4 into 10 raised power minus 23 grams. Multiplied by what? Multiplied by 6 into 10 raised power 23. So this term cancel. 6 4s are 24. The value comes out to be 24 grams. This is the molar mass of X. Now, if in the question, let's assume they are not asking you directly the molar mass of X. They're asking you identify the element X. And your options are sodium, your options are magnesium, your options are chlorine, your options is carbon. Which is going to be the correct answer? Let's say they are not asking you calculate the molar mass of X. They are asking you identify X. Your calculated molar mass of X. And 24 grams, that is basically the molar mass of magnesium. 24 grams, that is the molar mass of magnesium. So with like this also the question can be asked. Pretty much simple, yeah? Perfectly done? So be careful with all these things. Moving ahead. Have you heard about something called as isotopes? Have you heard about something called as isotopes? What are isotopes, my dear students? What are isotopes? You should be knowing it. Isotopes. These are the atoms. These are the atoms of what?Ese are the atoms of same element. These are the atoms of same element having same atomic number. But different atomic masses. Yes, something which you all must be doing. Same atomic number, different atomic masses. For example, if I talk about chlorine, you should be knowing chlorine. Chlorine has got two atoms. Which have got same atomic number but different atomic masses. 35, 37. Chlorine has got two atoms which have got same atomic number but different atomic masses. So should I be calling these two as the isotopes of chlorine? Absolutely, these two are called as isotopes of chlorine, right? Hydrogen, it has three isotopes, right? H11, H12, H13. Protium, deuterium, tritium, right? You should be knowing. Now, my dear students, in general, if I write something like this, try to understand. In general, I'm writing something like this. Let's say you're the element X. Or let me write it in the middle. Imagine that you all got the element X. I'm assuming this X has got three isotopes. That means this X has got three atoms which have got same atomic number, but their mass number is different. This is M1, this is M2, this is M3, right? So I should be calling these three as the isotopes of this X. And let me tell you, whenever element has got isotopes, whenever an element exists in the form of isotopes, at that point of time, what do? We do not calculate the normal atomic mass of element. We calculate the average atomic mass of the element. So when do we define the average atomic mass of the element? When do we define it? It is defined when the element exists in the form of isotopes, right? Now people, be careful with what I say. We have got the element X, it has got isotopes. Whenever element exists in the form of isotopes, we do not calculate the normal atomic mass of the element. What do we calculate? We calculate the average atomic mass. Now, in order to calculate the average atomic mass of the element, what do we need? Remember, we need the percentage abundances. We need the percentage abundances of these isotopes. So what are percentage abundances? What is meant by that? You'll get the idea in some time. First, you remember, in order to calculate average atomic mass, what do we need? We need percentage abundances of these isotopes, or I can say we need mole percentage of these isotopes. I'm assuming the percentage abundances of these isotopes are nothing but A%, B%, and C%. Once you know the values of A, B, and C, you can get the formula over here. And the formula is pretty much simple. M1A plus M2B plus M3C divided by what? Divided by A plus B plus C. This is one general result by means of which you can calculate the average atomic mass of an element which exists in the form of isotopes. As simple as that. Yeah? Right? And people, do remember one thing. The sum of percentage abundances of all the isotopes of a particular element, that's always equal to what? That's always equal to 100. Now let's try to solve one example so that you understand what it means. One very simple and basic example I'm giving you. Try to understand carefully. My dear students, for example, I'm taking the element chlorine. Understand carefully. I'm taking the element chlorine. Chlorine, it has got two isotopes. One is Cl35 One is Cl37. One is Cl37. Perfect. I'm telling you that the percentage abundances of Cl35 and Cl37, it is 75 and 25 respectively. 75 and 25 respectively, right? Now I'm asking you to calculate the average atomic mass of chlorine. Can you do that? Can you do that? You should be in a position to do it. It's pretty much simple. See, this 35 is basically the value of M1. This is the value of M2. This is the value of A. This is the value of B. All the terms are in front of you. Done and dusted, right? Done and dusted. So you'll be using the result M1A plus M2B divided by A plus B. That's always 100, right? M1 is given, M2 is given, A is given, B is given. When you solve this, the value comes out to be 35.5 AMU. So what is the 35.5 AMU? This is the average atomic mass of chlorine. This is the average atomic mass of chlorine, right? Yes? Am I clear? Am I clear, people? Am I clear, people? Say yes or no in the chats. Perfectly done. All right, people. Got it. Perfect. This is the question which has been asked many a times. This was asked once in JEE mains examination. See what kind of question was asked. Can't you kill it? Can't you kill it, people? Boron has two isotopes, this and this. What is the average atomic weight of boron? This is something which we are supposed to calculate. Isn't it simple? My dear students, boron, it has got two isotopes. It has got two isotopes. One is your boron N, one is your boron 11. Percentage abundances are given to us. This is 19 and this is 81. Perfect. So M1 is given, M2 is given, A is given, B is given. I just need to write the formula, and formula you know. Yeah, and formula you know. So I'll write average atomic mass of boron is nothing but M1A plus M2B divided by what? Divided by A plus B. All these things are given. When you solve it, the value comes out to be 10.81 AMU. The answer of this particular question is going to be option A. I believe all these sort of questions you can solve easily from now on. Yeah? Perfectly done. Perfectly done, people. Now, how do we calculate the number of moles? That's important. How do we calculate the number of moles? How do we calculate the number of moles? If I ask you. My dear students, the answer is again very simple. You know the formulas already. I just need to write the formulas and I'll show you their application. Try to understand carefully. Number of moles of the substance which I'm representing with N. Number of moles of the substance which I'm representing with N. Or let me write it. Number of moles of a substance. Number of moles of a substance. I'm representing this term with N. How do we calculate it? The first formula which we have. Given mass of the substance in grams. Given mass of the substance in grams divided by what? Divided by molar mass of the substance, which is expressed either in grams or you can say grams per mole. This is the first formula which we have to calculate number of moles. Given mass divided by molar mass. Number one. Number two. Number of moles of the substance is always equal. Given number of particles. Given number of particles. Given number of particles of the substance divided by Avogadro's number. Divided by Avogadro's number. Second formula. Third formula, which is only valid for gases. Which is only valid for gases. Be careful with this. This is only valid for gases. And the gases should be presented as STP, standard temperature pressure. And the formula is, it is given volume of the gas in liters. Given volume of the gas in liters divided by 22.4 liters. These are the three basic formulas which we have to calculate number of moles. Or sometimes you can use ideal gas equation to calculate number of moles of the gas, which is N is equal to PV divided by RT. Right? This can be also sometimes used. So these are some basic results by means of which we calculate number of moles of a particular substance. For example, I'm just giving you certain basic questions first of all. Slowly we'll rise the level. Right? For example, these are the basic questions which we have. Can't you solve them? Can't you solve them, people? Calculate the following. Calculate the number of moles in 160 grams of NaOH. Look carefully. I'm given with mass of NaOH. I'm supposed to calculate moles. I'm supposed to calculate moles. That will be equal to given mass of NaOH in grams divided by molar mass of NaOH when you calculate 23 plus 16 plus 1. Value comes out to be 40. And 40 grams per mole. The value comes out to be 4. So that means 160 grams of NaOH means what? 160 grams of NaOH means 4 moles of NaOH. Done and dusted, right? Look at the second one. 67.2 liters of carbon dioxide at STP. We are given with the volume of the gas. We are given with the volume of the gas. We are supposed to calculate moles of the gas. How do we calculate moles when volume is given? Given volume of the gas in liters divided by 22.4, right? The value comes out to be 3. So 67.2 liters of carbon dioxide at STP means that we are given with 3 moles of carbon dioxide. As simple as that. Yeah? Look at the next one. Number of moles in 24 into 10 raised power 23 atoms of carbon. Look carefully. We are given with the particles. We are given with the particles. We are supposed to calculate moles. So I'll say number of moles of carbon is equal to given number of particles. Given number of particles divided by what? Divided by Avogadro's number. Given number of particles divided by Avogadro's number. The value is 4. So basically 24 into 10 raised power 23 atoms of carbon means that we have got 4 moles of carbon. As simple as that. Done and dusted. Right? Look at the next one, people. Number of moles in these many molecules of water. Again, we are given with particles. Again, we are given with particles. So calculate moles. Moles of water will be equal to given number of particles. Given number of particles divided by what? Divided by Avogadro's number. Right? The value comes out to be 6, 8. This is 80. Perfect. These are the simple results. 3, 4 basic results by means of which you can calculate moles of a particular substance. Right? Am I clear with all these things? I should be. Yeah? Right, people? Now understand. Now understand. Over here, I'm writing a term number of moles. I'm writing a term number of moles, which is represented by N. And dear students, how many ways do we have? How many ways do we have to calculate number of moles of a particular substance? You tell me. How many ways do we have? Either I'll be given with mass of substance, or I'll be given with particles of the substance, or I'll be given with volume of the gas. There are 3 ways by means of which I can calculate moles, right? Yes? Now people, let me tell you, in order to calculate moles, either mass of the substance should be given to us. Either mass of the substance should be given to us, number 1. Number 2, or number of particles of the substance should be given to us. Number of particles of the substance should be given to us, or I would say volume of the gas. Volume of the gas in liters at STP should be given to us. Perfect. In order to calculate moles, these are the things which should be given to us, either mass or volume or particles. Right? Now you know already. Now you know already. If we are given the mass of the substance and we are supposed to calculate moles, if we are given the mass of the substance and we are supposed to calculate moles, what do we need to do? Given mass of the substance divided by molar mass of the substance. What do we get? We get moles. If I reverse the same, if moles of the substance are given, and we are supposed to calculate mass of the same substance, what do we need to do? Moles of the substance multiplied by molar mass of the same substance. I'll be getting the mass. I'll show its application in some time. Now, if number of particles are given, and you are supposed to calculate moles, given number of particles divided by Avogadro's number, or if you reverse it, if moles are given and you are supposed to calculate particles multiplied by Avogadro's number. Simple, right? If volume is given, you are supposed to calculate moles divided by 22.4 liters, right? If moles are given and you are supposed to calculate volume multiplied by 22.4 liters. This is the simple mole conversion diagram which you need to remember. Now people, if I ask you something like this, understand very carefully. For example, you are given with the mass of substance. You are given with the mass of substance and you are supposed to calculate volume. You are given with mass. Let's say you are given with mass. You are supposed to calculate volume of the substance. Is there any direct result between mass and volume? No. What do we need to do? If mass of the substance is given and we are supposed to calculate volume, there is no direct result. So what do we need to do? We need to follow the arrows. Which take us from mass till volume. We need to follow the arrows which take us from mass till volume. Now, which all arrows take us from mass to volume? So first I'll be following this particular arrow. Given mass divided by molar mass, I'll be getting moles. Then I'll be following this arrow. Moles multiplied by 22.4. I'll be getting volume. As simple as that. Right? For example, there is a question in which mass is given and we are supposed to calculate particles. Mass is given and particles are to be calculated. For example, mass is given, particles are to be calculated. There is no direct arrow. What do I need to do? I need to follow all the arrows which take me from mass till particles. And which all arrows are those? This is the first arrow. So given mass divided by molar mass gives me moles. Then, once you calculate moles, multiplied by Avogadro's number, that gives me particles. I believe you can do that. I believe you can do questions on this. Simple. For example, 1-2 questions I'll solve with you for the related to this diagram. Let me see if you can solve this or not. Can you do this? Calculate the mass of 67.2 liters. We are given with volume. We are supposed to calculate mass. We are given with volume. We are supposed to calculate mass. We are given with volume. We are given with volume and we are supposed to calculate mass. Right? So this is given, this to be calculated. So I'll start from here and I'll follow all the arrows which take me from volume till mass. So if I ask you which all arrows I need to follow, my dear students, this is the first arrow which I'll be following and this is the second arrow which will be following. So question will be done and dusted with that. Right? So what is the given volume? What is the given volume? 67.2 liters. So 67.2 liters divided by 22.4. The value comes out to be 3. So I got number of moles as 3. 3 multiplied by molar mass. Molar mass of what? Molar mass of carbon dioxide. So 3 multiplied by molar mass of carbon dioxide is how much? 44 grams. So 3 multiplied by 44 comes out to be 132 grams. So 132 grams is the answer of the question. Perfect. So I would say the mass of 67.2 liters of carbon dioxide at STP is how much? 132 grams. As simple as that. Done and dusted, right? Yeah. Now, similarly, if I ask you, calculate the molecules present in 440 grams of carbon dioxide. My dear students, in this question, mass is given, particles are to be calculated. Mass is given, particles are to be calculated. So you'll start from mass and you'll reach till particles. So first step will be number of moles of carbon dioxide will be equal to given mass of carbon dioxide in grams divided by molar mass of carbon dioxide. The value comes out to be 10. So you got the moles, right? Now, number of molecules of carbon dioxide. Number of molecules of carbon dioxide. The second step is moles are to be multiplied by the Avogadro's number. Moles are to be multiplied by the Avogadro's number. Moles are 10 multiplied by Avogadro's number. So these many molecules are present in 440 grams of carbon dioxide. Am I clear? 10 Na is the final answer of the question. I believe you can do it. I believe you can do it from now on easily. Guys, I want you to solve this question. Look at the question carefully once. Look at the question carefully once. Can you solve it? Just say it. Just say it. Just say it. Can you solve it? I just want to know. Can you solve it? Yes or no? Yes or no? Yes or no, people? Yes or no? Yeah? You should be in a position to solve it. The question is pretty much simple. Calculate the number of moles present in 96 kg of X. So we are given with mass of X. We are supposed to calculate moles. We are given with mass of X. We are supposed to calculate moles. So number of moles of X is equal to mass of X in grams, which is 96,000 grams. Given mass divided by molar mass of X. Divided by molar mass of X. Now people, if I ask you, are we somewhere given with the molar mass of X? I don't think so. Molar mass of X is not given to us, but mass of one atom of X is given to us. If you know the mass of one atom of X, just multiply it with Avogadro's number. Just multiply this term, 4 into 10 raised power minus 23 grams. Just multiply it with Avogadro's number. What do I get? What do I get? The value comes out to be 24 grams. 24 grams is the molar mass of X. Something which I told you already, right? So divide this 96,000 with what? With 24 grams per mole. The value comes out to be how much? Quick. People are saying 4,000. Absolutely. You guys are perfectly right. Done and dusted, right? Done and dusted. Done and dusted. Guys, if I ask you a question like this, have you seen this question? This question was asked in JEE long back. but it's a proper NEET standard question. Can you kill this one? How many moles of electron? So you're supposed to calculate moles. How many moles of electron? V is 1 kg. So you are given with mass, you have to calculate moles. You are given with mass, you have to calculate moles. So number of moles of electrons is equal to mass of electrons in grams divided by molar mass of electron. Divided by molar mass of electron. Divided by molar mass of electron. Mass of electron in grams is 1 kg, which means 1000 grams. Molar mass of electron means mass of one electron, which is 9.1 into 10 raised power minus 28 grams, multiplied by 6.022 into 10 raised power 23. This becomes grams per mole. Just the matter of calculation and you guys are done. Just the matter of calculation and you guys are done. Yeah? Perfectly done, people. Perfectly done. Now, one more type of question that will be asked. One more type of question that will be asked. Calculation of atoms, electrons, protons, neutrons, ions. This you would have seen frequently. How many electrons are present in 67.2 liters of carbon dioxide? How many valence electrons are present in 4.2 grams of N tri-negative, which was asked 3 years back in NEET, right? These sort of questions you would have, you would have seen questions based on these. Atoms, electrons, protons, etc. Now, in order to solve this set of questions, I would want to give you one diagram, which you will be remembering. That's all. One diagram, and we are done. Understand properly what exactly I'm going to say. My dear students, here I'm writing something as given quantity. Given quantity. Whatever will be given to us as per the question, be it mass of the substance, be it particles, be it volume, whatever is given to us, you'll be calling that as given quantity. Whatever is given in the question. Your first step always is to convert the given quantity into number of moles. Your first step always is going to be, you will be converting the given quantity into number of moles, right? You'll be converting the given quantity into number of moles. Once we get the moles, we'll be multiplying moles by the Avogadro's number. The substance whose quantity is given, if that substance is in molecular form, then at that point of time, moles multiplied by Avogadro's number, it gives me the number of molecules. Once we get the molecules, we are done. We can calculate atoms, we can calculate electrons, we can calculate protons, we can calculate neutrons, etc., etc. This diagram I would want every one of you to remember and follow directly from now onwards. Now, people, how do we apply this diagram? Yeah? How do we apply it? For that, I'll be taking one simple question, which will make you understand all these things properly. For example, one basic question. Calculate the total number of atoms in 448 liters. Calculate the total number of atoms in 448 liters of carbon dioxide. At what? At STP. This is the question. What are we supposed to calculate? Be careful. Calculate the atoms. And whenever we are supposed to calculate atoms, we are supposed to follow this diagram. The first step, convert the given quantity into moles. Moles multiplied by Avogadro's number. You get the molecules. Once you get the molecules, you can calculate atoms. Done and dusted. See people. The first step, this is my given quantity. I'll be converting the given quantity into moles. So number of moles of carbon dioxide is equal to given volume of carbon dioxide in liters divided by 22.4. Perfect. The value comes out to be 20. Perfect. I got the moles. My first step is done. Now, the given substance is in molecular form. Second step, moles multiplied by Avogadro's number. That gives me molecules, right? So number of molecules of what? Of carbon dioxide will be equal to 20 multiplied by Avogadro's number. These many molecules we have. So these many molecules of carbon dioxide we have. You getting it? We are given with 448 liters of carbon dioxide. So I'll say in 448 liters of carbon dioxide, we'll have these many molecules of carbon dioxide. Now, what are we supposed to calculate? Atoms. If I ask you, tell me, how many atoms are present in one molecule of carbon dioxide? In one molecule of carbon dioxide, there are 3 atoms present. Right? You know it. In one molecule of carbon dioxide, there are 3 atoms present. Now, people, we are done. One molecule of carbon dioxide contains 3 atoms. 2 molecules will contain multiplied by 2. 3 molecules multiplied by 3. 4 molecules multiplied by 4. How many molecules do we have? 20 Na. So 20 Na molecules of carbon dioxide will contain 3 multiplied by 20 Na. The value comes out to be 60 Na atoms. So there are in total 60 Na atoms present in 448 liters of carbon dioxide. Am I clear? Am I clear, people? Am I clear? Am I clear? Am I clear? Say it. Say it in the chats. Say it in the chats quickly. Say it in the chats quickly. Yeah? This is your asked question. Calculate the valence electrons. Calculate the valence electrons in 4.2 grams of N tri-negative. Be careful with what I say. N tri-negative. Is it in molecular form or ionic form? Is it in molecular form or ionic form? This is an ionic form. This is an ionic form. So once I calculate its moles, if I multiply those moles by Avogadro's number, will I get molecules or I'll get ions directly? You say it. You say it. First of all, I'll be calculating its moles. Once I calculate moles, once I multiply those moles by Avogadro's number, what will I get? Will I get molecules or ions? I'll directly get the ions. I'll directly get the ions, right? So my first point, convert the given quantity into moles. So number of moles of N tri-negative is equal to given mass of N tri-negative divided by molar mass of N tri-negative, right? The value will be 0.3. Perfect. So you got the moles. Now, moles multiplied by Avogadro's number, that gives me number of ions directly. Number of ions of N tri-negative will be equal to moles multiplied by Avogadro's number. So these many ions we have. These many ions we have. Now comes one point. What do we have to calculate? Valence electrons. Valence electrons. Let's tell me one thing. If I talk about nitrogen, whose atomic number is 7, one atom of nitrogen will contain how many electrons? 7 electrons. One atom of nitrogen contains 7 electrons. But this is tri-negative, so it has gained 3 more. So in total, there are 10 electrons present in one N tri-negative. In one N tri-negative, there are in total 10 electrons present. Now, out of these 10 electrons, can I say 2 electrons will be in the first shell, 8 electrons will be in the second shell? Perfect. 2 electrons in the first one, 8 in the second one. So this is my valence shell, wherein 8 electrons are present. This is my valence shell, wherein 8 electrons are present. So if I ask you in one N tri-negative, how many valence electrons are present? There are 8 valence electrons present in one N tri-negative. So if you have 2 N tri-negative multiplied by 2, 3 N tri-negative multiplied by 3, how many do we have? 0.3 Na. So in 0.3 Na N tri-negatives, how many valence electrons will be there? 8 multiplied by 0.3 Na valence electrons, which will come out be how much? 2.4 Na valence electrons. So these are the total valence electrons which are present in 4.2 grams of N tri-negative. Yes. Right, people? Right? Am I clear? Say it in the chats quickly. Am I clear? Am I clear? It's just give me a second. Just give me a second. Perfect, guys. Perfect. I believe all these things are okay. One question wherein you might face some problems. One simple question. These are 3 questions. Basic questions these are. But I believe there will be some students who will fall in trap. These are one-step questions. These are one-step questions. Calculate the number of atoms in 16 grams of helium. Atoms we have to calculate. Atoms. So I'll be following this diagram which I gave you. First step, convert the given quantity into moles. So number of moles of helium is equal to Given mass of helium in grams divided by molar mass of helium, right? The value comes out to be 4, right? Now, helium is in atomic form. Helium is in atomic form. So, moles of helium multiplied by Avogadro's number. What that gives us? That does not give us molecules. That gives us atoms because this is in atomic form, right? So, number of atoms of helium. Number of atoms of helium will be equal to what? It will be 4 multiplied by Avogadro's number. 4 multiplied by, done. This is something which I was supposed to calculate. Number of atoms in 16 grams of helium. Done and dusted, right? The second one. Atoms in 16U of helium. 16U. 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 It is not 16 grams here. So you cannot use the result given mass in grams divided by molar mass. Because this is 16U. How do we do this? Understand. 16U. We are given 16U of helium. Right? Tell me one thing. What is the atomic mass of helium? 4U. 4U. 4U is basically, I would say 4U is the mass of one atom of helium. Correct? 4U is the mass of one atom of helium. Now tell me, 1U will be 1 by 4 atoms of helium. I just divided this equation by 4. 1U is equal to 1 by 4 atoms of helium. Am I given with 1U or 16U? 16U. 16U will be 1 by 4 multiplied by 16, right? Which will be 4 atoms of helium. Perfect. So 16U is nothing but 4 atoms of helium. It's simple. 4U is equal to 1 atom. So multiplied by 4. 16U is equal to 4 atoms. Correct? No need to think a lot. Okay. Molecules in 126U of HNO3. Molecules in 126U of HNO3. Now, 63U is the mass of one molecule of HNO3. Is the mass of one molecule. So if I multiply this equation by 2, it becomes 126U. Will be the mass of 2 molecules of HNO3. Right? So molecules, 126U means 2 molecules of HNO3. Am I clear? Say it. Am I clear? Am I clear, people? Quickly say it. I want you guys to say it quickly. Yeah? Right? Perfectly done. Let's go ahead and let's talk about something called as stoichiometry, right? Something which you hate. Something which you hate, I believe. Do you? No. I'll make it simpler for you. Try to understand what exactly I'm going to do. My dear students, the stoichiometry, it is almost used everywhere when it comes to your physical chemistry. Right? This is used everywhere. Now the real mole concept starts, yeah? Exactly. Okay, stoichiometry. First of all, in order to make you understand what the stoichiometry is, how to apply this, and what kind of questions are asked, I'm going to write a general equation. N2 gas plus H2 gas. What does it give? It gives NH3 gas. This is a general chemical equation, right? General chemical equation. If I ask you, is this reaction balanced or not? Is the reaction balanced or not? The reaction is not at all balanced. So first of all, whenever a question is asked in stoichiometry, the first thing which we need to do is to balance the reaction. So balance the reaction. This has to be 3 times, this has to be 2 times, and this is 1. Balanced. My dear students, after balancing the reaction, this 1, 3, and 2, these are called as stoichiometric coefficients. Now, after balancing the reaction, I can treat these stoichiometric coefficients as moles. And how exactly? I can say, as per the stoichiometric coefficients of reactants and products, we can say, from stoichiometry, we can say 1 mole N2 completely reacts with 3 moles of H2 and produces 2 moles of NH3. This is something, this statement, this information we got from the stoichiometric coefficients. We got to know 1 mole of N2. In this reaction, 1 mole of N2 completely reacts with 3 moles of H2 and produces what? Produces 2 moles of NH3. Right? Now, if I ask you, if 1 mole of N2 is reacting with 3 moles, tell me, what about 2 moles of N2? Can I say 2 moles of N2 will react with 6 moles of H2 and will produce 4 moles of NH3? It is simple, as if I multiplied this equation by 2. Right? Simple. Simple, guys. Yes? Right? Point number 1. Point number 2. Point number 2. Here in this particular statement, I wrote all the terms in terms of moles. So basically, which method I'm using right now? I'm using the mole method in stoichiometry. I'm using the mole method. Number 1. Number 2. My dear students, if I ask you, what is the molar mass of N2? Molar mass of N2 will be 28 grams. What does that mean? That means mass of 1 mole of N2 is 28 grams. Am I given with 1 mole of N2 only? Yes. So what is the mass of 1 mole of N2? You know it already. It's 28 grams. So instead of 1 mole of N2, I wrote 28 grams of N2. Same. Now, what is the molar mass of H2? 2 grams. Molar mass of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. But I'm given with 3 moles. So what is the mass of 3 moles of H2? 3 2s are 6. So I'll write 6 grams of H2. Gives. What is the molar mass of NH3? 17 grams. That means mass of 1 mole of NH3 is 17 grams. Therefore, mass of 2 moles of NH3 will be 34 grams. So 34 grams of NH3. This particular statement I wrote only in terms of mass. So I can say I'm using mass method here in stoichiometry right now. Yeah. Now, people, I can treat these stoichiometric coefficients directly as volume as well. I can say 1 liter of N2 completely reacts with 3 liters of H2 and produces what? Produces 2 liters of NH3. It is not necessary that you take volume in liters. You can take volume in ml as well. You can say 1 ml of N2 completely reacts with 3 ml of H2 and produces 2 ml of NH3. Done and dusted, right? So first of all, you should be in a position to write all these 3 statements for a particular equation. Whenever you are given with a chemical equation, perfect, you should be in a position to write all these 3 statements, be it in terms of moles, be it in terms of mass, be it in terms of volume. And my dear students, always will be trying to solve the questions with the help of mole method. No need to remember all the methods. Just remember mole method. And how do we solve the questions with the help of mole method? Before letting you know how do we solve the questions with the help of mole method, I would want to give you certain reactions which are frequently asked. Certain reactions. Number one, remember it. KClO3, when it is heated, it gets converted into KCl. With that, you get O2 gas. This is one reaction which you have to remember. Number 2, calcium carbonate upon heating gives calcium oxide plus carbon dioxide. Number 3, acid plus base, what does it give? It gives salt and water. Okay, it gives salt and water. Number 4, whenever you have got the hydrocarbon like this, CXHY, it can be methane, CH4, C2H6, whatever, right? When you do its combustion, it produces always carbon dioxide and water. There is one general way to balance this particular equation. See, this is X, this can be X here, this is Y, it has to be Y by 2, and the stoichiometric coefficient of oxygen has to be X plus Y by 4, right? Similarly, if you have got a compound like this, CXHYOZ, like glucose, C6H12O6, if you do its combustion, it will again lead to the formation of carbon dioxide and water only. How do we balance this type of the reaction? This is X here, so make it X. This is Y here, so make it Y by 2, and make this as X plus Y by 4 minus Z by 2. This is how you balance this particular reaction. Okay, perfect. Similarly, guys, I want you to remember one more thing. Sodium bicarbonate, NaHCO3, when you heat it up, it gives sodium carbonate plus water plus carbon dioxide. This reaction also you would have seen somewhere, right? Similarly, one more reaction. BaCl2 plus Na3PO4. What does it give? It gives Ba3PO4 whole twice plus NaCl. This one more reaction which you need to remember. Now, my dear students, let's try to see the questions which can be asked. I'll be starting from the basic question. From zero, I'm starting. Basic. I'll be trying to solve all the questions with the help of which method? I'll be trying to solve all the questions with the help of mole method. The question is, calculate the mass of O2 produced on heating 12.25 grams of KClO3. This is the question. So imagine that you've got a container, and in that container you have kept 12.25 grams of KClO3. In that container you have kept 12.25 grams of KClO3. Now you are heating that. You are heating 12.25 grams of KClO3. Calculate the mass of O2 that will be produced. Since you know, when KClO3 is heated, it gives you what? It gives you KCl, and with KCl you get O2 gas, right? So O2 gas is produced through this particular reaction. You know it. Yeah. Now, I'll be solving all the equations with the help of mole method. In the mole method, the first thing which you need to do is to balance the reaction. So try to balance the reaction. Reaction is balanced. After balancing the reaction, convert the given quantity into number of moles. I am given with the mass of KClO3. Convert the mass of KClO3 into moles of KClO3. Moles of KClO3 is equal to given mass of KClO3 in grams divided by molar mass of KClO3. The value comes out to be 0.1. So as per the question, we are heating 12.25 grams of KClO3. That means we are heating 0.1 moles of KClO3. Now guys, this is the one whose data is given. This is the one whose data is to be calculated. The one whose data is given, the one whose data is calculated. I just have to relate these two. I've got nothing to do with KCl here. I can say, as per stoichiometry, from stoichiometry, I got to know 2 moles of KClO3 upon heating. 2 moles of KClO3 upon heating produces 3 moles of O2. 2 moles of KClO3 upon heating produces 3 moles of O2 from stoichiometry. Therefore, 1 mole KClO3 upon heating, 1 mole KClO3 upon heating produces 3/2 moles of O2. If I use the unitary method, 1 mole of KClO3 upon heating produces these many moles of O2. But as per the question, do I have to heat 1 mole of KClO3? No, I need to heat 0.1 moles of KClO3. So I can say 0.1 moles of KClO3 upon heating produces 3/2 multiplied by 0.1. The value comes out to be 0.15 moles of O2. So these many moles of O2 are produced. Right? These many moles of O2 are produced. But am I supposed to calculate moles of O2? No. I'm supposed to calculate mass of O2. How do you convert moles into mass? Mass of O2 will be equal to moles of O2 multiplied by molar mass of O2. As simple as that. This is 0.15 and this is 32. The value comes out to be 4.8 grams. So I would say 4.8 grams of O2 are produced when we do the decomposition of 12.25 grams of KClO3. Am I clear? Am I clear, people? Say it in the chats. Am I clear? One more thing. Remember it directly. One more thing. People, I wrote a statement over here in this format. The one whose data is given and the one whose data is to be calculated, they are to be related. And remember, the one whose data is to be calculated, that has to be on the right side of this statement always. The one whose data is to be calculated, that has to be on the right side of the statement always. Okay? In this question, I was supposed to calculate the mass of oxygen. So O2 is the one whose data was to be calculated. That's why it's on right side. If I was supposed to calculate something about KClO3, then I was supposed to reverse the statement. I believe it's clear. One more question. Simple question. Understand. Calculate the volume of carbon dioxide produced at STP by complete combustion of 570 grams of octane. Now tell me the formula of octane first of all. C8H18. This is your octane. You are doing the combustion of octane. That means you are making it to react with what? You are making it to react with O2. It will lead to the formation of carbon dioxide, and with carbon dioxide, there is water. With carbon dioxide, there is water. With carbon dioxide, there is water. You know it. Now, my dear students, tell me one thing. Tell me one thing. Tell me one thing. Which method we are going to use? Mole method. In the first thing which we do in the mole method, we balance the reaction. And I've already told you how do we balance it. This is x. X is 8, so this is 8. Y is 18. Y by 2 makes it 9. X plus y by 4 makes it 25 by 2. Simple. After this, convert the given quantity into number of moles. What is my given quantity? Check it. I'm given with mass of octane. I'm given with mass of octane. So I'll be calculating number of moles of octane, which will be equal to mass of octane in grams divided by molar mass of octane. The value comes out to be 5. So as per the question, we are doing the combustion of 570 grams of octane. What does that mean? That means we are doing the combustion of 5 moles of octane. We are doing the combustion of 5 moles of octane. That means we have to do the combustion of 5 moles of octane basically. Now, the one whose data is given and the one whose data is to be calculated, they are to be related. That's it. They are to be related. Perfect. And the one whose data is to be calculated, that has to be on the right side of the statement. I'll write the statement. From stoichiometry, I know 1 mole octane, when it undergoes combustion, it produces 8 moles of carbon dioxide. It produces 8 moles of carbon dioxide. As per the question, do I have to do the combustion of 1 mole of octane? No, I have to do the combustion of 5 moles of octane. So when 5 moles of octane undergoes combustion, I'll say 8 multiplied by 5, 40 moles of carbon dioxide are produced. 40 moles of carbon dioxide are produced. But am I supposed to calculate moles of carbon dioxide produced? No, I'm supposed to calculate volume of carbon dioxide. How do we convert moles into volume? Volume of carbon dioxide at STP is equal to moles multiplied by 22.4 liters. The value comes out to be 896 liters. So I would say 896 liters of carbon dioxide will be produced when we do the combustion of 570 grams of octane, when we do the combustion of 5 moles of octane. If I'm clear, let me know once in the chats. Everyone. Everyone, people. Everyone. Quickly. Yeah? Done? I want you to say it in the chats, guys. Please and please do not sleep. I do not want you guys to sleep. I do not want you guys to sleep. One more question with this and then we'll move ahead. Can you give this question a try? Can you give this question a try, guys? Look at the question carefully. Simple question again. Again, one simple question. You are given with the reaction and the reaction is given in the balanced format. How many grams of NO2? How many grams of NO2? How many grams of NO2 are required to produce 25.2 grams of HNO3? The reaction is balanced. The first thing, convert the given quantity into number of moles. Right? We are given the mass of HNO3. So we'll calculate the moles of HNO3 first, which will be equal to given mass of HNO3 in grams divided by molar mass of HNO3, that is 63 grams per mole. What is the value coming out to be after solving this? How much it comes out to be? How much it comes out to be? I think it will be 0.4 approximately, right? It will be approximately 0.4, right? I hope so. It is 0.4, correct? It will be 0.4. So I converted the given quantity into moles, right? Now, I just have to relate these two things. And the one whose data is to be calculated, that has to be on the right side. So I'll write the statement like this. I'll say from the stoichiometry, 2 moles of HNO3 are produced from 3 moles of NO2. 2 moles of HNO3 are produced from 3 moles of NO2. Therefore, 1 mole HNO3 is produced from 3 by 2 moles of NO2. Therefore, 0.4 moles of HNO3 As per the equation, 0.4 moles of HNO3 will be produced from 3 by 2 multiplied by 0.4 moles of NO2. The value comes out to be how much? 0.6 moles of NO2. So as per the equation, we got to know 0.6 moles of NO2 are required to produce 0.4 moles of HNO3. Now, am I supposed to calculate moles of NO2? No. What am I supposed to calculate? I'm supposed to calculate mass of NO2. How do you convert moles into mass? How do you convert moles into mass? Mass of NO2 is equal to moles of NO2 multiplied by molar mass of NO2, which will be how much? 46, right? Is this going to be 46? 46 multiplied by 0.6, approximately it will be 27.6 grams. 26.7 grams of NO2, 27.6 grams of NO2 are required to produce 25.2 grams of HNO3. I hope I'm clear. Someone is feeling sleepy, right? Do the same in the examination hall as well, yeah? It'll be good for you. I hope people, I'm clear with all these things. Yeah? Yeah? Someone was feeling sleepy, of course, they should sleep, right? They should know exactly. From 2 to 5:20. Yeah? You need to sleep. Do you have anything else to say? If you are feeling sleepy? Is there anyone else who is feeling sleepy? Is there anyone else who is feeling sleepy? Is there anyone else who is... someone is going to sleep after NEET. That's good. That's nice. आप कहाँ हो आज सर? मैं हूँ कश्मीर में घर पे. Yes, there'll be breaks in between. Just wait, guys. We just have studied we have started 1.5 hours before. Even after NEET, I too will sleep. Chalo, let's have a look on one more important concept, that is a limiting reagent, right? This again, one very important concept which you need to know. What is limiting reagent first of all? How do you define the term limiting reagent? My dear students, limiting reagent, it's basically defined as the reactant which gets completely consumed, the reactant which gets completely consumed earlier in the reaction. Completely consumed earlier in the reaction is what you call as the limiting reagent, and the other one is called as excess reagent. And the other one is called as the excess reagent. Now, what is meant by that? Try to understand carefully what is limiting reagent, because this is something which is very, very, very important. My dear students, for example, you have got a balanced chemical equation like this. A plus B gives C plus D. It is one balanced chemical equation. Imagine that. Okay. Let's say I'm writing at time t is equal to 0. Time t is equal to 0 means the reaction has not started. Time t is equal to 0 means reaction has not started. Reaction has not started means products have not got formed yet. Products have not got formed yet, right? So initially at time t is equal to 0, what do I have? I'll be only having reactants with me. Imagine I've got a container in which this reaction has to take place. At time t is equal to 0, before the start of the reaction, there will be only reactant present. You know it, right? Let's say you have got 10 moles of reactant A and 5 moles of reactant B in the container initially. And right now, I'm assuming reaction has not started. So this is 0, this is 0. Whenever in a question you are given with the amounts of all the reactants, whenever in a question you are given with the amounts of all the reactants, at that point of time, you'll be using the concept of limiting reagent. Okay, here you are given with the amounts of all the reactants. So over here I'll be using the concept of limiting reagent. Now, my dear students, when the reaction will start, when these reactants will start reacting and forming the products, what will happen to the moles of reactants with time? Moles of reactants with time will decrease, right? Can I say out of these two reactants, there will be one reactant which would have got completely consumed? I'm assuming this B is the reactant which got completely consumed earlier in the reaction. So you are left with 0 moles of B. That reactant which gets completely consumed earlier in the reaction, that's something which you call as limiting reagent. Other one is what you call as excess reagent, right? And people, it's clear. When one of the reactant is consumed completely, right? This A, this what I call as excess reagent. That means out of 10 moles of A, there will be some moles of A still left in the container. Similarly, some moles of C and some moles of D would have got formed as well. But tell me one thing. When one of the reactant is completely consumed, can I say at that point of the time, the reaction would have stopped? Absolutely, the reaction would have stopped. Absolutely, the reaction would have stopped. That particular reactant which gets completely consumed earlier in the reaction, that's called as limiting reagent. Other one is called as excess reagent. Excess reagent does not get completely consumed. There will be some amount of excess reagent still left in the container, right? And there would be some products which would have got formed. As simple as that. Now, how do we use this concept in the questions? That's the point. That is the point. My dear students, one question and every single thing will be done in that particular question. For example, I'm given with a reaction N2 plus H2 gives 2 times NH3. Understand what I say. See what kinds of questions can be asked. Imagine at time t is equal to 0. I'm given with 10 moles of N2. I'm given with 10 moles of H2 and this is 0. So first of all, which concept do I need to use here? I'm given with the amounts of all these reactants. I need to use the concept of limiting reagent. And my dear students, whenever we need to use the limiting reagent concept, the first thing is balance the reaction. The reaction is already balanced. Right? After balancing the reaction, we are supposed to identify the limiting reagent. How do we identify the limiting reagent? Have a look. See, one simple trick. You have got N2, you have got H2. Stoichiometry coefficient here is 1, here is 3. How many moles of N2 are given? 10. How many moles of H2 are given? 10. Divide the given moles of reactants by their respective stoichiometric coefficients. The one which gets the lesser value, that's always your limiting reagent. So this is getting the lesser value, so H2 is my limiting reagent. I hope you got to know how to identify, right? So H2 is my limiting reagent. If H2 is my limiting reagent, I'll be left with nothing of H2. The reaction would have stopped. Okay, this is what you call as excess reagent. Perfect. So there will be some moles of N2 which will be present in the container. There will be some moles of NH3 which would have got formed. Now, how to get to know how many moles of NH3 have got formed? How many moles of N2 are still in the container? How do we check that? Understand. All the data will be given by the limiting reagent. So people have a look. When I relate limiting reagent with NH3, I'll say 3 moles of limiting reagent produces 2 moles of NH3. Limiting reagent is the one which decides everything. 3 moles of limiting reagent produces 2 moles of NH3. Therefore, 1 mole of limiting reagent produces 2 by 3 moles of NH3. 2 by 3 moles of NH3. 1 mole of limiting reagent produces these many moles of NH3. Therefore, 10 moles of limiting reagent. Therefore, 10 moles of limiting reagent produces 2 by 3 multiplied by 10. The value is 6.66 moles of NH3. So I got to know at the end of the reaction, 6.66 moles of NH3 would have got formed. This is point number 1. Point number 2. Out of 10 moles of excess reagent, how many moles of excess reagent will be left in the container? How do we check that? See guys, again limiting reagent is going to decide that. Relate the limiting reagent with N2 now. Right? And how do I relate it? I relate it like this. I'll say 3 moles of limiting reagent. 3 moles of limiting reagent reacts with 1 mole of N2. Reacts with 1 mole of N2. So 1 mole of limiting reagent reacts with 1 by 3 moles of N2. Therefore, 10 moles of limiting reagent would have reacted with 1 by 3 multiplied by 10. The value is 3.33 moles of N2. So I got to know 10 moles of limiting reagent have reacted with 3.33 moles of N2. So 3.33 moles of N2 have reacted. How many did I take? I took 10. Out of 10, how many are reacting? 3.33. So 10 minus 3.33 will be 6.66. So these are the moles of N2 which shall be still left in the container as such. Right? These are the moles of N2 which will be still left in the container as such. So you got to know the moles of NH3 formed. You got to know moles of N2 left. Now, if they do not ask you the data about moles, let's say they're asking you, calculate the molecules of NH3 formed. Calculate the molecules of NH3 formed. You got the moles multiplied by Avogadro's number. That will give you the molecules. Let's say they are asking you, calculate the mass of NH3 formed. You got the moles multiplied by molar mass of NH3. That is mass of NH3 formed. What is the mass of excess reagent left? These are the moles of excess reagent left. Multiplied by its molar mass, you'll be getting the mass of excess reagent left. How many molecules of N2 are left? How many molecules of N2? Moles of N2 left. Multiplied by Avogadro's number. Anything can be asked. Am I clear? Am I clear, people? Am I clear, people? Quick. Am I clear? Now, I'm going to give you one question which you'll be solving, and that's it. And that's it. Tell me the answer of this question. Very simple and basic. And I have given the reaction already in the balanced format. Quick. Be very quick now. The reaction that's given, that is 6 times LiH plus 8 times BF3. What does it give? It gives 6 times LiBF4 plus what? Plus B2H6. Plus B2H6. As per the question, at time t is equal to 0, we are starting with 2 moles of each of reactants. We are starting with 2 moles of each of reactants. How many moles of B2H6 can be produced? How many moles of B2H6 can be produced? The first thing, is the reaction balanced? Yes, the reaction is balanced. Now, identify the limiting reagent. How? Divide the given moles by the respective stoichiometric coefficients. 2 divided by 6. 2 divided by 8. Whose value will come out to be less? Is 2 by 6 less or 2 by 8 less? I'll say 2 by 8 is less. So this is the limiting reagent. This is the one which is going to decide everything. Right? This is the one which is going to decide everything. What do we have to calculate? Moles of B2H6 formed. So just relate limiting reagent with B2H6. So I'll say 8 moles of limiting reagent. 8 moles of limiting reagent gives 1 mole B2H6. 8 moles of limiting reagent gives 1 mole B2H6. Therefore, 1 mole limiting reagent gives what? Gives 1 by 8 moles of B2H6. 1 by 8 moles of B2H6. Therefore, 2 moles of limiting reagent. 2 moles of limiting reagent gives 1 by 8 multiplied by 2. The value is 1 by 4, which will be 0.25 moles of B2H6. So these many moles of B2H6 would have got formed at the end of the reaction. This is something which I was supposed to calculate. Am I clear? Am I clear, people? Am I clear, people? Say it in the chats quickly. Everyone. Everyone in the chats. Everyone. Yeah? So I hope you can do the questions when it comes to the topic limiting reagent. I hope it's super clear to you. Right? I hope it is super clear to you. Guys, one question I want you guys to solve right now. Can you do it? Can you do this question? I do not know whether I'll be doing thermodynamics in this marathon or in the next marathon, right? Let's see how much we can finish today, and the rest of the things we'll be finishing in the next marathon. You need not worry. Okay, first of all, can you do this question on your own? Can you do this question on your own? Quick. Done? See guys, we are given with 10 moles each of reactants. 10, 10, 0, 0. Now identify the limiting reagent. 10 divided by 3, 10 divided by 2. This is limiting. What do we have to calculate? Calculate the moles of Ba3PO4 whole twice. So relate limiting reagent with this. 3 moles gives 1 mole. 1 mole gives 1 by 3. So 10 moles gives 10 by 3. So the answer is 3.33. 3.33 moles of barium phosphate would have got formed. It is very simple and basic. Okay. Now, people, comes one more topic. That is percentage yield. Have you heard about the term percentage yield? This again important. Percentage yield. Before doing the questions, I'll first of all give you the result. Calculate percentage yield. Result by means of which you can calculate the percentage yield. Remember the result, then I'll show you how it's to be done. See guys, percentage yield is always equal to experimental amount or the actual amount. Experimental amount or the actual amount divided by expected amount divided by expected amount multiplied by 100. This is the formula by means of which we calculate the percentage yield of the reaction. Okay, this is the formula by means of which we calculate the percentage yield of the reaction. Remember, this experimental yield, it will be most of the times given to you in the question itself, right? And expected amount, we always calculate with the help of stoichiometry. Expected amount, we always calculate with the help of stoichiometry. This will be given to us in the question, right? This we calculate with the help of stoichiometry. Once we get the two amounts, multiply with 100, we get the percentage yield. For example, this is the question. This is the question. We are given with a reaction that is calcium carbonate. Calcium carbonate upon heating reduces calcium oxide plus carbon dioxide. This is the reaction which we have. This is the reaction which we have. As per the question is concerned, on heating 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. This is something given to us in the question. On heating 40 grams of calcium carbonate, 20 grams of calcium oxide is produced. So it is given to us in the question. And in the question, which data is given? Experimental data. So it has been seen experimentally that when you heat 40 grams of calcium carbonate, 20 grams of calcium oxide are produced. So this has been observed experimentally. So this 20 grams, it was observed 20 grams of calcium oxide is produced as per the question. So your experimental amount is equal to what? 20 grams. So I got one term, experimental amount. What do I need now? What do I need now? What do I need now? I need expected amount. How do I get the expected amount? With the help of stoichiometry. Understand. Reaction is balanced. Reaction is balanced. Now, let me use the mass method in stoichiometry. Tell me one thing. What is the mass of 1 mole of calcium carbonate? The mass of 1 mole of calcium carbonate means molar mass of calcium carbonate, which is how much? 100 grams. What is the mass of 1 mole of calcium oxide? That means molar mass of calcium oxide, 56 grams. So can I say as per stoichiometry, 100 grams of calcium oxide, 100 grams of calcium carbonate. When you heat 100 grams of calcium carbonate, as per stoichiometry, 56 grams of calcium oxide should get formed. Yes. As per stoichiometry, 100 grams of calcium carbonate when heated should produce 56 grams of calcium oxide. So 1 gram calcium carbonate upon heating should produce how much? 56 divided by 100 grams of calcium oxide. Therefore, 40 grams of calcium carbonate, 40 grams of calcium carbonate upon heating should produce how much? Should produce how much? These many grams of calcium oxide. This will come out to be 22.4 grams of calcium oxide. So, my dear students, I used stoichiometry and I got to know with the help of stoichiometry that when you heat 40 grams of calcium carbonate, these many grams of calcium oxide should produce. These many grams of calcium oxide should produce. This is something which I got with the help of stoichiometry, right? So, this is the amount of calcium oxide which I was expecting to get formed with the help of stoichiometry. So, this is something which I call as the expected amount. Correct? Now, if I want to calculate percentage yield, which will be experimental amount divided by expected amount multiplied by 100, the value will be 89%. So, this is the percentage yield of the reaction. This is the percentage yield of the reaction, right? My dear students, try to understand one thing. If the yield of the reaction was 100, if the yield of the reaction was 100%, at that point of time, whatever amount of calcium oxide you would have expected with the help of stoichiometry, same would have been the actual amount of calcium oxide formed in the lab. if the yield of the reaction was 100%. Okay? Here the yield of the reaction is 89%. That means whatever you expected to get formed, not the entire amount will get formed in the lab. Only 89% of this amount will get formed in the lab. Only 89% of this amount will get formed in the lab. I hope I'm clear. I hope I'm clear, people. Yes. Right? Let's solve one more question with the help of which it will be completely clear to you. Completely clear to you. Okay, one more question on this. One more question on this. As per the question is concerned, my dear students, there is a reaction given and it said that 15.6 grams of benzene produces 18 grams of nitrobenzene. Something which is given to us in the question. In the question, what do we get? In the question, we get the experimental amount. So it has been observed that when you heat 15.6 grams of benzene, you get 18 grams of nitrobenzene. So this is something which has been observed in the lab. So I'll be calling this particular amount as experimental amount. Now what do I need? I need expected amount. I need expected amount. What do I do for that? I'll be using stoichiometry. I'll be using stoichiometry to get the expected amount. So this is one, this is one. The mass of 1 mole of benzene is how much? 78 grams, which is the molar mass. What is the mass of 1 mole of nitrobenzene? That means molar mass of nitrobenzene, I think it will be 123 grams. So with the help of stoichiometry, I can say 78 grams of benzene should produce 123 grams of nitrobenzene. Therefore, 1 gram of benzene should produce how much? 1 gram of benzene should produce 123 divided by 78 grams of nitrobenzene. And therefore, 15.6 grams of benzene, 15.6 grams of benzene should produce how much? Should produce how much? Multiplied by 15.6 grams of nitrobenzene, right? This value will come out to be 24 grams. So as per stoichiometry, I got to know that 24 grams of nitrobenzene should get produced. Should get produced. So this is something which I was expecting to get formed. This is my expected amount. How much is actually getting produced? Only 18 grams of nitrobenzene. Now, calculate the yield. Yield is experimental divided by expected multiplied by 100. Solve it. I think the value comes out to be 73, 75, something like that. I hope this is clear to everyone. I hope this is clear to everyone. Right? I hope this is clear to everyone. Now comes one more topic. That is percentage purity. Yes, if the yield of the reaction is 100%, at that point of time, experimental and expected will be the same. Yeah? All right. Percentage purity. Percentage purity. Let me first of all write the formula. Percentage purity of a compound in an impure sample. In an impure sample is equal to mass of the pure compound in grams divided by the mass of impure sample multiplied by 100. Now let me make you understand first of all what this percentage purity is all about. It's an important concept from which a question was asked last year as well. Right? A question was asked last year as well. Guys, try to understand what exactly I'm going to say. Try to understand carefully. Imagine that you've got a container. This is a container. In this particular container, for example, you have kept calcium carbonate. Right? You have kept calcium carbonate. Let's say with calcium carbonate, there is something else present as well. A plus B plus C. I don't know what this A plus B plus C is. This A plus B plus C I'm calling as impurities. A plus B plus C I'm calling as impurities. Now tell me, in the container, do we have pure calcium carbonate or we have got impure sample of calcium carbonate? We have got impure sample of calcium carbonate. I'm assuming that the mass of the whole sample, the mass of the impure sample of calcium carbonate is, for example, 50 grams. Right? Now, in the 50 grams of complete sample, let's assume that 25 grams is the mass of pure calcium carbonate. 25 grams is the mass of pure calcium carbonate. 25 grams is the mass of pure calcium carbonate. 25 grams is the mass of pure calcium carbonate. If I need to calculate the percentage purity of calcium carbonate in this particular sample, what do I need to write? Percentage purity of calcium carbonate in the sample is equal to mass of pure calcium carbonate. How much is that? 25 grams divided by mass of impure sample of calcium carbonate. How much is that? 50 grams multiplied what? Multiplied by 100. Multiplied by 100. Okay, multiplied by 100. Perfect. How much this value will come out to be? This 1, this 2, this is 50. So percentage purity of calcium carbonate in this sample is 50. What does that mean? That means, as per definition, that means 50 grams of pure calcium carbonate. 50 grams of pure calcium carbonate is present in 100 grams of the impure sample. Right? So percentage purity of a compound in a sample, what does it mean? It means that mass of pure compound, let me write the definition. That mass of the pure compound which is present in 100 grams of the impure sample. Which is present in 100 grams of the impure sample. I hope you got to know the meaning of all this stuff, right? Number one. Number two, before solving the equation, remember, in the reactions only pure substance participates. In the reactions only pure substance participates. Pure substance participates. Impurities, they do not participate in the reaction. Impurities do not participate in the reaction. Remember this? Okay. Now, I'm going to give you one statement. You need to decode that statement. See guys, I'm writing something like this. I'm writing 40 grams of 80% pure calcium carbonate. 40 grams of 80% pure calcium carbonate. What it means? 40 grams of 80% pure calcium carbonate. If you see a statement written like this, how do we decode this statement? See, this 40 grams, this is the mass of the whole impure sample of calcium carbonate. This is the mass of whole impure sample of calcium carbonate. Now, out of these 40 grams, how much is pure calcium carbonate? 80%. 80% of these 40 grams, which will come out to be 32. So 32 grams is basically the mass of pure calcium carbonate. The mass of pure calcium carbonate. So in total, the whole sample is 40 grams. Out of 40 grams, 32 grams is the mass of pure calcium carbonate. So 8 grams will be the impurities. Right? 8 grams will be the impurities. I hope this is clear. Perfect. Right? Now guys, understand? Try to solve this question. When we start next lesson, sir? Once we complete this, then only we can go to the second one, right? I don't want to skip any topic, guys. Okay? 50 grams of 80% pure calcium carbonate is heated. Calculate the volume of carbon dioxide gets produced at STP. So basically, tell me one thing. When calcium carbonate is heated, what do we get? We get calcium oxide plus carbon dioxide. What do we need to calculate? Volume of carbon dioxide. Tell me one thing, people. 50 grams of 80% pure calcium carbonate. Tell me, what is the mass of pure calcium carbonate that's given to us? What is the mass of pure calcium carbonate that's given to us? That is 80% of 50 grams. So the sample which we have, in that sample, we have got 40 grams of pure calcium carbonate, right? 40 grams of pure calcium carbonate. So how many pure moles of calcium carbonate do we have? Pure moles of calcium carbonate. Pure mass of calcium carbonate divided by molar mass of calcium carbonate. So these are the pure moles of calcium carbonate. In the reaction, only pure substance participates. Impurities do not participate. Now we are done. Impurities do not participate. I can say, as per the stoichiometry, 1 mole calcium carbonate, when you heat it up, 1 mole carbon dioxide is produced. 1 mole carbon dioxide is produced. Therefore, 0.4 moles of calcium carbonate upon heating will produce 0.4 moles of carbon dioxide. So we got the moles of carbon dioxide produced. And my dear students, was I supposed to calculate moles of carbon dioxide produced? No, I'm supposed to calculate volume. So volume of carbon dioxide produced will be moles of carbon dioxide produced multiplied by 22.4 liters. The value will be 8.96 liters. So 8.96 liters of carbon dioxide will be produced. Am I clear? Am I clear, people? Am I clear? Quickly. Is this percentage purity concept clear? How many questions will be asked from physical chemistry? From class 11 physical chemistry, minimum 10, 11 questions will be asked. Yeah? Perfect, guys. I hope you can easily solve the questions which are based on what? Which are based on the percentage purity. Okay? Perfect. Now comes one of the easiest topics and the topic from which questions are frequently asked. What is that? Empirical molecular formula. Have you heard about this one? Empirical molecular formula. Empirical molecular formula. Let's have a look, people. What kind of questions are asked from empirical molecular formula? First of all, let's understand what empirical molecular formula is all about. See, guys. First of all, let's say I'm talking about glucose. Do you know any formula for glucose? Do you know? You should be knowing it, guys. C6H12O6, right? Okay. If I ask you what is the ratio over here, 6:12:6. This is the ratio. This is the ratio of the atoms. This is a normal ratio. Or is it the simplest ratio? Can you simplify it further? You can simplify it further. When you simplify it, if you divide it throughout by 6, this becomes 1:2:1. This ratio over here, I'm calling as simplest ratio. This ratio over here, I'll be calling as actual ratio. Right? As per actual ratio, the formula is this. Perfect. So this formula I'll be calling as molecular formula. And as per simplest ratio, the formula has to be C1H2O1. This is what I call as empirical formula. Okay? The one which gives the simplest ratio, that is empirical formula. The one which gives the actual ratio, that is the molecular formula. Number one. So one is your empirical formula, one is your molecular formula. Now. With the help of molecular formula, you can calculate molecular mass. With the help of what? With the help of molecular formula. Right? Calculate the molecular mass. 12 multiplied by 6 plus 1 multiplied by 12 plus 16 multiplied by 6. The value comes out to be 180 U. This is the molecular mass of glucose. With the help of empirical formula, you can calculate empirical mass. How much is that? 12 multiplied by 1 plus 1 multiplied by 2 plus 16 multiplied by 1. The value comes out to be 30 U. So you got the molecular mass as well, you got the empirical mass as well. Once you get molecular and empirical mass, my dear students, I'm going to write a number N. What is N? N is just the ratio of, molecular mass to that of empirical mass. N is just the ratio of molecular mass to that of empirical mass. If I ask you, what is the N value for glucose? You'll say molecular mass of glucose is 180 divided by 30. The value of N is 6. And once you get N value, my dear students, remember molecular formula is always equal to empirical formula multiplied by N. Empirical formula multiplied by N. Now guys, just these things you have to remember. We are sorted. Now, how do we apply all this? How do we get questions on this? Before that, there is one more result which I would want you guys to remember. Do remember, molar mass is equal to 2 times the vapor density. Sometimes in a question, they give you the vapor density of a compound. Sometimes in a question, they give you vapor density of a compound. From vapor density, you just have to multiply that by 2. You'll be getting the molar mass. Okay, remember this one as well. For example, let's see what kind of questions are asked. Okay, and I'll just tell you simple things by means of which you can solve the questions in lesser time. See guys, directly I'm taking a question. Try to understand. Calculate the empirical formula of the compound that contains 26.6% of potassium, this much percentage of chromium, this much percentage of oxygen by weight. So you have got a compound. Which contains 3 elements. What are the elements? Potassium, chromium, oxygen. You have got a compound which has got 3 elements. Potassium, chromium, oxygen. The mass percentage of these is given. Mass percentage of potassium in the compound is this much. Mass percentage of chromium in the compound is this much. Mass percentage of oxygen in the compound is this much. Right? What do we have to get? We have to calculate empirical formula. How do we calculate empirical formula? There is a general way of getting the empirical formula. First of all, you should know the atomic masses of all these elements. First of all, you should know the atomic mass of all these elements. Okay? First of all, you should know the atomic mass of all these elements. Once you know the atomic mass of all these elements, what is the second thing which you need to do? Whatever percentage is given to you, divide the percentage by the atomic mass. Divide this percentage by its atomic mass. Divide this percentage by its atomic mass. On dividing, what do we get? We get the atomic ratio. You call this as atomic ratio. You call that as atomic ratio. You call this as atomic ratio. So what am I supposed to do? Given percentage, divide by atomic mass. What do we get? Atomic ratio. Now tell me one thing. Which one is the least number among these three numbers? 0.68. I'll be dividing all these three numbers by that least number. Okay. What do I get? I got the least atomic ratio. This was atomic ratio. Now I'll be calling this as least atomic ratio. Now the atomic ratio here is coming out to be 1:1:3.5. Atomic ratio here is coming out to be 1:1:3.5. No doubt, it's the least atomic ratio. But is it the simplest ratio? Is it the whole number ratio? I mean, this is not the whole number ratio. So convert it into whole number ratio. So multiplying throughout by 2. This becomes 2:7. This particular ratio, should I be calling this as the simplest whole number ratio? Yes. Right? And formula as per this will be K2 CR2 O7. Right? And this particular formula you'll be calling as empirical formula. Am I done? Right, people? Are we done with this? One more question. One more question. A compound contains two elements, A and B, A and P, right? Perfect. Two elements, A and B, combined to yield the percentage by mass. Percentage of A is given as 75.08. Therefore, percentage of B will be 100 minus this, which will be how much? Almost 24. Almost 24 point something, 24.92 something, I believe. Right? Perfect. These are the percentages that are given to us. Now, atomic masses of A and B are given to us. What is the atomic mass of A? That is 75. What is the atomic mass of B? That's 16. Now, what do we get? Atomic ratio. How? This divided by this, the value is 1. This divided by this, the value is how much? 1.5, I think. Yeah? 24 divided by 16. That will be approximately 1.5 only. Okay? We got the atomic ratio. We got the atomic ratio. Since we got the atomic ratio, what do we need to calculate now? Least atomic ratio. So divide them by the simplest number, by the least number. Least number is 1. The value here is 1. The value here is 1.5. Perfect. The value here is 1. The value here is 1.5. Now, is this 1:1.5? Should I be calling this as simplest whole number ratio? No. I'll be dividing this by 2. This becomes 2. This becomes 3. So the formula becomes A2B3. Right? And this is what you call as empirical formula here. Are we done? Are we done with this? Are we done with this? Quick. Are we done with this, guys? Are we done with this? Look at one more type of the question. Look at one more type of the question. You have got a compound that contains hydrogen, carbon, chlorine. Its molar mass is this. What will be the molecular formula of the compound? What will be the molecular formula of the compound? My dear students, you know, in order to get the molecular formula, what do we need? We need empirical formula. Once we get empirical formula, multiply that with n. That is the point, basically. So first of all, my first point is to calculate what? Empirical formula. And, you know, empirical formula stuff is same, right? You do the process, you get the empirical formula. Empirical formula over here you got as H2C1Cl1. H2C1Cl1. This is the empirical formula. This is the empirical formula, right? From the empirical formula, what can I calculate? I can calculate empirical mass. What will be empirical mass? 1 into 2 plus 12 into 1 plus 35.5 into 1. That will be approximately how much? Approximately it will be 49 grams. Approximately it will be, approximately it will be 49 U. This is the empirical mass. right? My dear students, since you got empirical mass, can I calculate molecular mass? Molecular mass is given to us as with the equation, right? 98.96 U. This is the molecular mass. You have empirical mass, you have molecular mass. Can I get the N value? N value is basically molecular mass divided by what? Divided by empirical mass. What is molecular mass and what is empirical mass? Molecular mass is 98. Empirical mass is how much? 49. The value comes out to be 2. If you got the N value, we are done, guys. Molecular formula is equal to. Empirical formula was H2C1 Cl1 multiplied by N. That's 2. So it is at the end C2 H4 Cl2. This is the molecular formula of the compound. I hope you can solve this sort of equation. Right? Perfect, guys. Perfectly done. Yeah. Now, have you heard about something called as concentration terms? The last topic of the chapter. Concentration terms. This is the last topic of the mole concept chapter. This is the last topic of the mole concept chapter. Laws and all that is outdated. Perfect. Do not study gas laws. I mean these laws of chemical combination. That's outdated. Concentration terms. My dear students, first of all, if I talk about solution, if I talk about a solution, just tell me in the chats, how many components a solution has? You tell me that. How many components a solution has? 2 components. One is what you call a solute. One is what you call a solvent. Perfect. Solute, you are going to represent by number 1. Solvent, you are going to represent by number 2. Okay. Now. How do you define solute? It is that component of the solution which is present in lesser amount. And this is that component of the solution which is present in larger amount. Which is present in larger amount. Okay. Which is present in larger amount. First of all, do remember, mass of the whole solution is always equal to mass of solvent plus mass of solute. Mass of solvent plus mass of solute. Perfect. Do remember, whatever is the phase of solvent is equal to the final phase of the solution. Final phase of the solution. Remember this. Sometimes you'll be given with something as binary solution. What is a binary solution? Binary solution is the one which has got 2 components, out of which one solute and one solvent. One solute, one solvent. Right? Ternary solution. What is that? What is that? 2 solutes and 1 solvent. 3 components. Quaternary solution. 4 components. 3 solute components and 1 solvent components. So that particular solution which has got 2 components is your binary, right? You know it. Perfect. Binary, ternary, quaternary. Sometimes they'll mention a term, aqueous solution. Aqueous solution is the one wherein the solvent used is water. Aqueous solution is the one wherein the solvent used is water. Okay, solvent used is water. Now guys, the first concentration term which we have, that is what you call as mass percentage of solute. Or you call it as weight by weight percentage of solute. Weight by weight percentage of solute. Now how do you define this particular term? How do you define it? Let me not define it. How do you calculate it? How do you calculate weight by weight percentage of solute? It is equal to mass of solute in grams divided by, directly I'm going to give you the formulas. You have to remember all these formulas, okay? Mass of solute in grams divided by mass of solution in grams multiplied by what? Multiplied by 100. This is how you calculate weight by weight percentage of solute. This is how you calculate weight by weight percentage of solute. Number 1. Number 2. How do we calculate weight by volume percentage of solute? Weight by volume percentage. This is also asked. I'll show you its application in some time. But before that, we have to write all the results. Okay, weight by volume percentage of solute. How do you do that? Mass of solute in grams divided by volume of solution in ml multiplied by 100. Multiplied by 100. Okay? Right? The third one, that is volume by volume percentage of solute. How do we calculate the volume by volume percentage of solute? It is equal to volume of solute in ml divided by volume of solution in ml multiplied by 100. Multiplied by 100. Similarly, guys, there is one result that connects this and this directly. Weight by volume percentage of solute is always equal to weight by weight percentage of solute multiplied by density of solution in grams per ml. Remember this one as well. Remember this one as well. I'll show you their application in some time. First of all, you have to remember all these results to calculate all of them. To calculate all of them. Okay. The fifth one. Mole fraction of solute is always equal to number of moles of solute divided by total moles present in the solution. Mole fraction of solvent, number of moles of solvent divided by total moles present in the solution. Divided by total moles present in the solution. Right? Molarity, which is represented by capital M. How do you define molarity, by the way? Number of moles of solute present in 1 liter of solution. How do you calculate it? That's important. That's important. Number of moles of solute divided by volume of solution in liters. Number of moles of solute divided by volume of solution in liters. Okay? Right? Or you can write it like this. Number of moles of solute means mass of solute divided by molar mass of solute. Volume of solution in liters means volume of solution, you can take it in ml and you can multiply here with 1000. This one more result to calculate molarity. There is one more result to calculate molarity directly. Do remember that as well. It is equal to 10 multiplied by weight percentage of solute multiplied by density of solution in grams per ml divided by molar mass of solute. This one more result, by means of which you can calculate molarity. By means of which you can calculate molarity directly. Right? Directly. This molarity, you must be knowing it now. Molarity is temperature dependent term. This is temperature dependent term. So when you change the temperature of the solution, molarity always changes. Right? Perfect. Yeah? Right, people? So you have to remember these results. Now there are few more results, then I'll show you certain questions by means of which you'll understand when to use which formula. See guys, the seventh one, that is molality. That is molality. Molality is represented by M, which is equal to number of moles of solute divided by mass of solvent in kg. Or you can write it as mass of solute divided by molar mass of solute, mass of solvent in grams and multiplied by 1000. Perfect. Similarly, guys, there is one more result. Molality is equal to 1000 multiplied by molarity of the solution divided by 1000 multiplied by density of solution minus molarity multiplied by molar mass of solute. This is one more result. This is one more result. Right? And at the same time, molality can be calculated by one more result. That is mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute multiplied by molar mass of solvent. These are few results which are asked. Nothing apart from these results is asked. Nothing apart from these results is asked. And guys, remember molality. This is temperature independent. This is temperature independent. Okay. Let me give you a few questions so that you understand what kind of questions are asked from these concentration terms. Understand. First question. Let's say the question is like this. Calculate the mole fraction. Calculate the mole fraction of solute in 10% weight by weight of NaOH aqueous solution. NaOH aqueous solution. Can you solve this question? Quickly. It's a simple one. Calculate the mole fraction of solute in 10% weight by weight of NaOH aqueous solution. Quick. First of all, what is meant by this 10% weight by weight of NaOH aqueous solution? It means that 10 grams of NaOH, 10 grams of solute are present in 100 grams of solution. 10 grams of solute are present in 100 grams of solution. Okay. So my dear students, 10 grams of solute, that means mass of solute I calculate as 10 grams. Mass of solvent I calculate as 100 minus 10, which is 90 grams. I calculate mass of solute and mass of solvent. I calculate mass of solute, mass of solvent. Now, can I calculate moles of solute and moles of solvent? Moles of solute is equal mass of solute divided by molar mass of solute. This is mass of solvent divided by molar mass of solvent. This term, W2 by M2. Mass of solute is 10 grams. Molar mass of solute, molar mass of NaOH, that's 40. The value comes out to be 1 by 4. Mass of solvent is 90 grams. Molar mass of solvent. Solvent here is water because it's aqueous. So 18, the value comes out to be 5. So you got your N1 as well as N2. If you got your N1 as well as N2, what am I supposed to calculate? Mole fraction of solute. How do I do it? Mole fraction of solute is equal to number of moles of solute divided by total moles present in the solution. Now N2 you have, N1 you have. When you solve this, the value comes out to be 1 upon 21. This is the mole fraction of solute which we were supposed to calculate. Am I clear with this, people? Quickly. I'll give you the break after like 15 minutes. I'll give you the break after 15 minutes. Just wait for some time. Am I clear with this? Number one. For example, you get a question like this. For example, you get the question like this. Calculate the mass of water in grams that has to be added to 16 grams of methanol. To 16 grams of methanol to make its mole fraction. To make its mole fraction as 0.25. Can you solve this one? Can you solve this one? In the last question, 18 was the molar mass of solvent, molar mass of water. Guys, this is again a one simple question, and see exactly how do you deal with this particular question. This is simple. As per the question, imagine that you have got 16 grams of methanol in the container. You have got 16 grams of methanol in the container. As per the question, how much water has to be added? Let's say we are adding some X grams of water. After the addition of X grams of water in the container, I'm assuming the mole fraction of methanol is becoming 0.25. Mole fraction of methanol is becoming 0.25 after the addition of X grams of water. Now, if I ask you how many moles of methanol are there in the container? Mass of methanol divided by molar mass of methanol, 0.5. If I ask you how many moles of water are there in the container? Mass of water divided by molar mass of water. Right? I can say these are the moles of water which has been added to make the mole fraction of methanol as 0.25. Now tell me, mole fraction of methanol means number of moles of methanol divided by total moles present in the solution. Total moles present in the solution, that is equal to 0.25. Now, moles of methanol is how much? 0.5 divided by moles of methanol, 0.5, moles of water, X divided by 18. And this value is equal to 0.25, which means 1 by 4. So when you calculate X from here, X will come out to be 27 grams. So 27 grams of methanol, 27 grams of water has to be added. Then only the mole fraction of methanol will come out to be how much? Then only the mole fraction of methanol will come out to be 0.25. Am I clear? Am I clear? Yes, am I clear? Let me give you one more question, and with that, we'll take a break. And right after the break, we'll start one more chapter. Right after the break, we'll start one more chapter. But before taking the break, one question which you will be solving right now. Okay? For example, I'm giving you a question like this. Dissolving 120 grams of urea. Dissolving 120 grams of urea in 1000 grams of water gives a solution of density 1.15 grams per ml. Calculate molarity of that solution. Calculate molarity of that solution. Quick. Can you give it a try? It's a simple question, guys. So you have got 120 grams of urea, which you are dissolving in 1000 grams of water. So first of all, you identified your solute and solvent. Perfect. So mass of solute, that is given to me. That is 120 grams. Mass of solvent, that's given to me. How much? That is 1000 grams. Therefore, mass of solution will be how much? Mass of solution will be this plus this. That's 1120 grams. Perfect. Now, what is the molar mass of solute? What is the molar mass of urea? Remember, molar mass of urea is 60 grams per mole. Right? What I'm supposed to calculate? Molarity of the solution, which will be nothing but mass of solute multiplied by 1000 divided by molar mass of solute. And this is volume of solution in ml. This is the formula which we'll be using. Now, if I ask you, am I given by W2? Yes. 120 multiplied by what? Multiplied by 1000 divided by molar mass of solute? Yes. But volume of solution is not given. But somehow we have to calculate volume of solution. Somehow we have to calculate volume of solution. How exactly? How exactly? We are given with the density of solution. Density of solution is 1.15 grams per ml. Can I say density of solution is nothing? It is just mass of solution divided by volume of solution, which is equal to 1.15 grams per ml. What is mass of solution? 1120 grams divided by 1.15 grams per ml. That will give you what? That will give you volume of solution. And when you solve this, this will come out to be 973 ml. This is the volume of solution which we calculated from density. If you got the volume of solution, so put it here. Put the volume of solution here. And when you put the volume of solution here, what do I get? The value, final value will come out to be 2.05 molar. So this is the final molarity of the solution. This is the final molarity of the solution. And guys, there will be one question which will be asked from this particular result as well, right? Sometimes there will be a question given in which molality will be given and you are supposed to calculate molarity. Use this result directly. Sometimes mole fraction will be given and you will be supposed to calculate molality. Use this particular result. So these are some direct results which you can remember from now onwards. Okay, am I clear? And these are the only types of the questions, my dear students, which can be asked from the chapter mole concept. Right? Now we shall be moving into the chapter redox reaction. But before starting the redox reaction, I know you need a break. So I'm giving you the break. This is the lunch break, by the way, right? It is the lunch break till it's 12:33. Lunch break till 1. Okay. So be back on time. Be back on time, and then we shall be starting the chapter redox reactions. Okay. Perfect, guys. Till then, I'll also be back. I'll also have some lunch. But be back on time. Okay. Be back on time. Is it a promise? Because I don't trust you guys. Okay, I would require everyone to be here. Perfect, then only I'll continue the session. Otherwise, you're gone. Hello, see you. See you after the break. What's up, people? Everyone is back? Is everyone back? Call up everyone, call up everyone. Let's start the chapter number 2. Call up everybody quickly. So guys, now we shall be starting one more chapter which is very important, that is the redox reactions. Okay? Are you guys done with your lunch? Are you guys done with your lunch quickly? Let me know in the chats. Are you guys done with your lunch? Okay. All right, people. All right, all right. People are still doing it, huh? They are not giving us lunch. Who is not giving you the lunch? Who is not giving you the lunch? People are still joining in. Let people join, then we shall be starting this chapter. No, I did not have my lunch yet. No. No. Because I don't want to feel sleepy during the session. That is the reason why I did not have the lunch. Yeah? Yes, exactly. Whatever I'm teaching you, this much is enough. This much is enough. People are joining in. Yes, let them join in like 1 minute. Then we shall start. Let them join in. Okay, whatever I discussed till now, is every single thing clear? You can honestly say yes or no. Honestly, I would want honest answers from you. Whatever topics I discussed with you till now, is every single thing clear? Yeah? Perfect. That's great. That's great, people. Perfect then. So let's start the next chapter, that is your redox reaction. Again, I must tell you, this is one of the important chapters, right? Which is there in the physical chemistry. So my dear students, the first topic which we are going to cover here, that is going to be the oxidation state. Now, first of all, how do we define the term oxidation state? This is the first and the basic terminology over here. How do we define the term oxidation state? Oxidation state is defined as the charge present on an atom of an element. It is defined as the charge present on an atom of an element in a given compound. What is meant by that? You'll get the idea in some time. But before that, I'm going to write few terms over here. Oxidation state, it is defined as the charge present on an atom of an element in a given compound. This charge can be real or virtual. This charge can be real or virtual. In case of the ionic compounds, the charge is real. And in case of the covalent compounds, the charge is virtual. The charge is virtual. Now let's get to know one by one what is the meaning of all these things because they are really important. See guys, for example, if I take an ionic compound over here, that is NaCl. This example I have taken many a times. Okay, let's say I've got an ionic compound that is NaCl. My dear students, in case of NaCl, if you see how this NaCl exactly gets formed. In case of NaCl, I would say sodium loses its outermost electron, gets converted into Na positive. Perfect. And that one electron is gained by chlorine. And after gaining this one electron, it gets converted into Cl negative. So what happens basically, Na positive and Cl negative is getting formed here. Na positive, Cl negative gets formed here. And once Na positive, Cl negative gets formed, after that, there will be force of attraction between them. And that force of attraction, you already know, that's what you call as ionic bond. That's what you call as ionic bond. Perfect. Now, my dear students, over here, if you look carefully, sodium loses its one electron completely. Chlorine gains that one electron completely. So can I say over here, during the formation of ionic compound, can I say complete loss and gain of electron is taking place? Absolutely complete loss and gain of electrons is taking place. Now, people, if I ask you, in case of NaCl, what is the charge present on sodium? You will say the charge present on sodium is +1. What is the charge present on chlorine? The charge present on chlorine is -1. The charge present on an atom of an element is what you call as oxidation state. That means, if I ask you, what is the oxidation state of sodium over here? You will say +1. What is the oxidation state of chlorine over here? You will say -1. Perfect. And my dear students, in case of ionic compounds, there is complete loss and gain of electrons happening. And whenever charges arise on the atoms, due to complete loss and gain of electrons, those charges are what you call as a real charge. So this +1 over here, I'm saying oxidation state of sodium is +1. It means that sodium has lost its one electron completely. Chlorine has gained one electron completely. So the charges which you see over here on sodium and chlorine, these are the real charges. These are the real charges. So remember, in case of the ionic compounds, the charges present are real. Now, in case of covalent compounds, we say the charges are virtual. The charges are virtual. For example, let's say I have a covalent compound over here. Perfect. There's a bond between A and B. I'm assuming that electronegativity of B is greater than that of electronegativity of A. This is something which I'm assuming. If B is more electronegative, can I say B has got more tendency to attract the bonded pair towards itself? Due to which B gets delta negative and A gets delta positive. If you ask me, what is the oxidation state of A over here? I'll say it's +1. What is the oxidation state of B over here? It is -1. But over here, if you see, shifting of electron pair is happening. Displacement of electron pair is happening. Displacement of the bonded pair is happening. Due to which charges are coming on these atoms. The charges on these atoms are not due to complete loss and gain of electrons. The charge on these atoms is due to what? Displacement of electron pair. And whenever charges arise on the atoms due to the displacement of electron pair, these charges are not the real charges. These are just the virtual charges. Right? So I would say this +1, -1. These are not the real ones. These are the virtual ones. Right? I hope this is clear. For example, there is a double bond between A and B. And I believe B is, for example, more electronegative than A. So B will attract both the electron pairs towards itself, due to which it carries -2 delta. This carries +2 delta. If I ask you what is the oxidation state of A here, you'll say +2. What is the oxidation state of B? -2. But does that mean A has lost 2 electron completely? No. Does it mean B has gained 2 electron completely? No. It is just the 2 bonded pair of electrons have been shifted towards B. So remember, in case of ionic compounds, due to the complete loss and gain of electrons, the charges on the atoms are real. But in case of covalent compounds, the charges are not real. They are virtual, right? They are not the real charges. These are virtual charges. I believe this is clear to everyone, right? And my dear students, I hope that you already know, on moving from left to right, what happens to electronegativity? Electronegativity increases. On moving from top to the bottom in the periodic table, electronegativity decreases, right? In the periodic table, fluorine is considered to be maximum electronegative, followed by oxygen, followed by nitrogen. This is the electronegativity order which you have to remember. Remember these things. Remember these things, they are very important. Okay? Remember these things, they are very important. Perfect. Now guys, there is one more thing. There is one more thing which I want you guys to remember, then I'll move ahead. This is just the basics which needs to be understood. Okay. For example, between A and B, let's assume there's a coordinate bond. There's a coordinate bond. Okay. If B is more electronegative than A, if B is more electronegative than A, if B is, guys, just give me a second, just give me a second, just a second, just a second. Guys, just give me a second, okay? Okay. So what I was saying is, if there's a coordinate bond between A and B, and I'm assuming B is more electronegative than A, okay? If this is the scenario, then this A is assigned the charge +2, this B is assigned the charge -2, right? But if the scenario is like this, for example, A is more electronegative than B, then the contribution of this bond towards the charges is going to be 0. We do not consider their charges. This is the rule which you need to remember. This is the rule which you need to remember. Okay? Remember this particular point. This is for the coordinate bonds. This is for the coordinate bonds. From less electronegative to more electronegative, yes, you have to consider. From more electronegative to less electronegative, you do not have to consider. Remember these two things as well. Now I'm going to jump into the rules by means of which you can calculate the oxidation states. You can calculate the oxidation states. The first rule says that oxidation state of an element in its standard state. Oxidation state of an element in its standard state is taken as 0. Now, what is the standard state? How do we define the standard state? In short, I would say it is that state of the element, standard state, or you can call it as the most stable state. Most stable state as per thermodynamics, right? Most stable state as per thermodynamics. For example, if I talk about hydrogen, hydrogen in nature exists in the form of H2 gas. Chlorine in nature exists in the form of Cl2 gas. Bromine in nature exists in the form of Br2 liquid, right? Perfect. Iron in nature exists as Fe solid. Copper exists as copper solid. Perfect. So these are what I call as native states, standard states of these elements. And whenever an element is present in its standard state, its oxidation state is taken as 0. Whenever the element is present in its standard state, its oxidation state is taken as 0, right? Its oxidation state is taken as 0. Point number 1. Point number 2. My dear students, whenever you see an element which has got allotropes, if the element has got allotropes, allotrop 1, allotrop 2, right? Allotrop 1, allotrop 2. That allotrop which is thermodynamically more stable, will be considered as the standard state of the element. For example, allotrop 2 is thermodynamically more stable, right? Allotrop 2, let's assume it is thermodynamically more stable. Therefore, allotrop 2 will be considered as the standard state of the element A. For example, if you talk about carbon, carbon has got two main allotropes. One is diamond, one is graphite. One is diamond and one is graphite. Thermodynamically, graphite is considered to be more stable. And if graphite is thermodynamically more stable, that means the standard state of carbon, I'll be writing like this. I'll be writing carbon, graphite. This is the standard state of carbon over here. And whenever the element is present in its standard state, its oxidation state is taken as 0. This is rule number 1. Rule number 2. Rule number 2 is for your group first and group second elements. Group first elements, your alkali metals. Group second elements, your alkaline earth metals, right? My dear students, whenever in any compound you see alkali metal present, its oxidation state directly you will be taking as +1. Whenever you see alkaline earth metal present, its oxidation state directly you will be taking as +2. Okay, oxidation state of your group first and group second elements, they are taken as +1 and +2 respectively. Remember it directly. Number 3 is going to be for hydrogen. My dear students, whenever you see hydrogen attached to an element, whenever you see hydrogen attached to an element which is more electronegative than hydrogen, whenever hydrogen is attached to an element which is more electronegative than hydrogen, at that point of time, the oxidation state of hydrogen is taken as +1. Whenever you see hydrogen attached to less electronegative element than itself, right, the oxidation state of hydrogen will be taken as -1. And whenever hydrogen will be present in its standard state, its oxidation state will be taken as 0. These are the three things which you have to remember about hydrogen. These are the three things which you need to remember about hydrogen. That's all. That's all. Okay? These are the three things which you need to remember about hydrogen. Now, there are few things which you need to remember about oxygen as well. There are few things which you need to remember about oxygen as well. There are few things which you need to remember about oxygen as well. The first point about oxygen. Whenever you see oxygen attached to the less electronegative element than itself, whenever you see oxygen attached to less electronegative element than itself, generally oxidation state of oxygen at that point of time is taken as -2. For example, you have got MgO, oxygen attached to less electronegative element than itself. Its oxidation state is -2. For example, you have got water, oxygen attached to less electronegative element than itself. Its oxidation state again is -2. Perfect. So whenever you see oxygen attached to less electronegative element than itself, generally its oxidation state will be taken as -2. Now, my dear students, there are few special compounds which oxygen forms. One is what you call as peroxides. One is what you call as superoxides. And one is what you call as oxyfluorides. These are some special compounds which oxygen forms. Whenever you see oxygen in the form of O2 dinegative, whenever in a compound oxygen will be present in the form of O2 dinegative, understand that is a peroxide. Right? Whenever you see oxygen present in the form of O2 negative, remember that is a superoxide. For example, you know about your hydrogen peroxide H2O2. Do you know its structure? This is O single bond O. This, for example, H. This is H. This is the structure of your H2O2. Now, you tell me one thing. If you look at this particular bond between oxygen and hydrogen, which one is more electronegative? Oxygen. So this bonded pair will be shifted towards oxygen. So oxygen carries -1. This carries +1. What about this particular bond? This oxygen will carry -1. This will carry +1. What about this particular bond? On both the sides, you have got oxygen. So electron pair is exactly at the center. So what is the charge present on one oxygen atom? -1. The charge present on one atom of an element is what you call as oxidation state. So I would say oxidation state of oxygen here is -1. So remember, whenever oxygen forms the peroxide, right? Oxidation state of oxygen is taken as -1. Oxidation state is basically charge present on one atom, right? No doubt, you're writing O2 dinegative here. But I have to check how much charge is present on one atom of oxygen. And charge present on one atom of oxygen is -1. So that is the oxidation state of oxygen in case of peroxide, right? In case of peroxide. And my dear students, this particular linkage, a single bonded linkage between two oxygen atoms, that's what you call as peroxide linkage. This is what you call as peroxide linkage. Perfect. Now, in case of superoxides, you will find oxygen in the form of O2 negative. Now, if I ask you, the charge present on two oxygen atoms here is -1. Therefore, the charge present on one oxygen atom will be -1/2. And the charge present on one atom of an element is what you call as oxidation state. So, in case of superoxides, the oxidation state is -1/2. Right? Perfect. I hope this is clear. Now, in case of oxyfluorides, what you will find oxygen showing positive oxidation states. In case of oxyfluorides, you will find oxygen showing positive oxidation states. For example, I'm going to take two compounds over here. One is OF2 and one is O2F2. These are the two compounds which I've taken, OF2 and O2F2. First of all, if you look at the OF2 structure, this is O, this is F, and this is F, right? O2F2, this is the structure of your O2F2. Perfect. Look at these structures carefully. Guys. First of all, if you look at this particular single bond between oxygen and fluorine, which one is more electronegative? Fluorine is more electronegative. So bond pair is shifted towards fluorine, due to which this will have -1, this will have +1, right? Similarly, look at this particular bond between fluorine and oxygen. Which one is more electronegative? Fluorine. So -1, +1. So what is the total charge present on oxygen here? +2. So oxidation state of oxygen here is +2. Similarly, O2F2. Look at this particular bond between oxygen and fluorine. Which one is more electronegative? Fluorine. So -1, +1. Due to this particular bond, -1, +1. Due to this bond, nothing is going to happen. Because on both the sides, you've got oxygen. So charge present on one oxygen atom here is +1. And the charge present on one atom of an element is something which you call as oxidation state. So I would say oxidation state of oxygen here is +1. The charge present on one oxygen atom is +1, which is what you call as oxidation state. Yes? I believe it's clear. I believe it's clear. Someone is saying majority from Kashmir. Is that? Guys, can you let me know in the chats, where are you guys from? Can you write your states? I want to see from which place majority of the students are watching me right now. See, I'm live from Kashmir. Where are you guys from? Quickly, write your states in the chats. Write your states in the chats. Let me see the majority. Majority is not from Kashmir, yes? Majority is from Tamil Nadu, Karnataka, okay. From Kashmir also few people are watching. Nice. What about the rest? Oh, someone is watching from Nepal. Andhra people are watching, yes. Great. All right. So basically students are watching from all over the country, right? Okay, so I hope you got to know about oxygen, and these were few things which you have to remember about oxygen, yeah? Okay. Now guys, one more thing which I would want to discuss here, that is about halogens. About halogens. Okay, you know halogens, they are your group 17 elements. My dear students, halogen you represent with X, right? Whenever you see halogen attached to a less electronegative element whenever halogen is attached to less electronegative element than itself, the oxidation state of halogen will be taken as -1. The oxidation state of halogen will be taken as -1. For example, you have got HCl. Perfect. You have got HF. Perfect. You have got HF. Right? You have got HF. Yeah? So over here, this is halogen, attached to less electronegative element than itself. So oxidation state directly here is -1. Now the point is, what about halogens? Do they show positive oxidation state anytime? Do they show positive oxidation state? My dear students, there are few compounds wherein halogens, they show positive oxidation state. For example, you have got interhalogens. For example, let's say I'm taking one compound, ClF3, right? It's an interhalogen. Perfect. You have got BrF5, interhalogen. You have got IF7, interhalogen compound. If I ask you what about the oxidation state of these underlined halogens, what you'll say? You'll say oxidation state here will be +3 because it's attached to 3 fluorine atoms. Here is going to be +5. Here is going to be +7. So basically halogens can show oxidation state positive as well. They can show positive oxidation states as well. Similarly, for example, you know, there's a compound Cl2O. Chlorine, here is the halogen. If you look at its structure, this is O, for example, this is Cl and this is Cl. Correct? This is OCl2. If you look at this particular bond between oxygen and chlorine, which one is more electronegative? Oxygen. So due to this bond, -1, +1. Due to this bond, -1, +1. So again, you can see the charge present on one chlorine is +1. So I'll say halogen over here is showing +1 oxidation state. So basically my point is halogens can show positive oxidation state as well. Right? Exactly. It's all about electronegativity. I believe this is clear. I believe this is clear. It's all about the electronegativity. Okay? Now, people, now understand. There is one important rule which you need to know. One important rule which you need to know. What is that? The sum of oxidation states, the sum of oxidation states of all the elements, the sum of oxidation states of all the elements in a compound is equal to the net charge present on the compound. Is equal to the net charge present. This is something which every one of you would have heard. I'm pretty much sure about that, right? So people, the sum of oxidation states of all the elements present in a compound, it's always equal to what? It is always equal to the net charge present on the compound. Just give me a second. Perfect. See guys. See what is the meaning of this particular statement. I have taken over here two compounds, right? And I'm underlining certain elements over here. I'm asking you to calculate their oxidation states. How exactly you are going to do it? How exactly? It's simple. Let the oxidation state of chromium be X. We have got 2 chromium atoms. So multiplied by 2 plus oxygen attached to less electronegative than itself. So oxygen generally shows -2 oxygen state. There are 7 oxygen atoms is equal to net charge is -2. When you solve X, X will come out to be +6. So +6 is the oxidation state of chromium here. That means +6 is the charge present on 1 chromium atom. As simple as that, right? Sulfur. Assume its oxidation state as X, so which will be 2X. Oxygen will show -2 oxygen state. There are 3 oxygen atoms. Net charge is -2. So the value of X will be here, +2. So +2 is the oxidation state of sulfur here. Correct? Let the oxidation state of nitrogen be X. Hydrogen shows +1. There are 4 hydrogen atoms. Net charge is +1. The value of X when you solve, it will come out to be -3. Simple. ClO4 negative, right? Similarly, when you solve it, this is X plus oxygen -2. There are 4 oxygen atoms. Net charge -1. It is +7, right? This is +6. Perfect. So this is how you calculate oxidation states of different elements. For example, you have got Fe2O3. Fe2O3. Here the oxidation state of iron, when you calculate, it will be +3. Here it will be +8 divided by 3. +8 divided by 3. And whenever you see oxidation state coming out to be fractional, whenever you see oxidation state coming out to be fractional, remember that is the average oxidation state. Remember that is the average oxidation state, right? That is the average oxidation state. For example, Fe3O4. Fe3O4, it actually is a mixed oxide. It is a mixed oxide. It is a mixed oxide and it exists in the form of FeO.Fe2O3. It exists in this format. It exists in this format. And if you look carefully, this iron, this will be X -2 is equal to 0. So this iron is in +2 and this iron is in +3. So if I calculate average oxidation state of iron over here, see, the first iron is in +2. This iron is in +3. This iron is in +3. Perfect. And these are 2 iron atoms. In total, there are 2 + 1, 3 iron atoms. When you calculate it, this value will come out to be +8 by 3. So this +8 by 3 is basically the average oxidation state of iron here in case of Fe3O4. Similarly, I believe you would have studied the coordination compounds, or if not, there will be a marathon for that. You know, this CN, it is a negatively charged ligand. I hope you remember. It's a negatively charged ligand. It carries charge -1. So if this is X, right, CN will carry -1. There are 6 CN. Net charge is -3. So X value, when you solve, it will come out to be +3. This carbonyl, it is a neutral ligand. Neutral ligand. So 0. Perfect. Similarly, you can calculate here also. Perfect. Now, look at these two compounds. NH4NO2. NH4NO2. Let me tell you this NH4NO2, it exists in the form of NH4 positive and NO2 negative. And the oxidation state of these 2 nitrogen atoms here will be different. Check it out. Let's say the oxidation state of this nitrogen is X. Hydrogen will show +1. There are 4 hydrogen atoms. The charge here is +1. So X value, when you solve it, it will be -3. So charge present on this nitrogen is -3, right? Look at this particular nitrogen. This is X. Oxygen will show -2. There are 2 oxygen atoms. Net charge is -1. X will come out be what? It will come out be +3. So the charge present on this nitrogen is +3. If I ask you to calculate average oxidation state of nitrogen, on the first one it is -3. On the second one it's +3. Total nitrogen atoms are 2, right? Average oxidation state of nitrogen here comes out be 0. It comes out be 0, right? Now, talk about Ki3. Talk about Ki3. See, potassium, it belongs to what? Potassium, it belongs to what? Potassium belongs to group first elements. And group first elements, what do they show? They show +1 oxidation state. Now, let's assume the oxidation state of iodine here is X. Perfect. So it is +1 plus 3X. Net charge is 0. So the value of X comes out being -1/3. So -1/3 is the oxidation state of iodine over here. I hope I'm clear. I hope I'm clear. I hope I'm clear. Now, guys, there is one very strong point which you have to remember and take a note of it. Take a note of it. Let me tell you, the maximum oxidation state of an element, the maximum oxidation state of an element can never be, the maximum oxidation state of an element can never be greater than +7. Can never be greater than +7 except osmium in OSO4, where osmium shows +8 oxidation state. The maximum oxidation state of an element, it can never be greater than +7. There is one exception, that is osmium. Osmium in osmium tetroxide, it shows the oxidation state of +8. Okay, it shows the oxidation state of +8. Now, guys, can you tell me one thing? I'm writing a compound over here, CrO5. Can you let me know the oxidation state of chromium here? Quickly. Can you let me know the oxidation state of chromium in CrO5? Quick. The rules which we have discussed, as per those rules. The rules which we have discussed, as per those rules. This has to be X. This has to be -2. Multiplied by 5, net charge is 0. So the value of X has to be +10 as per the rules we discussed. But can the oxidation state of element be greater than +7? No. That means we have done some mistake. It is incorrect. Whenever, with the help of formula, oxidation state of an element comes out to be greater than +7. Whenever, with the help of formula, oxidation state of an element comes out to be greater than +7, at that point of time, you have to consult the structure of that particular compound. Right? So there are some compounds, my dear students, there are some 11 to 12 compounds whose structure you need to remember on priority. Now, what are those compounds? What are those structures? Let's have a look. People. Let's have a look. The first compound which I have, that is CrO5. CrO5. Perfect. Let me tell you, the CrO5, we say it has got a butterfly-like structure, which is not true though, right? Butterfly-like structure. Let me tell you, it is deep blue in color as well. Now the point is, what is its structure? This is chromium, double bond O, oxygen, single bond, and here oxygen, single bond. This is the actual structure of your CrO5. Now, look at this particular double bond between chromium and oxygen. Oxygen is more like to negative. So due to double bond, it will be -2. This chromium will be +2. Due to this single bond, this oxygen is -1, this is +1. Due to this single bond, this -1, this +1. Due to this single bond, -1, +1. Due to this single bond, -1 and +1. So if I ask you, what is the total charge present on chromium here? Total charge present on chromium, it will be how much? +2, +3, +4, +5, +6. So +6 is the actual oxidation state of chromium in case of CrO5. Now, people, if I ask you how many peroxide linkages do we have? How many peroxide linkage? Peroxide linkage means oxygen, single bond, oxygen. There's the oxygen, single bond, oxygen. This is oxygen, single bond, oxygen. So in case of CrO5, the number of peroxide linkage is 1. Okay? Right? At the same time, if they ask you, how many oxygen atoms are there with -1 oxidation state? Right? What you have to do? Number of peroxide linkage multiplied by 2. Number of peroxide linkage multiplied by 2. The value comes out to be 2. This was your first structure, that was CrO5. Right? That was your CrO5. Let's have a look on the second structure. CrO6. CrO6, right? This has been asked in your NEET as well. CrO6, right? This is Cr, oxygen, oxygen, peroxide, oxygen, oxygen, peroxide, oxygen, oxygen, peroxide. Now you tell me quickly what is the oxidation state of this chromium? It is going to be +6 because 6 single bonds with oxygen atoms, right? Now if I ask you how many peroxide linkages are there are 3 peroxide linkages. How many oxygen atoms are there with -1 oxidation state? 3 2s are 6. Done and dusted, right? There is something which you call as Carr's acid. H2SO5. You call it as the Carr's acid. Perfect. What about the structure of this Carr's acid? You need to remember this as well. This is S double bond O, for example, right? Double bond O, oxygen attached with hydrogen, oxygen, oxygen, and hydrogen. H2, S, and 5 oxygen. 1, 2, 3, 4, 5. Yes. Perfect. After having a look at this particular structure, can you let me know the oxidation state of sulfur? See, double bond, single bond, single bond. So this sulfur will have +6 oxidation state because +2 due to this double bond, +2 due to this double bond, +1 due to this single bond, +1 due to this single bond. So +6, right? How many peroxide linkages do we have? Peroxide linkages, this is a peroxide linkage 1. If I ask you how many oxygen atoms will be there with -1 oxidation state, peroxide linkage multiplied by 2. Done? Now you have got the fourth one. Fourth one is going to be your, this was your H2SO5. Okay. Now we have got H2S2O7. You call it as oleum. You call it as oleum. H2S2O7. Perfect. H2S2O7. So this S, this is O, this is S. Double bond O, double bond O. Double bond O, double bond O. Oxygen attached with hydrogen, and this oxygen attached with hydrogen. So this is the structure of your H2S2O7. Check, have we used all the 7 oxygen? 1, 2, 3, 1, 2, 3. Yes. Right? This is the structure of your H2S2O7. Now, if I ask you what is the oxidation state of this sulfur and this sulfur, check it out. There's a double bond. So +2 from this double bond, +2 from this double bond, +1 from this single bond, +1 from this single bond. So +6. Similarly, this will be +6, right? +6, +6. Now, if I ask you the average oxidation state of sulfur over here, the first atom is +6, second is +6, total number of sulfur 2. So +6 is also the average oxidation state of sulfur here in case of oleum. Believe it's clear? Right? I believe it's clear. Is it clear, people? Quickly. Perfect. Sir, butterfly structure, peroxide linkage 2. What did I write? Oh, guys, there's a mistake which I've done over here. Oh, thank you so much. There are 2 peroxide linkages, right? So peroxide linkages are 2. So how many oxygen atoms are there with -1 oxidation state? 2 2s are 4, right? I hope you would have corrected it automatically. I said the same, but I wrote different. Yeah? Right? This is auto-corrected. Perfect. This was your oleum, H2S2O7. Now, moving ahead. Have you heard about Marshall's acid? H2S2O8. This is your H2S2O8. If you look at this, the oxidation state of this particular sulfur will come out to be +6. The oxidation state of this particular sulfur will come out to be +6. Now, there's a peroxide linkage here. So number of peroxide linkages is 1, and number of oxygen atoms with -1 oxidation state is 2. Correct? It is just, if you remember the structure, you are done. Right? The sixth one, this has been frequently asked in many examinations. Na2S4O6. Many examinations. In JEE, 2 times the same question has been asked. Na2S4O6. Right? And remember its structure. There's the structure. This is the structure of your Na2S4O6. Now, if you want to calculate the oxidation states of different sulfur atoms, this sulfur is having +2, +4, +5. So +5, this will be 0, this will be 0, and this will be plus 5. So the correct set of oxidation state here is plus 5, 0, 0, plus 5. Now, if you ask me, the average oxidation state of sulfur here, it will be plus 5, second one carries 0, third one carries 0, fourth one plus 5, total sulfur 4, the value comes out to be plus 2.5. So plus 2.5 is the average oxidation state of sulfur in case of Na2S4O6. Okay, this was your sixth structure. Now, the seventh one, your K3CrO8. K3CrO8. Remember its structure as well. So this is Cr, this is oxygen, oxygen, single bond, oxygen, oxygen, oxygen. Then you have got these peroxide linkages, and you have got potassium, potassium, potassium. This is K3Cr 1, 2, 3, 4, 5, 6, 7, 8. Yes, perfect. Now guys, if I ask you about all these things, what is the oxidation state of chromium here? You will say plus 5. If I ask you how many peroxide linkages do we have? First peroxide, second peroxide, third one, and fourth one. So 4 peroxide linkages. How many oxygen atoms with oxygen state -1? It is 8. Done. This was your K3CrO8. This was the 7th one. Now, 8th one. 8th structure. 8th structure is your C3O2. 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 This is your C3O2. If you calculate the oxidation states, this carbon is having +2. This carbon, 0, because on both the sides you have got carbon. This is +2. If you ask me average oxidation state of carbon here, the first one +2, second one 0, third one +2, total carbon 3. The value is +4/3. The value is +4/3. Right? The value is +4/3. This was your C3O2. Now, the 9th one, that is Br3O8. Br3O8. You need to remember its structure as well. This is Br, this is Br, this is Br, right? Double bond, double bond, double bond, double bond, double bond, double bond. Everywhere you have got double bonds like this. Okay? And if you remember the structure, now you can easily calculate the oxidation states of different elements. Easily you can do that. Now, if you talk about this particular bromine, +2, +2, +2, that means +6. This one, +2, +2, +4, +2, +2, +2. This is +6. So if you ask me the average oxidation state of bromine over here, it will be +6, followed by +4, followed by +6, total 3 bromine, 6, 6, 12, 4, 12, 4, 16. So +16/3 is the average oxidation state of bromine here. Right? Perfect. This was your Br3O8. Br3O8. Now, the 10th one, bleaching powder, CaOCl2. CaOCl2. This is Ca, this is OCl, and this is Cl directly. Okay. Now, if you look at the oxidation states of different elements here, calcium and chlorine. Chlorine is more electronegative, so -1, +1. Oxygen is more electronegative, -1, +1. Oxygen is more electronegative, -1, +1. Right? So oxidation state of this calcium is +2, this oxygen is -2, this chlorine is +1, this chlorine is -1. If you ask me the average oxidation state of chlorine here, one is having +1, the second one is having -1, 2 chlorine atoms in total. So the average oxidation state of chlorine here comes out to be 0. Right? Perfect, guys? Right? This was the 10th one. Now, few more, 3, 4 structures. 11th. BASCN whole twice. You will find, this particular compound, why am I giving you? Because after this, we have to discuss n factor calculation. In n factor calculation, a question is asked from this as well. BASCN whole twice. You need to know its structure as well. SC triple bond, right? SC triple bond. Now, people, understand. Understand. First of all, there is a triple bond between carbon and nitrogen. Which one is more electronegative? Nitrogen. So -3 and +3. Single bond between carbon and sulfur. Sulfur is more electronegative, -1, +1. Right? Because you know sulfur is group 16, carbon is group 14. On moving from left to right, electronegativity increases. Now, barium and sulfur. Sulfur is more electronegative, -1, +1. Due to this bond, -1, +1. Perfect. Due to this bond, -1, +1. Due to this triple bond, -3, +3. Can you calculate the oxidation states of all these elements here? Can you calculate the oxidation states of all these elements here? Right? See guys, this nitrogen is having -3 oxidation state. This carbon is having +4 oxidation state. -2, +2, -2, +4, and -3. Okay? I believe all the things are clear. I believe all the things are clear. Now, H3PO2, H3PO3, H3PO4 and H3PO5. You need to remember their structures as well. You need to remember their structures as well. Now guys, let's have a look what their structures are. First of all, everywhere you keep P double bond O. Keep P double bond O everywhere. Keep P double bond O everywhere. Now, one oxygen directly attached with hydrogen. One oxygen directly attached with hydrogen, right? So we have got H3PO4. So this is your, what did I do here? Just a second, guys. I had to write H3PO2. I made for H3PO4. So this is H3PO4 here. This is H3, H3P, 1, 2, 3, 4. Okay. Here I'll make H3PO2. Here I'll make H3PO2. P double bond O, oxygen attached with hydrogen. Wait. Guys, how do we make the structure for H3PO2? I forgot. Chalo. Let's make for H3PO3. Oxygen attached with hydrogen. Okay, there's a peroxide linkage here. No, peroxide linkage is here, H3PO5. Oxygen attached with hydrogen. Oxygen attached with hydrogen. This oxygen, oxygen, and hydrogen. This is your H3P, 1, 2, 3, 4, 5. H3PO5. Okay, let's talk about these two now. H3PO3. H3PO3. Okay, this is P double bond O. Perfect. This oxygen attached with hydrogen. We have 3 hydrogen atoms, right? This oxygen attached with hydrogen, and this will be 1 hydrogen directly here. So this will be H3P1, 2, 3. Perfect. H3PO2. This is P double bond O. This is oxygen attached with hydrogen. Perfect. 2 oxygen atoms. So this hydrogen and this hydrogen. So these are the structures of these H3PO2, H3PO3, H3PO4, right? Yeah, exactly. Brain is not braining anymore. Done? So guys, these are the structures which you need to remember. These are the structures which you need to remember. These are the structures which you need to remember. I hope I am perfectly clear to everyone. Yeah, is it all clear till now? Let me know once in the chats. I would want some fire emojis, guys. Do not sleep, please. Otherwise, I'll sleep. I want from everyone. Is it like clear, properly clear? Honestly, you can say. Whatever structures I gave you, just remember these structures. Whatever structures I gave you, just remember these structures. That's all. That's all. Perfect. If the structures are clear, now let's move ahead. Oh, by the way, structures were already made here. Why did I make them again? Structures were already on the slides. Perfect. Now guys, if I ask you, how do you define the term oxidation? There are many ways by means of which you can define the term oxidation reduction, right? Perfect. There are many ways by means of which you can define the term oxidation and reduction. Oxidation involves loss of electrons. Number 1. Oxidation involves loss of electrons. Oxidation involves removal of hydrogen, something which you have seen in class 8th, 9th. Addition of oxygen is also called as oxidation. Addition of more electronegative element is also called as oxidation, right? But I would just want you guys to remember this one. Addition, loss of electrons. Just remember this one, loss of electrons. Gain of electrons is what you call as a reduction. Addition of hydrogen is called as a reduction. Removal of oxygen is called as a reduction. Removal of more electronegative element is called as a reduction. For example, try to understand carefully. If you look at the first one, magnesium is losing 2 electrons. Magnesium is losing 2 electrons, getting converted into Mg positive. So this process involves loss of electrons. I would say magnesium is undergoing oxidation here. Magnesium is undergoing oxidation here, right? Over here, removal of hydrogen is happening. Removal from water, you are removing hydrogen. Removal of hydrogen is happening. Removal of hydrogen is also what you call as oxidation. Over here, addition of oxygen is happening. Addition of oxygen is also what you call as oxidation. And in this particular case, addition of more electronegative element is happening, right? This is also what you call as oxidation. If you see, there is one thing common in everyone. All these are oxidation processes. All these processes over here, they are oxidation processes. But if you perfectly analyze, magnesium, its oxidation state here is 0. Here the oxidation state is +2. So the oxidation state of magnesium is increasing here. Correct? Oxygen, its oxidation state here is -2. Here it is 0. So -2 to 0. Again, the oxidation state is increasing. Perfect. Calcium, oxidation state 0. Calcium oxidation state +2. Again, the oxidation state is increasing. Carbon, its oxidation state 0. Here the oxidation state is +4. Oxidation state again increasing. All these processes were oxidation processes, right? And there is one thing common. Oxidation state of an element is increasing. So in short, forget everything and remember one thing. Increase in the oxidation state is what you call as oxidation. Whenever from now onwards, if you see oxidation state of an element increasing, whenever from now onwards, if you see oxidation state of an element increasing, remember that particular element is undergoing oxidation. In the similar way, decrease in the oxidation state is what you call as reduction. So that particular element which undergoes decrease in the oxidation state, we say that species undergoes reduction. And the one which undergoes oxidation is what you call as reducing agent. The one which undergoes reduction is what you call as oxidizing agent. You should know it. The one which undergoes oxidation. The one which undergoes oxidation is what you call as a reducing agent. The one which undergoes reduction, that's what you call as oxidizing agent. Right? Now, let's try to analyze all these things properly. For example, I'm giving you a reaction. I'm asking you to identify your oxidizing agent and reducing agent. You should be able to do it. See guys, first of all, I would want you guys to calculate the oxidation state of every species over here. So you calculate the oxidation state of every species, number 1. Now check, is the oxidation state of zinc increasing or decreasing? 0 to +2. Increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation. So I would say zinc is undergoing oxidation. If zinc is undergoing oxidation, definitely it will be losing electrons. Right? And the one which is undergoing oxidation, that's what you call as a reducing agent. So zinc here acts as a reducing agent. Right? Similarly, copper, +2 to 0, decrease in the oxidation state. Decrease in the oxidation state is what you call as a reduction. And reduction involves gain of electrons. So your copper dipositive here will be gaining electrons, right? The one which undergoes reduction, that's what you will be calling as oxidizing agent. Simple. Yeah? Is it simple, people? For example, I'm giving you one more. Calculate the oxidation state of everything over here. Iron in +2 oxygen state. Manganese +7 oxidation state. Iron +3 oxygen state. Manganese +2 oxygen state, right? You calculate the oxidation states. You calculated the oxidation states. Now people try to understand +2 to +3, increase. +7 to +2, decrease. Increase in the oxidation state is what you call as oxidation. So I would say this FeO is undergoing oxidation. The one which undergoes oxidation, that is the reducing agent. Plus 7 to plus 2, decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. So here I can say MnO4 negative is undergoing reduction. The one which undergoes reduction is termed as the oxidizing agent. So I believe from now onwards, you can easily identify which species is your oxidizing agent and which species is your reducing agent. Yeah? Am I clear, people? Am I clear? I hope from now onwards you can easily define your oxidizing agent and reducing agent. Now comes the most important part of the chapter. 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 What is that? Equivalent mass. How do we exactly define the term equivalent mass? How do we do it? See guys, equivalent mass, it is defined as that mass of the substance in grams, that mass of the substance in grams, which can combine or displace, either which can combine or displace either 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver or 80 grams of bromine or 80 grams of bromine. What does it mean? Try to understand, my dear students. For example, I'm writing a reaction over here. N2 plus 3 times H2. It gives NH3. It gives 2 times NH3. This is the reaction which I wrote over here. If you look carefully, my dear students, your nitrogen is being combined. Nitrogen is combining with what? Nitrogen is combined with hydrogen. It's combining with hydrogen. In this particular case, nitrogen is combining with hydrogen. Let's assume that I want to calculate the equivalent weight of nitrogen. How do we define the term equivalent weight? It is that mass of the substance. Which can combine or displace either 1 gram of hydrogen or this or this or this. And in this particular case, your nitrogen is combining with hydrogen. So no doubt, I have to calculate equivalent mass of nitrogen. But here in this particular case, I'll be calculating equivalent mass of nitrogen by taking hydrogen into reference. So I will exactly check how many grams of nitrogen are combined with 1 gram of hydrogen. That's something which I need to check. How many grams of nitrogen are combined with 1 gram of hydrogen. How exactly I'm going to do that? Understand. What is the mass of 3 moles of hydrogen? 3 moles of hydrogen means 6 grams. So can I say 6 grams of hydrogen? Can I say 6, as per stoichiometry, 6 grams of hydrogen combines with 28 grams of nitrogen here? From the stoichiometry I got to know. 6 grams of hydrogen combines with 28 grams of nitrogen. Therefore, I can say 1 gram of hydrogen combines with 1 gram of hydrogen combines with 28 divided by 6, which comes out to be 14 divided by 3 grams of nitrogen. If you look carefully, can I say this is the mass of nitrogen? Can I say this is the mass of nitrogen that has combined with 1 gram of hydrogen? That mass of substance which combines with 1 gram of hydrogen, that's what you call as equivalent mass. So this is something which I'll be calling as equivalent mass of your nitrogen. So this is the mass of nitrogen which has combined with 1 gram of hydrogen. That's what I'll be calling as equivalent mass of nitrogen. I hope I'm clear. I hope I'm clear. Yes? Perfect. Let me give you one more example so that it makes sense to you. I'm writing a reaction, magnesium plus O2. It gives MgO. If I balance it, this has to be 2 times, this has to be 2 times. Now it's a balanced chemical equation. My dear students, let's assume that I need to calculate the equivalent mass of magnesium. Equivalent mass of magnesium. But over here, if you look carefully, magnesium is combining with O2. Magnesium is combining with oxygen. So no doubt, I will be calculating equivalent mass of magnesium, but with oxygen taking into reference. With oxygen taking into reference. With oxygen taking into reference. Okay, now how exactly? Understand. What is the mass of 1 mole of oxygen? 32 grams? 32 grams. What is the mass of 2 moles of magnesium? 1 mole of magnesium means 24 grams, so it's 48 grams. As per stoichiometry, I got to know 32 grams of oxygen combines with 48 grams of magnesium. So 1 gram of oxygen combines with 48 divided by 32 grams of magnesium. Therefore, 8 grams of oxygen combines with these many grams of magnesium. Right? 8184. The value comes out to be 12 grams. So can you quickly check what did I calculate? I calculated basically that mass of magnesium. I basically calculated that mass of magnesium which is combining with 8 grams of oxygen, and that mass of substance which either combines with 1 gram of hydrogen or 8 grams of oxygen. That's something which you call as equivalent mass. So this is what you will be calling as equivalent mass of magnesium. This is the general definition. This is how you calculate the equivalent mass of different species as per their definition. As per their definition. Right? As per their definition. Now, there is one direct formula also by means of which we can calculate equivalent mass. And what is that direct formula? Remember that directly. Right? Remember, equivalent mass of the substance is always equal to. Equivalent mass of the substance is always equal to molar mass of the substance divided by n factor of the same substance. N factor is also called as valency factor. Molar mass of the substance divided by n factor. Now the molar mass of every substance you already know or you can calculate. But the point is, how do we calculate n factor? How do we calculate n factor? Now comes the actual topic, that is the n factor calculation. Okay. Now let's have a look on the n factor calculations. N factor calculation. N factor calculations. First of all, I'm starting with n factor of an element. N factor of an element. How do we calculate n factor of an element? It's always equal to the valency of an element. N factor of an element is what? N factor of an element is basically equal to what? The valency of an element. For example, take certain elements. Let's say I'm taking nitrogen. Let's say I'm taking magnesium. Right? Perfect. Let's say I'm taking sodium. These are few elements which I took. Now people, if I ask you, what is the valency of nitrogen? I'm asking you about the valency of nitrogen. What is the valency of nitrogen? You tell me quickly. What is the valency of nitrogen? It's 3. What is the valency of magnesium? It's 2. What is the valency of sodium? It's 1. Whatever is the valency of an element, that's something which you call as n factor of an element. So this is the n factor of your nitrogen. This is the n factor of your magnesium. This is the n factor of your sodium. Now equivalent weights of all these species. So equivalent weight of nitrogen will be equal to molar mass of nitrogen divided by n factor. Equivalent mass of magnesium is equal to molar mass of magnesium divided by n factor. Equivalent mass of sodium is equal to molar mass of sodium divided by n factor. So this is how you calculate n factor of an element. I mean, this is how you calculate equivalent mass of an element. Molar mass by n factor. N factor of an element is nothing but someone is saying this part is deleted. Who said this part is deleted? Who said so? Just make me talk to him or her, whosoever it is. That's why you should not watch random videos, right? Just stick to only one channel. Someone is saying for nitrogen valency is 5. Wow. Those are valence electrons. Valence electrons are 5. 8 minus 5 is 3. Valency, something which you study in class 8th. Okay. Someone is asking certain questions. Why can't we take 16 grams of oxygen for finding equivalent mass? I'll ask you one more question. Why can't we take 10 grams of hydrogen to calculate equivalent mass? These are all definitions which you need to follow, right? Okay. I have not given this. Somebody gave it like hundreds of years before. That's what I'm teaching. Yeah. So remember it. Remember it. Sure. So the first part is done. N factor of an element is basically what? N factor of an element is the valency of the element. Once we get the valency, that's something which you call as the N factor, and you're done. This is point number 1. Point number 2. Point number 2. That is N factor of a salt. N factor of a salt. N factor of the salt is equal to LCM of LCM of charge on cation, comma the charge on anion. LCM of charge on cation, comma charge on anion. I hope you remember how to calculate LCM. I wish and hope at the same time. For example, try to understand, people. Let's say I'm taking certain salts. First one is your NaCl, which you all must be knowing, right? Let's say I'm taking MgCl2, right? Let's say I'm taking Al2SO4 whole thrice. These are certain salts which I've taken. Yeah. Now, first of all, this is one. This one goes a charge here. This one will be the charge here. That crisscross thing which you studied earlier. This 2 is the charge here. This 1 is the charge here. This 3 is the charge here. This 2 is the charge here. So you got the charges on LCM, charges on cation and anion. Since you got the charges on cation and anion, now you have to take the LCM. LCM of 1 and 1 is 1. LCM of 2 and 1 is 2. LCM of 3 and 2 is 6. So LCM of charge on cation and anion, that gives you the N factor, right? So this is the N factor of NaCl. This is the N factor of MgCl2. This is the N factor of Al2SO4 whole thrice, right? Since you calculated the N factors, you can easily calculate their equivalent weights. Molar mass of NaCl divided by N factor. Molar mass of this divided by N factor. Molar mass of this divided by N factor. That gives you the equivalent mass of these salts. It gives you the equivalent weight of these salts. This was second point. The third point. This is important. N factor of acids. N factor of acids. How do we calculate N factor of acids? N factor of acid is nothing but basicity of the acid. N factor of an acid is nothing but basicity of the acid. Now, how do we define the term basicity of an acid? There are many ways by means of which you can define basicity of the acid. Number one, number of H positives donated. Number of H positives which an acid donates. Number two, number of OH negatives which an acid accepts. Or number three, the number of lone pairs which an acid donates. Perfect. For example, let me take certain acids, like simple acids. HCl, H2SO4, H3PO4. These are some simple acids which you already know. When you introduce this HCl into water, or when you introduce this H2SO4 into water, when you introduce this H3PO4 into water, tell me how many H positives it's going to donate. It will give away 1 H positive. This will give away 2 H positives. This will give away 3 H positives. And you know, number of H positives an acid donates. Number of H positives an acid donates, that defines its N factor. So N factor of HCl here is 1. N factor of H2SO4 here is 2. N factor of H3PO4 here is 3. If you got the N factors of these acids, you can easily calculate their equivalent weights. Right? How? Molar mass of HCl divided by N factor. Molar mass of this divided by N factor. Molar mass of this divided by N factor. Correct? Right? Now guys, here I'm going to write one statement. Be careful with that. I'm writing an acid. An acid donates only that H positive. An acid donates only that H positive which is connected. An acid donates only that H positive which is connected to more electronegative element. To more electronegative element. Like fluorine, oxygen, etc. Right? Why am I writing this particular statement? There's a point for that. You'll have a point over here. But dear students, for example, I'm writing H3PO2. Here I'm writing H3PO3. Here I'm writing H3PO4. And here I'm writing H3PO5. H3PO5. If I ask you what is the N factor of this, what is the N factor of all these 4 species? What do you think? All these are acids. What do you think? What do you think? What is the N factor of all these species which I took? Quick. It looks like this will give 3 H positives, this will give 3 H positives, this will give 3. So N factor of all of them should be 3, right? N factor of all of them should be 3. But I told you an acid donates only that H positive which is connected to more electronegative element like fluorine, oxygen, right? In this particular case, there is only one. If you look at its structure, which I gave you a few minutes back, there is only one hydrogen which is attached to more electronegative element like oxygen. So it will donate only that hydrogen, right? Over here in this particular structure, 2 hydrogens are attached with oxygen. So it will donate those 2 hydrogens. This will donate 3 hydrogens. This will also donate 3 hydrogens. So their N factors are respectively 1, 2, 3, and 3. And if you got their N factors, you're done. Right? If you got their N factors, you can easily calculate their equivalent weights. I hope this is clear to everyone. Yeah? But for that, my dear students, I gave you the structures of these compounds. You need to remember those structures first of all. Then only you can calculate the N factors. I hope this is clear. Now, there is one more point which is related to acids only. That is, it is the boric acid. Have you heard about boric acid? H3BO3? Right? Boric acid. Sometimes in the examination, they might give you boric acid in this format, BOH whole thrice. This is also the boric acid. You can write it like this as well. This again H3BO3. Right? This again H3BO3, boric acid. Perfect. This again boric acid. Now, when you introduce boric acid into water, what happens exactly? My dear students, this is H3BO3. When you introduce this boric acid into water, you get a reaction like this. BOH4 negative plus H positive. BOH4 negative plus H positive. Let me write it like this. This was your BOH whole thrice, right? Plus water gives this. Gives this. Gives this. Now, my dear students, if you look at this particular reaction carefully, how many OHs did we have here? 3. Now, how many do we have? 4. So, when this reaction is happening, can I say this acid is accepting one OH negative? It is accepting one OH negative, right? This acid is accepting one OH negative. The number of OH negatives an acid accepts, that also defines its basicity. And whatever is the basicity of the acid, that's its N factor. So do remember, N factor of boric acid over here will be 1 because it's accepting one OH negative. Let me tell you, this boric acid, it is a weak Lewis acid, by the way. It is a weak Lewis acid, and do remember its N factor is 1. And if you got its N factor, you can easily calculate its equivalent weight. Molecular weight divided by N factor. Molar mass divided by N factor. Done. Yeah? Perfect. Now, there are few things which you need to know about acids as well. I'm writing few reactions here. Let's say I'm writing H2SO4 plus NaOH. H2SO4 plus NaOH. For example, it gives NaHSO4 plus water. This is one reaction which I wrote. H2SO4 plus 2 times NaOH. 2 times NaOH. It gives Na2SO4 plus 2 times water. These are the two reactions which I wrote over here. Now, in these two reactions, if I ask you, in these two reactions, what is the N factor of this H2SO4 and this H2SO4? Understand. Understand. My dear students, both the reactions are first of all balanced. You know, when one H positive reacts with one OH negative, what do we get? We get 1 mole of water. When 2 H positives combined with 2 OH negatives, you get 2 moles of water. Perfect. In the first case, 1 mole of water is being formed. If 1 mole of water is being formed, can I say from here, 1 mole of H positive would have come. From here, 1 mole of OH negative would have come. They would have interacted and formed 1 mole of water. So this acid is donating only 1 H positive. The number of H positives an acid donates, that defines its N factor. N factor of H2SO4 in this reaction is 1. Right? If you look at the second one, 2 moles of water are being formed. 2 moles of water. So for the formation of 2 moles of water, I would say this would have given 2 moles of H positive. This would have given 2 moles of OH negative. They would have interacted and formed 2 moles of water. So since this is giving 2 moles of H positive, so its N factor has to be 2. So N factor of H2SO4, I mean N factor of an acid, it can change when you change the type of the reaction. My point is that. When you change the type of the reaction, N factor of an acid can change. Okay? N factor of an acid changes on changing the type of the reaction in which it is participating. Is that clear? This was all about acids which you need to remember. I hope all the things are clear till now. Is it? Is it, guys? Now, similarly, we can talk about the N factor of bases as well. We can talk about the N factor of bases as well. N factor of bases. How do you exactly define the N factor of bases? What is the N factor of a base? Exactly. N factor of the base is the acidity of the base. How do I define the acidity of the base? Number of OH negatives a base donates. Number of OH negatives a base donates. Second, number of H positives a base accepts. A base accepts. You can remember just these two. This is more than sufficient. This is more than sufficient. See guys, for example, if I talk about some simple bases, let's say you have got NaOH. You have got NaOH. Tell me, when you put this NaOH into water, how many OH negatives it's going to give? It's going to give you 1 OH negative. the number of OH negatives donated by a base that defines its N factor. So N factor of NaOH here is 1. So all these simple ones you can calculate, I believe. You can do that on your own. For example, I'm writing NH3. I'm introducing this NH3 into water. Now what's going to happen here? This nitrogen has got the lone pair. Perfect. This nitrogen has got the lone pair. It will take H positive from here and it will get converted into what? NH4 positive. Over here, 3 hydrogens, 4. So can I see this NH3? It has accepted 1 H positive. This NH3 has accepted 1 H positive. The number of H positives a base accepts, that defines its N factor. N factor of NH3 here is 1 because it's accepting 1 H positive. It is accepting 1 H positive. For example, you have got something like this. NH2, CH2, CH2, NH2. Now here you have got 2 nitrogen atoms. Here 1 lone pair, here 1 lone pair. So it will accept how many H positives in water? It will accept 2 H positives. Right? So N factor here will be 2. Perfect. For example, I'm giving you reactions like this. Zinc hydroxide plus HCl. Let's say it gives ZnOHCl plus water. Similarly, I'm writing one reaction like this. Plus 2 times HCl. It gives ZnCl2 plus 2 times water. Can you tell me the N factor of zinc hydroxide in both these reactions? Is it same or different? What do you think? Is it same or different? What do you think? Same or different? Same or different? Quick. See guys, over here 1 mole of water is formed. So for the formation of 1 mole of water, this would have given 1 mole of OH negative, right? So it is donating 1 OH negative, so its N factor here is 1. And over here it will be 2. Perfect. So if you got the N factor, you can easily calculate the equivalent weights. So this was how you calculate the N factor of the bases. Okay. Now comes the most important thing. What is that? That is N factor of oxidizing and reducing agents. How do we exactly calculate the N factors of oxidizing and reducing agents? This is the most important part. I hope all these things, whatever I discussed till now, I hope every single thing is clear. N factor of oxidizing and reducing agents. Guys, understand the things which I'm telling you. Understand it in the similar manner, the way I'm going to tell you. Okay? Perfect. See guys, here to make you understand all the things, I'm going to write 3 reactions, 3 general reactions, with the help of which you'll understand, first of all, how do we get the N factors of oxidizing and reducing agents. See guys, I'm writing a reaction, for example, a general reaction. A plus B gives A positive plus B negative. This is the reaction which I wrote. Understand carefully. First of all, the oxidation state of A is 0, this is 0, this is plus 1, this is minus 1. Now tell me, what is happening to the oxidation state of A? It is increasing. Increase in the oxidation state is oxidation. The one which undergoes oxidation, that is the reducing agent. 0 to minus 1, decrease in the oxidation state, reduction. So it is the oxidizing agent. So first of all, I identified which one is my oxidizing agent and which one is my reducing agent. Okay. Now, how do I calculate N factors of these oxidizing and reducing agents? First of all, it is always equal to number of moles of electrons lost, gained, or exchanged by 1 mole of substance. And how do we get this? That is the point. I'm writing here N factor of A, which is the reducing agent. N factor of A is equal. What is the change in the oxidation state of A? 0 to plus 1. 0 to plus 1, calculate the change. Change will be final minus initial. 1 minus 0, that comes out to be 1. This is the change in the oxidation state for one atom of A. How many atoms of A do we have? Only one. So I'm multiplying it with 1. So n factor of A here is 1. Simple. Right? N factor of A here is 1. What is the n factor of B here? What is the n factor of B here? 0 to minus 1. 0 to minus 1. Calculate the change. Final minus initial. Final is minus 1. Initial is 0. Take the mod. The value comes out to be 1. 1 is the change for one atom. How many we have? Only 1. This is the n factor of B. Simple. Simple, guys. Yeah? Correct? For example, I'm writing something like this. A2 plus B2. It gives 2 times A positive plus 2 times B negative. This is the reaction which I wrote. A2 plus B2 gives 2 times A positive plus 2 times B negative. Try to understand. Oxidation state 0, 0. Here we have got plus 1. Here we have got minus 1. If I ask you what is the n factor of A2 here, n factor of A2, it will be equal to A2. 0 to plus 1. Change. Final minus initial. The value comes out to be 1. 1 is the change for one atom, but I have 2. So 1 multiplied by 2. The value comes out to be 2. So 2 is the n factor of A2. N factor of B2 will be equal to 0 to minus 1. Change is 1. 1 is the change for one atom, but I have here 2. The value comes out to be 2. So this is how you calculate n factors of different species. Right? Right, people? And if you got the n factors, you can calculate their equivalent weights. Molecular weight divided by n factor. Perfect. Someone is asking a question that comes from this particular topic. This is the question, right? Equivalent weight. Calculate the equivalent weight of this species. Calculate the equivalent weight of that species. I hope all these things are absolutely clear to you. Okay? I hope all these things are absolutely clear to you. Now, guys, something really important, right? Something really important, which I'm going to let you know. You have got 2 important oxidizing agents here. One is called as KMnO4. One is called as K2Cr2O7. KMnO4 and K2Cr2O7. My dear students, this KMnO4, or you can write MnO4 negative. You can write MnO4 negative. In acidic medium, it gets converted into Mn di positive. Your KMnO4, or you can call it as MnO4 negative. MnO4 negative. And remember, you have to remember these things. In acidic medium, it gets converted into Mn di positive. In which medium? Acidic medium. Acidic medium, right? In neutral or slightly alkaline medium. In neutral or slightly alkaline medium, the KMnO4, it gets converted into what? MnO2. And let me tell you, in strongly alkaline medium, the same KMnO4, it gets converted into what? MnO4 dinegative. These 3 things you have to remember first of all. KMnO4 in acidic medium gets converted into Mn di positive. Right? In neutral or slightly alkaline medium, MnO2. In strongly alkaline medium, MnO4 dinegative. Now, what is the n factor of MnO4 negative in all these 3 mediums? How do I do that? How do I do that? See, oxidation state of manganese here is plus 7. Here it is plus 2. So in acidic medium, plus 7 to plus 2. What is the change? 5. 5 is the change for one atom of manganese. I have one atom only. So n factor of KMnO4 in acidic medium is just 5. Remember it directly from now onwards. Right? Similarly, manganese plus 4. So plus 7 to plus 4. What is the change? 3. So n factor of KMnO4 in neutral or slightly alkaline medium, it's 3. Similarly, here it's plus 6. Plus 7 to plus 6, change is 1. N factor in the third case is 1. N factor in the third case is 1. Okay? Right? Right, people? Is that clear? KMnO4, which is a strong oxidizing agent. In acidic medium, it shows N factor of 5. In neutral medium, it shows 3. In strongly alkaline medium, it shows 1. Yeah? Okay? And now, people, since this KMnO4, it's a strong oxidizing agent. What it does in acidic medium, that is again very important. That's again very important. What it exactly does in acidic medium. First of all, in acidic medium, you know, your KMnO4 or you can say MnO4 negative, it gets converted into Mn di positive. In which medium? I'm talking about acidic medium. Now, what it does to others, let's have a look. The first thing, KMnO4 in acidic medium converts Fe di positive into Fe tri positive. The first thing which you have to remember. It converts Fe di positive into Fe tri positive. Number two, it converts Sn di positive into Sn plus 4. Again in acidic medium, right? It converts oxalate ion into carbon dioxide. It converts H2O2 into O2. H2O2 into O2. It converts H2S into sulfur. It converts H2S into sulfur. It converts I negative into I2. It converts I negative into I2. These things you have to remember, guys. KMnO4 in acidic medium converts Fe di positive into tri positive, Sn plus 2 into Sn plus 4, oxalate into carbon dioxide, H2O2 into O2, H2S into sulfur, I negative I2. If you just remember this part, you can easily write the reactions. How? You can easily write the reactions. You need not to mug up the reactions which you see in D and F block elements for KMnO4 and K2Cr2. You can check that here only. How? Try to understand. The first reaction, your KMnO4 converts Fe di positive. In which medium? Acidic medium. Into what? Fe tri positive. Itself gets converted into Mn di positive. And with that, you just have to write water. This is the reaction. Done and dusted. Yeah? Similarly, your KMnO4, look at the second reaction. It converts Sn di positive. In which medium? Acidic medium. Into what? Sn plus 4. Itself gets converted into Mn di positive. And with that, you'll be writing water as well. That? Can you similarly write all the reactions? Can you similarly write all the reactions? Say yes or no in the chats. I don't want to waste time in order to write all these reactions now. Can you write all these reactions on your own? Say it quickly. Perfect. Now, if you talk about another one, K2Cr2O7. K2Cr2O7. This is also a strong oxidizing agent, and in acidic medium, it gets converted into chromium tripositive. In acidic medium, it gets converted into chromium tripositive. If I ask you first of all, what is the N factor of K2Cr2O7 here? Quickly. Chromium here is in +6 oxidation state. So +6 to +3, change, that is 3. 3 is the change for one atom of chromium, but I have 2. So 3 2s are 6. So N factor of K2Cr2O7 here is 6. Okay. Now, since K2Cr2O7, it's again a strong oxidizing agent, so it is going to show the similar reactions which your KMnO4 showed. First one, it converts Fe di positive into Fe tri positive. Number 2, it converts Sn plus 2 into Sn plus 4. Number 3, it converts I negative into I2. Number 4, it converts oxalate ion into carbon dioxide. Number 5, what was the fifth one? H2S to sulfur. Number 6, H2O2 to O2. It shows the similar reactions. Now you should be able to write all these reactions on your own. I'll just show you one or two. Rest you can do on your own. See guys. So first reaction will be your K2Cr2O7. It converts what? Fe di positive. In which medium? Acidic medium. Into what? Into Fe tri positive. Itself gets converted into Cr tri positive. With that, you'll be writing water as well. So this is the reaction. Done? This is the reaction. Let's say I need to write this particular reaction. K2Cr2O7 converts oxalate ion. In which medium? Acidic medium. Into what? Carbon dioxide. Itself gets converted into chromium tri positive. And with that, you'll be writing water as well. Done? In the similar way, you can write all these reactions. Someone is saying कुछ समझ नहीं आ रहा है. दिमाग यहाँ पे रखोगे तब समझ आएगा ना. I'm seeing you for the first time in the chat. Yeah. Suddenly you enter the session. How will you get? Watch it from the beginning, then you'll get. Okay, I believe all these reactions you can easily write from now on. Yeah. Am I clear, people? Say yes or no in the chats. Am I clear? Am I clear? Am I clear? This chapter will take still 1 hour, 1.5 hour. 1.5 hour this chapter will take. More. Yeah? Perfect. Now, guys, try to understand. Try to understand. Try to understand. Just a second. Just a second. Let me see whether you can calculate the n factors of these oxidizing and reducing agents. Okay. The first question. Calculate the n factor of this I2 here. Can you do it? N factor of I2? Yes, Lavanya, no need to worry. Can you calculate the n factor of I2 here? What is it? Quickly. See, guys. First of all, the oxidation state of iodine here is 0. Here it's plus 5. So 0 to plus 5. What is the change? Final minus initial. The value is 5. 5 is the change for one atom, but I have 2. So 5 to the 10. N factor for I2 here is how much? It is 10. Correct? It is 10. Yeah? Okay. By chance, I'm asking you to calculate the n factor of IO3 negative. What you'll do? IO3 negative. What you'll do? You'll just reverse the same process. Reverse. Now you'll be calling this as initial, this as final. So final minus initial is 5. 5 is the change for one atom and I have only one atom of iodine. So n factor of IO3 negative here will be 5. Yeah? Just reverse the stuff. That's all. Just reverse the stuff. That's all. Okay, this though you can easily do. Quickly tell me the n factor of IO4 negative here. IO4 negative, quickly. See, iodine over here is in plus 7 oxidation state. This is 0. So plus 7 to 0. Plus 7 to 0. Initial, final. Final minus initial. 7. 7 is the change for one atom. I have only one atom. So n factor here is 7. Now I2. 0 to plus 7. 0 to plus 7. Final minus initial. That's 7. 7 is the change for one atom, but I have 2. So 7 to the 14. So this is the n factor of I2. Yeah? I hope you can solve these sort of questions. Can you get the n factor of this particular species? Can you get the n factor of this particular species quickly? N factor of this particular species. Can you get it? Wait, guys, see. First of all, if we calculate the oxidation state of iron here, let's say it's X multiplied by 0.94 plus oxygen shows -2, net charge is 0. So the value of X will come out to be plus 200 divided by 94. Plus 200 divided by 94. Here iron is in plus 3 oxidation state. So this to this. Calculate the N factor. N factor is going to be equal. Final oxidation state minus initial oxidation state. Final minus initial. This is the change in the oxidation state for one atom of iron, but how many we have? 0.94. So multiplying it with 0.94, whatever value you get, that's something which will give you N factor of this non-stoichiometric compound. Yeah? Perfect? Right? Okay. Tell me the N factor of this oxalate ion here. Tell me the N factor of this oxalate ion here. Quickly. Quickly, people. Tell me the n factor of oxalate ion. Quick, 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 very quick. Done? Done, people? You should be able to solve this. Oxidation state of carbon, here is +3, here it's +4. So +3 to +4 changes 1. +3 to +4 changes 1. 1 is the change for one atom, but I have 2 atoms of carbon. So n factor of this particular species is 2 here, right? So I believe you can easily solve the n factor stuff. Yeah? I believe you can do that. Now guys, till now, what I was doing, till now, if you observed, we were calculating the n factors of those oxidizing or reducing agents wherein oxidation state of only one element was changing. And we were calculating change in the oxidation state of that element, right? Till now, if you observed, I gave you only those oxidizing and reducing agents wherein oxidation state of only one atom was changing. And we were calculating that change in the oxidation state. What if there is a species? What if there is the oxidizing or reducing agents wherein the oxidation state of more than one element is changing simultaneously? How do we calculate this n factor? Remember directly. If you have got a species in which oxidation state of, let's say, 2 elements is increasing or decreasing. Let's say you have got a species wherein oxidation state of 2 elements is increasing or decreasing. How do we calculate n factor of that particular species? It is simply going to be n1 plus n2. Let's say you have got a species in which oxidation state of one element is increasing, another one is decreasing. It is going to be mod of n1 minus n2. Just remember it directly. Just remember it directly. Whenever you see oxidation state of more than one element simultaneously increasing or decreasing, simultaneously oxidation state of both elements is increasing or simultaneously oxidation state of both elements is decreasing. At that point of time, n1 plus n2. If one increases, one decreases, n1 minus n2. Now, what is this n1? What is n2? Try to understand. See guys, if you look at this particular case, carefully, iron here is in +2 oxidation state. Carbon here is in +3 oxidation state because it's oxalate, right? Here iron is in +3, here carbon is in +4. If you check carefully, +2 to +3, increase. +3 to +4, increase. Oxidation state of more than one element is increasing simultaneously. So what do I do? How do I calculate its n factor? Its n factor will be calculated as n1 plus n2. Now the point is, how do I get n1 and how do I get n2? That is something which we already discussed. Have a look. +2 to +3, change is 1. 1 is the change for one atom of iron and I've got only 1. n1 is 1. +3 to +4, change is 1. 1 is the change for one atom of carbon, but I have 2. So n2 is 2. So n1 is 1, n2 is 2. So 2 plus 1 comes out to be 3. So 3 is the overall n factor of this particular species. I believe this is clear to everyone. Let me give one more example. People. All right. Look at this particular example. First thing, oxidation state of copper here is +1, sulfur here is -2. Copper here is +2, sulfur here is +4. So +1 to +2 is increase. -2 to +4 is also increase. Oxidation state of more than one element is increasing simultaneously. So how do you do it? n1 plus n2. +1 to +2, change is 1. 1 is the change for one atom, but I have 2. So n1 is 2. -2 to +4. -2 to +4, change is 6. Right? Change is 6. And there is one atom only. n2 is 6. 6 plus 2 is 8. 6 plus 2 is 8. Yeah? Right, people? Now let's see one of the element wherein oxidation state of one element increases, another element decreases. Let's see what happens in that. Just a second. Let's take one example of that as well. Look at this particular case. Look at this particular case. If you look carefully, iron has in +3 oxygen state, sulfur is in -2, iron here is in +2, right? And sulfur here is in +4. My dear students, if you look carefully, which case it is? Which case it is? +3 to +2, decrease. -2 to +4, increase. Oxidation state of one element is decreasing, another one is increasing simultaneously. How do I do it? N1 plus N2 or N1 minus N2? I'll be calculating its N factor as mod of N1 minus N2. Now, get the N1, get the N2. +3 to +2, change is 1. 1 is the change for one atom of iron, but I have 2. N1 is 2. Similarly, -2 to +4, change is 6. Final minus initial, change is 6. 6 is the change for one atom, but I have 3. So 6 3s are 18, right? So the value, overall value comes out to be 16. I hope this is clear. I hope this is clear. Now, the final case of the N factors. The final case of the N factors. The final case of the N factors. How do we calculate N factor for the substance? How do we calculate N factor for the substance that undergoes disproportionation? N factor of substance that undergoes disproportionation. That undergoes disproportionation. N factor of that substance which undergoes disproportionation. This is the final case of the N factors. Yeah? No, that was not disproportionation. The one which I gave you. See what is disproportionation. Let's say you have got the reaction like this. A2, it gives A positive plus A negative. Let's say this is the reaction. Okay? Oxidation state here is 0. Here it is +1. Here it is -1. 0 to +1. Increase in the oxidation state. 0 to -1. Decrease in the oxidation state. So I can say oxidation state of same element is simultaneously increasing and decreasing. There it was not the same element. Those were two different elements. Species was same, but elements were different. Here the element is same. Yeah? Right, people? So oxidation state of one element is increasing. Oxidation state of an element is increasing as well as decreasing simultaneously. Right? So how do I get its N factor? Its N factor is calculated as N1, N2 divided by N1 plus N2. N1, N2 divided by N1 plus N2, yeah? Right, people? It is basically oxidation as well as reduction of same species happening, of same element is happening. Right? Right, people? Now, get the N1, get the N2. We are done, we are sorted. See, 0 to -1, change is 1. 1 is the change for one atom out 2. So N1 value here is 2. N1 value here is 2. 0 to -1, change is 1. 1 is the change for one atom out 2. So N2 value is again 2. So 2 multiplied by 2 divided by 2 plus 2, the value comes out to be 1. 1 is the N factor of this A2 over here. I'm giving you a question. Tell me the answer of this question. Br2 gives Br negative plus BrO3 negative. Tell me the N factor of this Br2. You are in a position to answer this one. Trust me. Oxidation state here is 0. Here it's -1. Here it's +5. 0 to -1. Decrease. 0 to +5. Increase. Get its N factor. It is N1, N2 divided by N1 plus N2. N1, N2 divided by N1 plus N2. Now 0 to -1. Change is 1. 1 is the change for one atom, but I have 2. N1 value is 2. 0 to +5. Change is 5. 5 is the change for one atom, but I have 2. So 5 2s are 10. Right? So this is going to be 10 multiplied by 2 divided by 10 plus 2. The value is 20 divided by 12. So this is 4, 5, 4, 3. So N factor of Br2 here comes out to be 5 by 3. Yeah? There was one question asked long back in AIMS. H2O2 gives H2O plus O2. I'm giving you the oxidation stage. This -1, this -2, this is 0. Can you tell me its N factor right now? Can you tell me its N factor right now? N factor of H2O2 quickly. Quickly, people. Quickly. Quickly, everyone. everyone. People are saying it's 1. Are you sure? Are you sure? Are you sure? I feel you're sure about it, yeah? I feel you're sure about it. Chalo, let's see. -1 to -2. So decrease in the oxidation state. -1 to 0. Increase in the oxidation state. Again, oxidation state of the same element is increasing as well as decreasing simultaneously. Right? Right, people? So how do we calculate its n factor? N1, N2 divided by N1 plus N2. Now, -1 to -2. Change is 1. 1 is a change for one atom, but I have 2. So N1 is equal to 2. -1 to 0. What is the change? 1. 1 is the change for one atom, but I have 2. So N2 is also 2. So 2 multiplied by 2 divided by 2 plus 2. The value comes out to be 1. So n factor of H2O2 here in this disproportionation reaction, it is 1. Be careful with this. Right? I have seen a lot of teachers think n factor of H2O2 is equal to 2 in this disproportionation, but it is 1. Remember this. Yeah? Remember this. Perfect, guys? Perfect. So with this, your n factor calculation is done and dusted. Now, balancing won't take more than 15 minutes. Complete balancing. Guys, wait. What break you are saying? What break? Do you deserve the break or do I deserve the break? I deserve the break, right? More than you, but I'm not asking for it, nor I want it. We have to complete a lot of stuff. A lot of stuff. Okay? So first of all, since you are not going to write any boards examination, you just have to write NEET examination. So there is no need to go for all the methods of balancing. It is just you should know how to balance the reaction. That's enough, right? It is just you should know how to balance the reaction. Whether you are balancing it with this method or this method, one and the same thing. Our point is just to balance the reaction. So we are not going to discuss all these balancing stuff. We are just going to discuss one method, which is going to be easy for you, by means of which you can balance the reactions. Okay? And that method is your oxidation number method. Oxidation number method. Right? Oxidation number method. So, first of all, let's discuss oxidation number method in acidic medium. See how easy it is. Right? See how easy it is. See how easy it is. For example, my dear students, I'm writing a reaction like this. MnO4 negative plus Fe di positive. It gives Fe tri positive plus Mn di positive. This reaction, let's assume you have to balance in acidic medium. How you guys are going to do it? What are the steps to be followed? Understand. In less than 30 seconds, you can balance the reaction if you understand the concept behind it. See guys, first of all, get the oxidation states of these species. +7, +2, +3, +2. Got the oxidation states, right? Calculate the n factor of this particular species. +7 to +2. Change is 5. So its n factor is 5. +2 to +3. Change is 1. Its n factor is 1. So first thing what I did over here is I calculated the n factors. I calculated the n factors of all the reactants. I calculated the n factors of all the reactants. Right? Got the n factors? After getting the n factors, just crisscross them. Make this 1 as the coefficient here. Make this 5 as the coefficient here. First, get the n factors. After getting the n factors, just crisscross them. Okay? Number 2. Number 3. Balance all the atoms except hydrogen, oxygen. Balance all the atoms except hydrogen, oxygen. So 1 manganese, 1 manganese. 5 iron, 5 iron. Balance all the atoms except first one, get the n factors of reactants. Second, crisscross them. Third, balance all the atoms except hydrogen, oxygen. Now, you are balancing the reaction in which medium? In acidic medium. Now, in acidic medium, what do we need to do? We'll be balancing oxygen with the help of water molecules, and then we'll be balancing hydrogen with the help of H positives. Now, understand. First, you're going to balance oxygen. How many oxygen atoms do we have on the left side? Only 4. Is there any oxygen on right side? No. So can I say right side is oxygen deficient? Yes. How many oxygen deficiency is there? 4 oxygen deficiency. And oxygen deficiency is removed by water molecules. So I'll be adding 4 water molecules on this side so that oxygen becomes equal on both the sides. So oxygen is balanced. Now, balance hydrogen. How many hydrogen on this side? 4 2s are 8. Any hydrogen here? No. Right? So this side is hydrogen deficient. And that side, which is hydrogen deficient, add H positives on that side. 8 hydrogens, no hydrogen. So add 8 H positives here. Now there's a balanced chemical equation. Am I clear? You are not supposed to do anything extra. Okay? Just follow these marathons, follow the question practice which we do, extra 500 stuff. Perfect. That's more than sufficient. Nothing else you have to do. Don't waste your time. Done? I'll take one more example. With that, we'll get over. I'll take one more example. Chalo. For you guys, I'll take one more. Let's say we have got the reaction like this. Okay. Cr2O7 dinegative plus oxalate ion. It gives Cr tripositive plus carbon dioxide. Balance this reaction in acidic medium. Again, the similar approach. Again, people, the similar approach I'll be using here. Get the n factors. You know how to do it. Its n factor is 6. Its n factor is plus 3 to plus 4 is 1, 1, 2. Okay. You got the n factors. Now, after getting the n factors, crisscross them. So, make this 2 as the stoichiometric coefficient here. Make this 6 as the stoichiometric coefficient here. Done. Balance all the atoms except hydrogen oxygen. 4 chromium, 12 carbon. Now, balance oxygen with the help of H2O molecules. How many oxygen on left side? 7, 2, 14, 6, 4, 24. So 24 plus 14 comes out to be 38. 38 oxygen atoms. 24 oxygen atoms. Which side is oxygen deficient? Right side. How many oxygen deficiency? 14 oxygen deficiency. 14 oxygen deficiency means add 14 water molecules. Yeah? Now, talk about hydrogen. 28 hydrogen atoms. No hydrogen atoms. So add 28 H positives on this side. Right? To balance hydrogen. Now, this is a balanced chemical equation. No need to do anything. Yeah? Done? People, is everything clear? This was how do you balance the reactions in acidic medium. Okay? Right? I want everyone to say it in the chats. Is every single thing clear till here? Right? Okay, now comes your which medium? Basic medium. In basic medium, I'll give you one example. That's all. In basic medium, let me give you one example. That's enough. That's enough. Anyways, balancing is least important. Okay. How do we balance the redox reactions in basic medium? Okay. Look at this particular reaction carefully. Again, the first few steps are same. The first few steps are same. Oxidation state of chlorine here is 0. Iodine here is plus 5. Chlorine here is minus 1. Iodine is plus 7. Get the n factors. 0 to minus 1. Change is 1. 1 is the change for 1 atom out 2. So its n factors 2. Plus 5 to plus 7. Its n factors also 2. So you got the n factors. You got the n factors. Now, you got the n factors. Now, crisscross the n factors. Crisscross the n factors, nothing else. Crisscross the n factors. Make the 2 coefficient here as well. You have crisscrossed the n factors. Balance all the atoms except hydrogen, oxygen. So 4 chlorine, 2 iodines, 2 iodine. So balanced all the atoms except hydrogen, oxygen. Right? Now, since the reaction is happening in basic medium, till here everything is same. But now in basic medium, what do we need to do? We need to balance the negative charge first by adding OH negatives on that side, which is negative charge deficient. We need to balance. In acidic medium, we used to balance oxygen first by adding water molecules. But here, I'll be balancing the negative charge first by adding OH negatives on that side, which is negative charge deficient. And after that, I'll balance oxygen with the help of water. That's all. That's all. Now, have a look. No charge here. If you look at this, one IO3 molecule carries -1 charge, so 2 will carry -2. Okay? One Cl carries -1 charge, so 4 will carry -4. One IO4 carries -1, 2 will carry -2. So -4, -2 comes out to be -6. So you got the total negative charge on left side, total negative charge on right side. Okay? Tell me people, -2, -6. Which side is a negative charge deficient? Left side or right side? Which side is negative charge deficient? Left side or right side? Quickly. Left side or right side? Quickly. Left side is negative charge deficient. How much negative charge deficiency is on left side? 4. And that negative charge deficiency is compensated by OH negatives. So how many OH negatives I would add here? 4 OH negatives. Because there was the deficiency of 4 negative charges. Right? Done? Negative charge balanced. After that I have to go to oxygen. How many oxygen on left side? 3 2s are 6, 6 4 10. So 10 oxygen atoms on left side and 4 2s are 8. 8 oxygen atoms on right side. 10, 8. Which side is oxygen deficient? Which side is oxygen deficient? 10, 8. Right side is oxygen deficient. How much oxygen deficiency is there? 2 oxygen deficiency. That means oxygen deficiency is compensated by water molecules. So how many water molecules do I have to add on right side? I'll say I'll be adding 2 water molecules on right side. Perfect. The reaction automatically gets balanced. Perfect. Right, people? Am I absolutely clear to everyone? You can let me know quickly in the chats. This was your balancing, which is done and dusted. Quick. Quick, people. Done? Quickly, everyone in the chats. No, the chapter is not complete yet. Wait. Chapter is not completed yet. There are a few more important things which you need to know. I hope all these things are absolutely clear to every one of you. Let's move ahead, guys. Let's move ahead. Let's move ahead. Well, there was one concentration term which I did not discuss with you. That was normality. So let's try to cover this normality. And with normality, we'll end this chapter. Okay? With normality, we'll end this chapter. Okay? So guys, before talking about normality, I need to tell you about the number of gram equivalents. The number of gram equivalents of any substance. The way you calculate number of moles of any substance, in the similar way, we can calculate number of gram equivalents of any substance. The way we calculate number of moles of any substance, okay, the way we calculate number of moles of any substance, in the similar way, we can calculate number of gram equivalents of any substance. Okay, and how do we calculate number of gram equivalents of any substance? It is equal to mass of the substance in grams divided by equivalent mass of the substance. Divided by equivalent mass of the substance. Divided by equivalent mass of the substance. I'll write it. Mass of the substance in grams divided by what? Divided by equivalent mass of the same substance. This is the first formula by means of which we can calculate number of gram equivalents of particular substance. It is also equal to number of moles of the substance multiplied by n factor of the substance. Right? Number of moles of the substance multiplied by n factor of the substance. Okay? Now, similarly, there's a term called as number of milli-equivalents. Number of milli-equivalents of the substance. It is also, it's equal to given mass of the substance in grams divided by equivalent mass of the substance multiplied by 1000. Or instead of moles, you can write number of millimoles of the substance multiplied by n factor. So first of all, remember these two results by means of which you calculate the number of gram equivalents of the substance and number of milli equivalents of the substance. Yeah? Perfect? Perfect, guys? Okay, I'll be discussing titration also. Just wait. Just wait. So, my dear students, after remembering these formulas, now I'm going to move on to something called as normality. Normality, which is represented by capital N. Understand? Normality, which is represented by capital N. How do you define the term normality, first of all? How do we define the term normality, first of all? Normality is defined as the number of gram equivalents of solute, the number of gram equivalents of solute present in 1 liter of solution. How do you define molarity? Number of moles of solute present in 1 liter of solution, right? Here, in place of moles, what do we use? Gram equivalents. Number of gram equivalents of solute present in 1 liter of solution. How do you calculate normality? Simple formula. Number of gram equivalents of solute divided by volume of solution in liters. Gram equivalents of solute means mass of solute in grams divided by equivalent mass of solute. Volume of solution in liters means if I take it in ml, in the numerator, I'll have to multiply that with 1000. Right? Perfect. And there is one more direct result between normality and molarity. Normality is equal to molarity of the solution multiplied by n factor of solute. These are the three results which I would want you guys to remember as well. These are the three results which I want you guys to remember. Yeah? Perfect. Guys, there is one more thing. Do you see normality is equal to number of gram equivalents of solute divided by volume of solution in liters? So can I say gram equivalence is equal to normality multiplied by volume in liters? Gram equivalence is equal to this multiplied by this. I can say that, right? So gram equivalence, I can calculate like this as well. Normality multiplied by volume of solution in liters. Milli equivalence, I can calculate like this. Normality multiplied by volume of solution in ml. This is the just difference. This is the only difference. This is the only difference. If I take volume in ml, it gives you milli equivalence. If I take volume in liters, it gives you gram equivalence. That's all. That's all. That's all, people. If this is clear, just tell me the answer of this very simple and basic question. Quickly. What do you think is the answer of this one? Are we done with this? Are we done with this, people? Quickly. Quickly. Are we done with this? Okay. The gram equivalence in 50 ml of 0.5 normal NaOH. Guys, I told you already. Number of gram equivalence is equal to normality multiplied by volume of solution in liters. Normality is given as 0.5. Volume of solution is given as ml, 50 ml. So divide it with 1000. Then only you'll be getting liters. Just solve it and get the gram equivalence of solute in the solution. Right? Perfect. Now comes the actual stuff, and that is the last topic of the chapter. That is redox titration. That is redox titration. Okay? That is redox titration. Or I'll be calling it as equivalent concept as well. I'll be calling it as equivalent concept as well. I'll be calling it as equivalent concept as well. This is important. Have a proper eye on this, right? There can be questions asked from this particular topic in this particular examination as well. Okay? Equivalent concept. My dear students, for example, I have got a general chemical reaction A plus B. It gives C plus D. Okay? Equivalent concept says that you are not supposed to balance the reaction. Equivalent concept says that no need to balance the reaction. Okay? No need to balance the reaction. Simple equivalent concept says that gram equivalence of A reacted in the reaction has to be same as that of gram equivalence of B reacted, which has to be same as that of gram equivalence of C formed, which has to be same as that of gram equivalence of D formed. One simple statement you need to write. As per equivalent concept, whatever gram equivalence of A would have reacted, same gram equivalence of B also would have reacted. Same gram equivalence of C would have formed. Same gram equivalence of D also would have formed. Well, you can write the same statement in terms of milli equivalence as well. You can say milli equivalence of A reacted has to be equaled. Milli equivalence of B reacted has to be equaled. Milli equivalence of C formed. Milli equivalence of D formed. Milli equivalence of D formed. This is the concept which I'll be using in the questions. Number one. Number two, if this was case 1, let's say this is case 2 now. This was case 1. Now, I'm going to give you case 2. For example, you see a scenario like this. Let's say this is the container, and in this container, we have got A, B, and C. It's a mixture of A, B, and C. For example, I'm adding one more substance D over here. Let's say I'm adding one more substance D over here. And for example, the D which I'm adding, it is reacting with A, it is reacting with B, but it's not reacting with C. Let's say it's reacting with A, reacting with B, but for example, not reacting with C. Now, how do you write the statement over here in the case second? You'll write it like this. Gram equivalence of A reacted plus gram equivalence of B reacted, it has to be equal directly gram equivalence of D reacted. I'll have got nothing to do with the C over here. I've got nothing to do with the C over here. Nothing to do with C over here. Perfect. So remember these two statements. Remember these two statements. Okay? These two statements are super important, my dear students. So remember them directly. Yeah? Remember them directly. Now, how do we use them? Before that, there are few n factors which I want you guys to remember directly. For example, KMnO4 in acidic medium, tell me its n factor we have discussed. In acidic medium, its N factor is 5. K2Cr2O7. K2Cr2O7. In acidic medium, its N factor is 6. Okay. Now, people, for example, you have got FeSO4. You have got FeSO4. Let's say in acidic medium, it's reacting with KMnO4. Let's say in acidic medium, it's reacting with KMnO4. So can I say this KMnO4, it will convert this Fe di positive into Fe tri positive? So Fe di positive is being converted into Fe tri positive. So change is 1. So if I ask you, what is the N factor of FeSO4 here? When FeSO4 will be reacting with KMnO4 or K2Cr2O7 in acidic medium, its N factor will be taken as 1. Its N factor will be taken as 1. Correct? Now, similarly, if you have, for example, FeC2O4, ferrous oxalate, if it reacts with KMnO4 or K2Cr2O7 in acidic medium, its N factor will be 3. Just remember these few of N factors directly, right? Perfect. Then you have got FeC2O4 whole thrice, ferric oxalate. Its N factor, you'll be taking a 6. Okay. What else can we need here? More salt. More salt. If it reacts with KMnO4 or K2Cr2O7 in N factor, its N. I mean, if it reacts with KMnO4 or K2Cr2O7 in acidic medium, its N factor is 1. More salt. Remember directly. Then you have got Cu2S 6, CuS 8, right? CuS 8, sodium oxalate Na2C2O4 or potassium oxalate K2C2O4. When it combines with your KMnO4 or K2Cr2O7 in acidic medium, its N factor will be taken as 2. Perfect. Remember these N factors. And if you remember these N factors, now we are in a position to solve a lot of questions. But before solving the questions, I would want you guys to remember these formulas which I gave you. How many formulas are there to calculate gram equivalence? 3 formulas. One is mass by equivalent mass, given mass by equivalent mass. Second, moles multiplied by N factor. Third, normality multiplied by N factor. Sorry, normality multiplied by volume of the solution in liters. Similarly, given mass divided by equivalent mass multiplied by 1000. Millimoles multiplied by N factor. Third is normality multiplied by volume of solution in milliliters. Right? These are the results which we have. You know it. These are the results which we have. Now, people, it is the high time to use these results and do the questions based on titration. The first question which is on your screen. The first question which is on your screen. The first question which is on your screen. Quickly. Quick. Can you do this? See, guys, how exactly we are going to solve these questions. See exactly how we are going to solve these questions. First of all, the actual procedure of solving these questions is you're supposed to write the reaction first, then you're supposed to balance it, then etc. Takes a lot of time. Okay. Did I write the N factor of Cu2S reverse? Guys, N factor of Cu2S is 8, N factor of Cus is 6. If I interchanged by any mistake, please change that. Cu2S it is 8, Cus it is 6. Okay? Alright, now look at this particular question. Carefully look at the question. Carefully. What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar ferrous oxalate in acidic medium? So try to understand which all things are reacting over here. As per the question, your KMnO4 is reacting with what? Your KMnO4 is reacting with FeC2O4, ferrous oxalate. In which medium? In acidic medium. Okay. If I represent this by number 1, I'll be representing this by number 2. Okay. If I ask you what is the N factor of KMnO4 in acidic medium, you should know it, 5. What is the N factor of ferrous oxalate here? It will be 3. Already discussed. What volume of 0.1 molar KMnO4? So molarity of KMnO4 is given, 0.1. Molarity of ferrous oxalate is also given, 0.3. What volume of this is required to oxidize 100 ml of this? So its volume is given. Correct, people? Now understand and analyze things. Tell me one thing, people. You know, I have already given you one result which connects normality and molarity. Over here, if you look carefully, molarity we know, Its n factor we know. So molarity multiplied by n factor gives me normality. So normality of 1 is equal to 0.5. Correct? Molarity multiplied by n factor here gives me normality. So normality of 2 is equal to 0.9. Done. Now tell me one thing. Tell me one thing. Tell me one thing. Tell me one thing. Volume is given in ml. Volume is given in ml. The statement which I'll be using, should I be using the statement in terms of gram equivalence or milli equivalence? Volume is in ml. Volume ml means milli equivalence. I'll directly say milli equivalence of KMnO4 reacted has to be equal to what? Milli equivalence of ferrous oxalate reacted, right? Milli equivalence of 1 means normality of 1 multiplied by volume of 1 in ml. This is normality of 2 multiplied by volume of 2 in ml. What is normality of 1? 0.5. Volume of 1 we need to calculate. Normality of 2, 0.9. Volume of 2 is 100. So V1 comes out to be 180 ml. So what is meant by this 180 ml, people? What is meant by it? It means that 180 ml of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar ferrous oxalate in acidic medium. Yes. Am I clear with this? Am I clear with this? This is the first type of the question which can be asked in the titration. First type of the question. The second type I'm going to show you. Second type. Second type. How many moles of KMnO4? How many moles of KMnO4 will be required to react completely with 1 mole of K2Cr2O7? As per the question is concerned, over here, if you look carefully, KMnO4 is reacting with what? Potassium oxalate in acidic medium. I'm calling this as number 1, this I'm calling as number 2. N factor of KMnO4 in acidic medium is 5. N factor of this over here will be 2. You know it, already discussed. Now people, now, how many moles of KMnO4? How many moles of KMnO4 will be required to react completely with 1 mole of potassium oxalate? 1 mole of potassium oxalate. Perfect. Now tell me, since we are given with the data for moles, not millimoles. Moles means gram equivalence. If it was millimoles, then milli equivalence. I'll write the statement in terms of gram equivalence. I'll say gram equivalence of 1 has to be equal to gram equivalence of 2. Now, how many formulas do we have to calculate gram equivalence? One was mass wala result, second was moles wala result, third one was normality, right? I'll use moles wala result. Moles of 1 multiplied by n factor of 1 is equal to moles of 2 multiplied by n factor of 2. What is moles of 1? Needs to be calculated. This is 5. This is 1. This is 2. So N1 comes out to be directly 0.4. So I would say 0.4 moles of KMnO4 are required to react with 1 mole of potassium oxalate in acidic medium. Am I clear? Am I loud and clear, people? Am I loud and clear? Say it. Similar type of question. Similar type of question. Just relate the gram equivalence. You can do it. You can do it. N1 multiplied by n factor 1 is equal to this. Okay? Similar type of question. Similar type of question. Look at this one. Look at this one. 6 moles of a solution of An positive. The question is 6 moles of a solution of An positive. 6 moles of a solution of An positive. 6 moles of a solution of An positive. Requires 2 moles of Cr2O7 dinegative. Requires 2 moles of Cr2O7 dinegative for the oxidation of An positive to AO3 negative. For the oxidation of An positive to AO3 negative, and itself in acidic medium it gets converted into Cr tri positive. What do we have to calculate? Get the value of N. Get the value of this N. Look carefully, guys. These two are reacting. So equate their gram equivalence directly. First of all, what is the N factor of this An positive? Plus N to plus 5. Plus N to plus 5. Change. Change is final minus initial. Right? And we have got only one atom. What about the N factor of Cr2O7 dinegative? Plus 6 to plus 3. Change is 3. 3 is the change for one atom and 2. So 3 2s are 6. So equate the gram equivalence. Gram equivalence of first has to be equal to gram equivalence of second. So N1 multiplied by N factor 1 is equal to N2 multiplied by N factor 2. What is N1? 6. What is this? 5 minus N is equal to 2 multiplied by 6. 6 cancel. So N value comes out to be how much? N value comes out to be 3. What is this N? N was the charge present on A. So basically your A is present in a tri-positive state. Am I clear? Am I clear, people? Am I clear? Am I clear? Am I clear? Am I clear? Yes. Perfect. And that's all what can be asked from the redox. Okay. Is the redox reaction chapter clear? Is the redox reaction chapter clear? Which chapter do you want to start the next? Which chapter do you want to start the next? Which chapter do you want to start the next? Whatever chapter we are starting the next, that will take us 4 hours. Because now these are big chapters, right? That's why I told you I have kept 2 marathons for class 11th physical chemistry. By the way, do you think I'll listen to you? Yeah? I'm just making you happy by asking your suggestions, etc., etc. Huh? Do you really think? Do you really think I'll listen to you? Huh? Just tell me that. Huh? Are you that important? I'll ask you. Huh? What do we say? I'm the king of my own kingdom, right? Wait, let me see what majority asks. I'll create a poll here. You just tell me, okay? Then we'll start that chapter only after the break, but huh? Just a second. I'll create a poll. Just be like this. How to create a poll. Now I'm technologically unsound. I know that. Uh, just a second. Just a second. Start the poll. Which chapter next? Options. Atomic structure. Number 2 is thermodynamics. Number 3 is equilibrium. Poll has been started. Okay, you just fill it and let's take a break. After the break, I'll see what majority would have said and I'll go with that. Yeah, it is 3:40 right now. So break till. Have a good break. Okay, have some tea. Okay. So first, let's take a break. Ambika, she listens to you, huh? That's why I don't like her. She listens to everybody, right? She's not supposed to do that. Achha, chalo, I'll see you exactly at 4:15, huh? You can have your tea, you can freshen yourself. And then once we get back, I'll see what majority said and we can go ahead. Right? We can go ahead with what majority says. Chalo, guys. I'll see you after the break, huh? Take care. Take care, guys. See you. So, guys, is everyone back? Is everyone back? Yes. Poll results. Let me check the results of the poll. Just a second. Oh, it is a tie. 40% atomic structure, 40% thermodynamics. Huh? 40% atomic structure and 40% thermodynamics. So now which one to start? Quick. Quick. Say it in the chats, I'll do that. Say it in the chats, I'll do that. I think majority wants to start thermo, right? Okay. Thermodynamics. All right. Hello, then I'll listen to you only. All right. Chalo, I'll listen to you only. Let's start with thermo only. Yeah. Okay. So tell me once in the chats, like whatever things I discussed till now, is every single thing clear? Perfect, people. Perfect. All right, then let's go ahead with the thermodynamics. Let me check the slides once. Where is the thermodynamics? Where is the thermodynamics? Okay, here we have got the thermodynamics. Just a second. Just a second. Just a second. Just a second. Just a second, people. You can call up everyone till then. All right, can you let me know in the chats, like how many of you have studied thermodynamics before? Honestly, you can say yes or no. How many of you have studied thermodynamics before? Okay. Anyways, I'll be starting from the basics only. You need not to worry. You need not to worry. I'm just asking you. I'm just asking you. I'm just asking you. All right. Chalo then, let's get started. Let's get started, people. First of all, let's have a look on the basic terminologies which are involved in the chapter Thermodynamics. The basic terminologies which are involved in the chapter Thermodynamics. And I believe all of you would be already knowing the basic terminologies which involves your system, your surroundings, your boundary. Now, what is the meaning of all these particular things? Okay, what is the meaning of all these particular things? My dear students, if you look at this particular definition, system is basically that part of the universe which is under thermodynamic investigation. That part of the universe which is under thermodynamic investigation. What is meant by that? Just let me make you understand that quickly. For example, this is the container. Let's say this is the container. In this container, my dear students, for example, you have kept water. You have kept water inside this particular container. Okay, there is water in this particular container. For example, I have to raise the temperature of this water. Let's say I have to raise the temperature of this water by 1 degree centigrade. Let's say I have to increase the temperature of the water by 1 degree centigrade. What do I have to do? I have to supply heat. Okay, I have to supply heat to increase the temperature of this water by 1 degree centigrade. My dear students, for example, I have to do one investigation. Like how much heat is required. This is the investigation which I need to do. How much heat is required to raise the temperature of this water by 1 degree? Okay. I have to do one thermodynamic investigation related to this particular water which is there in the container. I have to check how much heat is required to raise the temperature of this water by 1 degree. Can I say this water which is inside this particular container right now, can I say this water is right now under thermodynamic investigation? Yes. This water right now is under thermodynamic investigation. Correct? That part of the universe which will be under thermodynamic investigation, what do you call that as? You call that a system. So this water which is there in the container, it is right now under thermodynamic investigation. So I'll be calling this water as my system. This is my system right now. This is the part of the universe. This water in the container is under investigation right now. I'm calling this as the system. My dear students, apart from this water, whatever is there in the universe, I'll be calling that as surrounding. Okay. And anything that separates system from the surroundings, that is something which you call as boundary. As you can see, these walls of the container, they are separating your system from the surroundings. So you'll be calling it as boundary. Right? So three terminologies: one is system, one is surrounding, one is boundary. That part of the universe which will be under thermodynamic investigation, that is your system. Anything in the universe except system, that is your surrounding. Anything that separates system from the surroundings, that is your boundary. Clear? Now, how many different types of boundaries do we have? My dear students, broadly speaking, I can say in this particular chapter, we are going to use these types of boundaries. Number one, real boundary. A real boundary is the one which can be seen by the eyes. That boundary which can be seen by the eyes. Imaginary boundary, it cannot be seen. By the eyes, right? Diathermic boundary, it is that boundary through which heat can pass, through which heat can flow, right? Okay? That boundary which allows the passage of heat. Either from system to surrounding or from surrounding to system. Adiabatic boundary, it does not allow the passage of heat. It does not allow the passage of heat, either from system to surroundings or from surrounding to system. Right? Perfect. Which does not allow the passage of heat either from system to surroundings or from surrounding to system. So one is real, which can be seen by the eyes. Imaginary cannot be seen. Diathermic is the one which allows the passage of heat either from system to surrounding or from surrounding to system. Adiabatic is the one which does not allow the passage of heat either from system to surroundings or from surrounding to system. Right? Now people, these are some basic things which I'm telling you. These are some basic things. I did not start the chapter yet. What are the types of the system which we have? What are the types of the system which we have? My dear students, we have got three types of system over here. One is called as open system, one is called as closed system, and one is called as isolated system. What is an open system, what is closed, and what is an isolated system? Let's have a look. Open system is the one which allows the exchange of energy as well as matter with the surroundings. Closed system is the one which allows only the exchange of energy with the surroundings, not the matter. And isolated system is the one which neither allows the exchange of energy nor the matter with the surroundings. Now, what does it mean? Let's try to understand. For example, I have got an open container. Let's say this container is open on one side. Okay. There is water in this particular container. H2O liquid. Perfect. This water is my system right now. It is under investigation. Imagine that the walls here are diathermic. That means through these walls, heat can pass. Heat can either go from system to surroundings or from surrounding to system. Heat can pass, right? Because I've used the walls as diathermic. Now, people, understand. If I supply some heat to this system, I'm supplying some heat to the system. Okay, I'm supplying heat to the system. Can I say between system and surroundings, exchange of energy is happening? Yes, exchange of energy is happening. Now, people, what is going to happen? When you supply heat to this water, what will happen? Evaporation will start. Water will start getting converted into vapors. Those vapors will go into the surroundings. Can I say between the system and surroundings, exchange of matter is also taking place? Whenever you see such kind of the system, which allows the exchange of energy as well as matter with the surroundings. That's what you call as an open system. Simple, right? Now, people, if you close this, will there be exchange of matter between system and surroundings? There won't be exchange of matter between system and surroundings. But exchange of energy will be there. Any such system which allows the exchange of energy, not the matter, with the surroundings, what do you call that as? You call that as the closed system. And any such system which neither allows exchange of energy nor the matter with the surroundings, you call that as isolated system. And the example of the perfectly isolated system is the universe. If you take entire universe under thermodynamic investigation, if you make entire universe as the system, then it becomes the example of the perfectly isolated system. Am I clear with this? This was just the basics. This was just the terminologies, right? Let's not talk about them in detail. The detailed discussion has to be for extensive and intensive properties. Over here, it needs a detailed discussion. So, people, what are extensive and what are intensive properties? Let me tell you, extensive properties are the ones whose value, changes on changing the size of the system. Or I can say whose value changes on changing the amount of substance present in the system. Whose value changes on changing the size of the system or the amount of substance in the system. Amount of substance present in the system. I'll write, otherwise intensive. Now, what is meant by all this? Try to understand, people, what exactly is meant by all this. Okay, try to understand. For example, this is a block. It's an iron block, for example. Let's say this, that it's an iron block. This iron block, imagine this iron block is under investigation right now. It is under thermodynamic investigation. So I should be calling this iron block as my system right now. So this is my system. This iron block is my system right now. Its mass is m, its volume is v, its temperature is T. Right? Mass of this iron block is m, volume is v, temperature is T. Now what exactly I'm going to do, I'll be dividing this iron block into two parts. I'll be dividing this iron block into two parts. Right? After dividing this iron block into two parts, if I take the smaller part, what will be the mass of this smaller part? Initially, the mass of whole iron block was m. Now it's going to be m by 2. Its volume will be v by 2. What about its temperature? Its temperature is still going to be T. Okay. So what am I doing? Am I changing the size of the system? Yes. Initially, this was the system. Now only this smaller part is the system. I changed the size of the system. Now, my dear students, if you look carefully, how many properties did I define for this system? I defined its mass, m, volume, v, temperature, T. When you changed the size of the system, mass of the system changed from m to m by 2. Volume of the system changed from v to v by 2. Temperature did not change. Those properties of the system whose value changes on changing the size of the system are what you call as extensive properties. And the ones whose value does not change, you call them as the intensive properties. So I defined three properties here. Out of these three properties, mass and volume, these are your extensive properties, and temperature is your intensive property. Right? Temperature is your intensive property. Are you guys clear with what are extensive and what are intensive properties quickly? Are you guys clear with this? Yes, are you clear with this? Perfect. Perfect, guys. Now, there are some examples of extensive and intensive properties which I would want you guys to remember. Directly questions are asked from these. Okay, these are the examples of some extensive properties, and over here I've mentioned some of the examples of the intensive properties. Perfect. From these examples, questions are asked. Now, there are few things which you need to know about extensive and intensive properties. Few important things. Number one, if I talk about extensive properties are additive in nature. Extensive properties are additive in nature. Are additive. Intensive properties are non-additive. What does that mean? Extensive properties, you can add or subtract extensive properties directly. You can add or subtract extensive properties directly, but you cannot add or subtract intensive properties directly. What does that mean? Extensive properties are additive, whereas intensive properties are non-additive. Intensive properties are non-additive. What it means? Let's try to understand this. Let's try to analyze this. For example, this is a container. This is one more container. Okay. My dear students, this container is filled with water. Even this container is filled with water. Okay. Imagine its mass is m, volume is v, temperature T. Mass is m, volume is v, temperature is T of the water present in the container. Right. Now, what am I going to do? I'm going to add them up. And put it here in the final container. I'm just going to mix them up in the final container. So this particular final container will be containing water. If I ask you, what is the mass of water present in the final container? This was m, this was m, this will be 2m now. What is the volume of this water now? V plus V makes it 2V. But if I ask you what is the temperature of this water? It is simple, guys. You have one glass of water at temperature 25 degrees centigrade. One more glass of water at temperature 25 degrees centigrade. You're mixing them in a bucket, in a bigger bucket, right? So what will be the temperature of the resultant water? It will be 25 only. So temperature of the water inside the container right now will be T also. How many properties I defined for the system? 3. Mass, volume, temperature. Out of these 3 properties, these 2 are extensive. And if you look carefully, when I added them up, m plus m made it 2m. V plus V made it 2V, but T plus T did not make it 2T. So can I say over here, extensive properties are being directly added, but intensive properties are not, right? So can I say intensive properties are non-additive? If intensive properties were additive, then temperature of this water should be 2T, but it's T only. This is first point. Extensive properties are additive in nature, whereas intensive properties are non-additive in nature. Number one. Number two. Division of two extensive properties. Division of two extensive properties. Division of two extensive properties makes the new property as intensive. Makes the new property as intensive. Makes the new property as intensive. What does it mean? For example, you have got, I'm defining two things, X and Y. Let's say this X is your extensive property. Let's say your Y is also your extensive property. Perfect. X and Y. Imagine these are two extensive properties. For example, I'm dividing these two extensive properties. After dividing these two extensive properties, I'm getting one more property, Z. When you divide two extensive properties, the new property which comes into play, that will be intensive in nature. That will be intensive in nature. For example, M stands for mass, V stands for volume. Mass is extensive, volume is extensive. Mass by volume is what you call as density. Density you'll be calling as intensive. Density you'll be calling as intensive, as simple as that. Right? So, division of two extensive properties makes the new property as intensive. Yeah, makes the new property as intensive. Okay, third point, which is again important. My dear students, an extensive property, let me write it in short form. If X is an extensive property, if you express this extensive property per unit mole, per unit mass, or per unit volume, right? If you express this extensive property either per unit moles, per unit mass, or per unit volume, the new property that comes into play, that automatically becomes intensive. For example, there is a term which we have to define in some time. Heat capacity, which is represented by C. Heat capacity, which is represented by C, it is an extensive property. If you express this per unit mass, it becomes specific heat capacity. Specific heat capacity is intensive in nature. It is intensive in nature. Heat capacity, which is extensive, if you define it per unit mole, it becomes molar heat capacity. Molar heat capacity is intensive. So remember, in short, whenever an extensive property is expressed either per unit mass, per unit mole, or per unit volume, the new property that arises, that is your intensive property. That becomes your intensive property. Am I clear with this? Am I clear with what are extensive and what are intensive properties? I hope I'm clear. I hope I'm clear. All of you. Say yes or no in the chats quickly. Yes? All clear? Perfect. Now people, now understand. Now understand. There is something called as state functions and path functions. State functions. What are state functions? What are state functions exactly? Right? From this also a question is asked. State functions. State functions are the ones which only depends on initial and final state of the system. Which only depends on initial and final state of the system. Initial and final state of the system. They only depend on initial and final state of the system. They are path independent. They are path independent. They are path independent. On the opposite side, if I define path function, what is the path function? What's the path function? First of all, path function also depends on initial and final. It also depends on initial and final position, initial and final state of the system. But at the same time, it's path dependent. It is path dependent. These are path dependent. These are path dependent, right? What are the examples of the state functions? Your pressure, volume, temperature, internal energy, enthalpy, entropy, Gibbs free energy. These are all your state functions. These are all your state functions. These are all your state functions. What about the path functions? Heat and work. Heat and work. These are the examples of your path functions. These are the examples of your path functions. These are the examples of your path functions. Heat and work. Yes, heat and work are the examples of your path function. My dear students, how can you remember what is state function, what is path function? You can relate it with one simple thing. You can relate it with one simple thing. For example, you're at point A and you want to go to point B. From A to B. You want to go from A to B. How many paths are available in order to go from A to B? I can choose infinite paths. This is one of the path. And this is, for example, one more path which I've chosen to go from A to B. This particular one I'll be calling as, you know it, displacement. This is what? Distance. Now tell me, displacement only depends on initial and final state. It's path independent. So you can relate it with your state function. Distance, it is path dependent. You can relate it with your path function. You can relate it with your path function. Yeah? You got it? There are two things which I would want you guys to know about state functions and path functions. Remember them properly. Remember them, guys. For example, A is the state function. A is a state function. B is a path function. A is a state function, B is a path function. Understand what I'm going to say. A is a state function, B is a path function. Okay. If I multiply this A by D, it becomes DA. And this becomes DB. I just multiplied A as well as B, B with D, right? DA, DB. What is this DA? DA is what I call as small change in A. DA is what I call as small change in A. DB, I won't be calling this a small change in B. This is what we'll be calling as small amount of B. This is what we'll be calling as small amount of B. If I integrate this dA and if I integrate this dB, what do we get? What do we get? Integral of small change gives you the large change. I'll be either calling it as large change in A or total change in A. Integral of small amount gives you total amount. It is total amount of B. Small amount, total amount. Integral of dB. Integral of dA over here I'll be representing with delta A. But integral of dB I'll be representing simply with capital B. Remember these two things. These are important. For example, one term which we have to discuss in some time, that is internal energy. Internal energy is the example of what? It is the example of a state function. Okay? It is the example of the state function. For example, Q, heat. Heat is the example of what? It is the example of a path function. It is the example of the path function. Correct? My dear students, if you multiply this U with D, and over here also you write dq. What is the meaning of both these? What is the meaning of these two terms? du and dq. What is du? du is basically small change in internal energy. du is basically small change in internal energy. What is dq? dq, I won't be calling a small change in heat. That does not make any sense. This is small amount of heat. This is small amount of heat. Now people, if you integrate them, if you integrate this one, if you integrate du as well as dq, if you integrate both of them, over here, this becomes delta U and this becomes normal Q. This delta U is what I call as total change in internal energy or large change in internal energy. This is total change in internal energy. This is what you call as small amount integral is total amount of heat. This is total amount of heat. Are these two things clear to you? Are these two things clear to you, people? Yes? Clear, people? I hope these two basic things are absolutely clear to you. Right? Perfect. Now comes one more term. That is state variables. State variables, or you call them as state parameters. What are state parameters or state variables? What are state parameters or state variables? Let me tell you, these are the variables which defines. These are the variables which defines the state of the system. These are the variables which actually defines the state of the system. These are the variables which actually defines the state of the system. State of the system. What does that mean? Before that, before letting you know the meaning of this particular statement, I'm going to write one more. On changing the state parameters, in the bracket I'm writing minimum 1. On changing the state parameters, minimum 1. On changing the state parameters, the state of the system automatically changes. The state of the system automatically changes. Let's try to understand what these state parameters exactly are. My dear students, for example, here we have got a container. Okay, here we have got a container. In this container, let's say you have got an ideal gas. This is the ideal gas in the container. Okay, let's say the pressure of ideal gas is P1, volume of this ideal gas is V1, temperature of this ideal gas is T1, right? Moles are N1. Perfect. Right? The ideal gas which is in the container whose pressure is P1, volume is V1, temperature is T1, moles are N1. I can say this ideal gas, for example, is present at its initial state. These are basically the parameters, these are the variables which are letting you know whether the system is at initial state, whether the system is at final state, whether the system is at intermediate state or whatever. So basically these are the parameters which actually defines the state of the system. These parameters exactly let you know, right, what is the state of the system. Okay, now people, remember, whenever you want to change the state of the system, what do you have to do? You just have to change the value of these state parameters. In order to change the state of the system, if you want this system to go from initial state to final state, what do you have to do? If you want to change the state of the system, you just have to change the value of state parameters. Minimum, if you change only one state parameter, the state of the system automatically changes. For example, if I just change pressure, rest everything I keep same. If I just change the pressure from P1 to P2, rest everything I'm keeping same. I'll say the state of the system has automatically changed. So remember, whenever you want to change the state of the system, you have to change the value of state parameters. Minimum, if you change one state parameter, the state of the system automatically changes. Okay? Am I clear? Now, let's move on. My dear students, there's a term called as thermodynamic process. I'm just giving you the introduction of the things first. Thermodynamic process. How do we define the thermodynamic process? What is a thermodynamic process? First of all, how do you define the thermodynamic process? It is simply defined as the path followed. To change the state of the system. It is the path followed to change the state of the system. Now, what that means? Try to understand. This is important. And I'm just giving you the introduction of the things. I did not go into the details yet. Details I'll let you know in some time. First of all, you have to understand the overall scenario, like what all things are to be discussed in this chapter. Okay? See guys, for example, we have got a gas in the container. Okay? Let's say the pressure of this gas is P1, volume is V1, temperature is T1, moles are N1. For example, I'm assuming that this system is present at its initial state. Now, my dear students, what exactly am I going to do? I am going to change the state of the system. How do we change the state of the system? By changing the value of state parameters. Right? By changing the value of state parameters. Let's say the final state parameters of the system are P1, V2, T2, and N2. What did I do? People? What did I do? We changed the state of the system. How exactly? We changed the value of state parameters. Since we changed the state parameter value, automatically the state of the system will automatically change. Now you tell me one thing. No doubt, I changed the state of the system, but if you notice one thing, pressure of the gas here was P1. Here also the pressure of the gas is P1. No doubt, I changed the state of the gas. I changed the state of the system. But during the change in the state of the system, I made sure that pressure of the system does not change. Pressure of the gas does not change. No doubt, I changed the state of the gas by keeping its pressure constant. I changed the pressure of the gas. I changed the pressure of the system by keeping the pressure of system. I changed the state of the gas by keeping its pressure constant. I could have changed the state of the system by keeping its volume constant as well. I could have changed the state of the system by keeping its temperature constant as well. So can I basically say there are a lot of paths available, right, to change the state of the system? You can change the state of the system by keeping the pressure of the system constant. You can change the state of the system by keeping volume constant. You can change the state of the system by keeping temperature constant, etc., etc. So there are a lot of paths available to change the state of the system. And the path followed, among these paths, which path you are following to change the state of the system, that's what you call as thermodynamic process. So what is a thermodynamic process? It is a path followed to change the state of the system. Right? It is a path followed to change the state of the system. I hope I'm clear. So over here, first of all, I'm writing isochoric process. Isochoric process. What is an isochoric process? Tell me quickly. What is an isochoric process? When do I say? Okay, first of all, let me tell you one more thing. From now onwards, whenever I use the term system, understand, I've taken a container. In that container, I've kept the ideal gas, and that ideal gas is under investigation. That ideal gas is my system. So from now onwards, whenever I say system, understand, I'm talking about the ideal gas which is there in the container. Okay? Understand, I'm talking about the ideal gas which is there in the container. Perfect? Now, for example, I'm saying that the ideal gas is undergoing isochoric process. What does that mean? That means we are changing the state of the system, but we are making sure during the change in the state, volume of the system is remaining constant. We are not going to let the volume of the system to change. No doubt, we are changing the state, but during the change in the state, we are not letting the volume of the system to change. Okay? Perfect? During isochoric process, volume of the system does not change. If volume of the system does not change, delta V, change in volume, will be zero. Change in volume will be zero. For example, I have to plot a graph. I have to plot a graph between pressure of the gas versus volume of the gas. How the graph will look like? Since volume is not supposed to change, it has to be a straight line. And this particular straight line, I'll be calling as isochore. This is something which I'll be calling as isochore. Right? Isochore. Perfect. Now, similarly, guys, I'm using the term isobaric process. What is meant by isobaric process? In isobaric process, when the ideal gas undergoes isobaric process, I'll say pressure of the gas remains unchanged. Pressure does not change. So change in pressure, delta P, it will be 0. Delta P will be 0, right? Delta P will be 0. I'm plotting the graph between pressure and volume. I'm plotting the graph between pressure and volume. The graph is like this. And you call this as isobar. You call it as isobar. Simple. Right? Similarly, guys, if I talk about isothermal processes, I'm just giving the introduction of the things. Isothermal process. What is an isothermal process? When do we say that ideal gas is undergoing isothermal process? Whenever ideal gas undergoes a change in state, but during the change in state, temperature of the gas does not change. If temperature of the system does not change, we say the gas is undergoing isothermal process. Right? Temperature constant. If temperature is constant, delta T is 0. Delta T is 0. Change in temperature is 0. Okay? For an isothermal process, delta T will be 0. Right? If you would have studied the gas laws, which gas law used to be there in which we used to keep the temperature of the ideal gas constant? I hope you remember that was your Boyle's law. Right? Perfect. So the ideal gas whose temperature is kept constant, the ideal gas whose temperature is kept constant, can I say this gas whose temperature is kept constant? It will be following the Boyle's law, right? PV is equal to constant. PV is equal to constant. This is what I'll be calling as equation of state for isothermal processes. This is what I'll be calling as equation of state for isothermal process. Equation of state for isothermal process. Right? Now, people, if I want to plot a graph between pressure and volume for the ideal gas, which is undergoing isothermal process, you can write P is equal to K by V. You can write P is equal to K by V. Pressure and volume here are inversely proportional to each other. And you know, whenever we need to plot a curve between two variables which are inversely proportional to each other, the nature of the curve is hyperbola, right? This curve is something which we call as isotherm. This is something which we call as isotherm. Perfect. If you look at the first process, isochoric, ideal gas is kept at constant volume. Ideal gas is kept at constant volume. Ideal gas is kept at constant pressure. Ideal gas is kept at constant temperature. Perfect. Perfect, guys. Now, there is one more process which we have to discuss. All these things we have to discuss in detail, by the way. Okay. There is one more process that's called as adiabatic process. When do we say that ideal gas is undergoing adiabatic process? Yeah, just tell me that. Whenever an ideal gas undergoes a change in state, but during the change in state, if there is no heat exchange between system and surroundings, during the change in the state, if there is no heat exchange between the system and surroundings, then and only we say that your ideal gas is undergoing adiabatic process. Perfect. Now, what is the equation of state in case of adiabatic process? PV raised power gamma is equal to constant. This is basically the equation of state for reversible adiabatic. That's something which I'll explain you after some time when I'll discuss reversible, irreversible process with you. Okay, this is the equation of state. The way PV is equal to K was the equation of state for isothermal. Similarly, this is the equation of state for adiabatic, right? Reversible adiabatic. Over here, if you want to plot a graph between pressure and volume, okay, you know, P is equal to K divided by V raised power gamma. Pressure and volume, again, they are inversely proportional. And whenever you have got two variables which are inversely proportional to each other, the nature of the curve is your rectangular hyperbola. Okay? And this curve is something which we call as adiabat. This curve is what we call as adiabat. My dear students, if you look carefully, over here you got the hyperbola. In this case also you got the hyperbola. In isotherm, hyperbola, right? In your adiabatic curve, you got hyperbola. Now, how do you identify? How do you check whether the hyperbola is adiabatic or isotherm? How do we check that? One simple trick I would want you to remember, that's all. Let's say this pressure, this is volume, okay? This is, for example, one hyperbola, This is the second one. These are the two hyperbolas that are given to me. Okay. I'm keeping the arrow towards right. I'm keeping the arrow towards right. I'm keeping the arrow towards right. Towards right, volume is increasing. Towards right, volume is increasing. Right? Volume is increasing. Increase in the volume is what you call as expansion. So both these graphs, they represent what? Expansion. They represent expansion. Now, which graph is for isothermal? Which graph is for adiabatic? What do we do? What do we do? Simple. This is the common point. This is our common point. I'll place my thumb at the common point. I'll place the thumb at the common point. Curl your fingers in a clockwise direction. That curve which touches the fingers first, that's always isothermal. So this is isothermal. This is isothermal. So automatically this becomes adiabatic. Right? Perfect. Similarly, guys, let's say I would have curve like this. This is pressure and this is volume. Pressure versus volume. Okay? Pressure versus volume. I'm starting from here. Let's say this one hyperbola. This is one more hyperbola. Arrow towards left. Arrow towards left. Towards left, volume is decreasing. Decrease in the volume is something which we call as compression, and both these curves, they represent compression. Both these curves, they represent compression. Okay? Now, place your thumb at the common point. Curl your fingers in the clockwise direction. That curve which touches your fingers first, that's your isothermal. So this is your isothermal. And this is your adiabatic. I hope you got to know how do we check whether the curve is adiabatic or isothermal. Am I clear? Am I clear, people? Am I clear? Am I clear? One more. See, guys, I'm not teaching you all this stuff in detail right now. In detail, I'll be doing it after some time. I'm just giving you the overview of the things. I'm just giving you the overview of the things. Okay? I'm giving you overview of the things. There is one more process which we have to discuss in detail after some time. That's what you call a cyclic process. What happens in cyclic process? What happens in cyclic process? In cyclic process, I would say, system returns to its initial state. System returns to its initial state after going through a lot of steps. System returns to its initial state after going through a lot of steps. System returns to its initial state after going through a lot of steps. For example, let's say this pressure, this volume. Let's say we are starting from point A. From point A, we are going towards point B. From point B, we are going towards point C. And then from C, again, we are coming to A. Right? We started from A, we started from A, and we reached A. Can I say the initial state and the final state of the system is same? Right? Can I say the initial state and the final state of the system is same? Can I say system is returning to its initial state after going through a lot of steps? Whenever you see such kind of the process in which system returns to its initial state after going through a lot of steps, you call that particular process cyclic process. So this is a cyclic process. This is a cyclic process. If it is a cyclic process in which systems initial state and final state are same, can I say change in the value of a state function? Change in the value of a state function for a cyclic process will be 0. Right? Change in the value of a state function for a cyclic process, that has to be 0. Because initial state, final state are same. And what are state functions? They only depend on initial and final state. If initial final state is same, that means the value of state function will be also same. Initial value of state function and final value of state function will be the same. If initial value of the state function, final value of the state function is same, that means change in the value of a state function, that has to be 0. So do remember, in case of cyclic process, change in the value of a state function, that's always 0. So your delta U, your delta H, your delta S, your delta G, all these terms for the overall cyclic process, they're always what? They're always 0. Am I clear with this? Am I clear with this, people? So change in the value of a state function for a cyclic process, that's always taken as 0. Yes? Perfect. Now, let's move on. Let's move on to a few more things. Let's move on to a few more things. Let's move on to a few more things. Okay? My dear students, if you ask me what is heat, how do you define the term heat? How do you define the term heat? How do you define the term heat? Let me tell you first of all, heat is defined as the mode of. Heat is defined as the mode of transfer of energy. Heat is defined as the mode of transfer of energy between the system and surrounding. It is defined as the mode of transfer of energy between system and surroundings. What does it mean? My dear students, whenever energy has to be exchanged between system and surroundings, whenever energy has to be exchanged, whenever the energy has to be transferred, either from system to surrounding or from surrounding to system, whenever energy has to be transferred, either from system to surroundings or from surrounding to system, this transfer of energy can happen via heat. So heat is nothing but the mode of transfer of energy. Heat is nothing but, it is the mode of transfer of energy. It is the mode of transfer of energy. And you know, heat always flows due to temperature difference. Heat always flows due to temperature difference. Right? Whenever there will be difference in the temperature between system and surroundings, then only heat will flow. And heat always flows from higher temperature to lower temperature. It flows from higher temperature to lower temperature. It flows from higher temperature to lower temperature. Now, people, here two things you have to remember. Two things you have to remember. That is the sign convention. That is the sign convention. Okay. Remember, whenever heat is absorbed by the system, when heat is absorbed by the system, when heat is absorbed by the system, at that point of time, Q value is taken as positive. Q value is taken as positive. And if heat is released, when heat is released by the system, Q value is taken as negative. Q value is taken as negative. Q value is taken as negative. For example, let's say this is the container which I have, and in this container I have got the ideal gas, which is my system. Perfect. Let's say the system is at temperature T1. Let's say the system is at temperature T1. Outside surrounding is at temperature T2. Surrounding is at temperature T2. My dear students, if, for example, if T2 is greater than T1, if T2 is greater than T1, can I say there is temperature difference between system surroundings? So heat will automatically flow. Heat will flow from higher temperature to lower temperature. Right now, surrounding is at higher temperature and system is at lower temperature. So heat will flow from surrounding to system. If heat is flowing from surrounding to system, what does that mean? That means system is absorbing heat. That means system is absorbing heat. And when heat is absorbed by the system, Q value is taken to be positive. Right? Q value is taken to be positive. Perfect. Similarly, if, for example, T1 is greater than T2, if system is at higher temperature, surrounding at lower temperature, heat will flow from system to surroundings. At that time, can I say heat is released by the system? And when heat is released by the system, Q value is taken to be negative. These are just few things which you need to remember about what? About heat. Am I clear? Am I clear, people? Am I clear? Yeah? Say it in the chats quickly. Am I clear? Perfect. Now comes one more term. What is that? That is work. That is work. And already we know what is heat. Is it a state function or path function? You know that. Heat is a path function. Yeah? Heat is a path function. Now, if I talk about work, which is denoted by W. If I talk about work, which is denoted by W, how do we define work? Work is again, the mode of transfer of energy. It is again the mode of transfer of energy between the system and surroundings. If energy has to be transferred either from system to surrounding or from surrounding to system, the transference of energy can happen via work as well. So work is again the mode of transfer of energy between system and surroundings. Mode of transfer of energy between system and surroundings. And already we know work. What is it? It is a path function. Work, it is a path function. It is a path function. Now guys, try to understand. Try to understand what exactly I'm going to say. For example, this is a container. This is a container, okay? Over here, it is the piston which is frictionless, massless, whatever, okay? And here, I have kept an ideal gas. This is the ideal gas in the container. Let's say the piston is right now at point A. When the piston is at point A, let's say volume of this gas right now is V1. Volume of the gas right now is V1. Okay. My dear students, if I ask you on this piston, how many pressures are exerted on this piston? These internal gas molecules will be colliding with the piston. So in this direction, there will be pressure of gas. In this direction, there will be pressure of gas. Similarly, outside, there is atmosphere. Those atmospheric gas molecules will be also colliding from outside. So this is your P external. So on the piston, two pressures are acting. Pressure of the gas, P external, right? Now, case one. My dear students, tell me, if P gas is greater than P external, if P gas is greater than P external, will the piston go inside or piston go outside? Piston will go outside. Let's say the piston went outside and stopped somewhere here, right? Where the volume is V2. Let's say pistons stopped here. When piston is going outwards, what is happening to the volume of the container? Volume of the container is increasing. If volume of the container is increasing, that means volume of the gas is increasing. If volume of the container is increasing, that means volume of the gas is increasing. So if P gas is greater than P external, can I say at that point of time V2 is greater than V1? What is happening to the volume of the gas? Volume of the gas is increasing. Increase in the volume of the gas is what we call as expansion. Increase in the volume of the system is what we call as expansion. Whenever there is expansion, we always say work is done by the system. Whenever there is expansion, we always say work is done by the system. And let me tell you, whenever work is done by the system, W value, as per sign convention, in chemistry, is taken to be negative. W value is taken to be negative. In what? In chemistry, not in physics. Okay? Remember these points. These are super important. Okay? I hope I'm clear. This was point number one. Point number two here. If P external is greater than P gas, if P external was greater than P gas, if P external was greater, can I say at that point of time, final volume will be less than initial volume? Right? So what is happening? Decrease in the volume of the gas is happening. Decrease in the volume of the system is happening. Decrease in the volume of the system is what you call as compression. And whenever there is compression, we always say work is done. On the system. And whenever work is done on the system, W value, as per sign convention, is taken as positive. Right? Is taken as positive. This was case number two. Case number three, I'm writing here. Tell me. If P gas was equal to P external, if P gas and P external were equal, what would have happened? Will there be any movement of the piston? No. If there is zero movement of the piston, that means transfer of energy between system and surroundings is not happening in the form of work. That means transfer of energy is not happening in the form of work, right? If P gas is equal to P external, work at that point of time is equal to zero. Am I clear? Am I clear, people? Okay, guys? So basically remember one thing. Whenever you see piston moving, going outwards or inwards, remember at that point of time between system and surroundings, energy is transferred in the form of work, right? Except in case of free expansion. That I'll teach you separately. Whenever you see piston moving, either going outwards or inwards, what is happening at that point of time? Exchange of energy between system and surroundings is happening in the form of work, except in case of free expansion. Free expansion will be discussed later on. Okay? Now, my dear students, how do we calculate? How do we calculate this work done? How do we calculate this work done? I'm not deriving the result, I'll just give you the result. W is equal to minus integral P external dV from V1 to V2. From V1 to V2. This is the formula by means of which we calculate work. This is the formula by means of which we calculate work. Okay? Minus integral V1 to V2 P external dV. My dear students, here only we have to define two processes, which I'll be defining in some time. But right now I want you just to remember them. I just want you to remember them. There are two processes. One is called as a reversible process. And one is called as irreversible process. What are reversible, irreversible process? You will get the idea in some time. Right now, you just remember things. In case of reversible processes, what you will observe pressure of the gas and P external. They'll be almost equal. And if P gas and P external will be always equal, that means W reversible is equal to minus integral V1 to V2. Instead of P external, we are going to write P gas multiplied by dV. This is the result which is used to calculate work done in case of reversible processes. This is the result which is used to calculate work done in case of reversible processes. Now, similarly, in case of irreversible processes, what you will observe, you will find external pressure as constant. Why is that? You will get the idea in some time. Okay, just remember things first of all. External pressure will be constant. If external pressure is constant, P external will come out. Integral of dV is V, upper limit, lower limit. So, at that point of time, W irreversible will be minus P external, V2 minus V1. That means minus P external delta V. So these are the two general results which you need to remember in order to calculate work. One for reversible process, one for irreversible process. One for reversible process and one for irreversible process. One for reversible process, one for irreversible process. Yeah? Perfect, guys? Am I clear with this? Am I clear with this? Am I clear with this? Just remember the units of energy. This is something which we shall be frequently using. You know, the SI unit of energy, that is joule. TGS unit of energy, that's erg. 1 joule is equal to 10 raised per 7 ergs. Other units of energy which we shall be using in this chapter, one is ATM liter, one is bar liter, one is calories. Remember, 1 ATM liter is 101.3 joules. 1 bar liter is 100 joules. 1 calorie is 4.2 joules. 1 ATM liter is 24.2 calories. These conversions are important. You have to remember them. Right? And I'll be using them in some time. Okay, these conversions are really important, guys. You need to remember them. Okay? Perfect. So can you solve one simple question here? This question I gave you yesterday in that small video. I gave you one video yesterday. I don't know whether you have watched that video or not. One small video I gave you yesterday. Yeah? Look at this particular question. My dear students, if you look at the first reaction, see, first of all these processes are happening at STP. STP means pressure, temperature, constant. So all these processes are happening while pressure and temperature is kept constant. Pressure, temperature is kept constant. Now, look at the first process. 4 times NH3 gas plus 7 times O2 gas. It gives 4 times NO2 gas plus 6 times H2O gas. This is the process, which is carried out at constant pressure temperature. Okay, which is carried out at constant pressure temperature. My dear students, have you heard about this equation PV is equal to nRT? Right? Since pressure temperature is constant, R is already constant. Can I say volume is directly proportional to moles? Absolutely. Volume is directly proportional to moles. So, if moles increase, volume will increase. If moles decrease, volume will decrease. Right? You know this. You know this. Now, if I ask you on the reactant side, how many gaseous moles do we have? 7 plus 4 is 11. On reactant side, we have got 11 gaseous moles. On product side, 6 plus 4, 10 gaseous moles. So when this process is happening, are moles increasing or decreasing? Moles are decreasing. Moles are decreasing. And you know, if moles decrease, volume will automatically decrease. Decrease in the volume is what you call as compression. Decrease in the volume is what you call as compression. Whenever there is compression, work is done on the system. Work is done on the system and W value is taken to be positive. That's what we had to check. Work is done on the system and W value is positive. Look at the second case. Gas, liquid. On reactant side, you have got gases. On product side, you have got liquid. On reactant side, you have got gases. On product side, you have got liquid. So gases are getting converted into liquid. You know, gas molecules are far, liquid molecules are close, right? So gas is getting converted into liquid. So that means molecules are coming close. What is that? What does that mean? Expansion or compression? Compression. Whenever there is compression, work is done on the system. Whenever work is done on the system, W value is again taken to be positive. Right? W value is taken to be positive. Look at the next one. Or leave the third one aside. Look at the fourth one. Solid is getting converted into gas. Solid is getting converted into gas. That means molecules are going far. Expansion is happening. Whenever there is expansion, work is done by the system. W value is taken to be negative. Look at the third one. Solid is getting converted into liquid, but it is ice basically. It is H2O solid. Ice is getting converted into liquid water. Ice is getting converted into liquid water. It's a special case, guys. Ice is getting converted into liquid water. Normally, if you think solid is getting converted into liquid, so it has to be the case of expansion, right? It has to be the case of expansion. But in case of ice, due to the special structure of ice, volume of ice is more than that of volume of liquid water, right? Volume of ice is more due to the special cage-like structure. Volume of ice is more than that of volume of liquid water. So when this process is happening, decrease in the volume is happening. Decrease in the volume is what you call as compression. Whenever there is compression, work is done on the system. W value is taken to be positive. W is positive here also. Am I clear? Am I clear with all these questions, people? Am I clear with all these questions? Am I clear with all these questions? Okay, one simple and basic question. Let me give you. Let me see if you can solve this or not. One simple and basic question. The question is, calculate the work done. Calculate the work done in joules. When an ideal gas undergoes an expansion from 10 raised power minus 3 decimeter cube to 10 raised power minus 1 decimeter cube against a constant external pressure of 10 raised power minus 5 Newton per meter square. Can you solve this question? It's a very simple and basic question. It's a formula-based one. It is a formula-based question. Can you solve this? Can you solve this, people? Quickly. Done? Done, guys? Is it done? First of all, tell me, we have to calculate work. How many expressions I gave you till now? 2 expressions. One was for reversible, another one for irreversible. Right? In reversible, I told you P gas and P external, they're almost equal. In irreversible, I told you P external is constant. Here, it is mentioned that external pressure is constant. External pressure is constant. So, I'll be considering this process to be irreversible. So, which formula I'll be using? W irreversible. W irreversible is nothing but minus P external, V2 minus V1, right? So, minus, what is P external? 10 raised power minus 5 Newton per meter square. What is V2? What is V2? Final volume. Final volume is 10 raised power minus 1. What is initial volume? 10 raised power minus 3, right? I've taken pressure as per SI system, right? Sorry, this is not decimeter cube. Let me just change the units. Meter cube, okay? Write it directly as meter cube. 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube, okay? Pressure I have taken as per SI system. Volume also I took as per SI system. That means the value of W which will be getting at the end, that will be also as per SI system, right? So it's minus 10 raised power minus 5 as such, okay? If I take 10 raised power 3 as common here, if I take 10 raised power 3 as common, it becomes 10 raised power minus 1 divided by 10 raised power minus 3, minus 1, correct? So since I've taken 10 raised power minus 3 common, so this becomes minus 10 raised power minus 8. Okay, this 10 raised power minus 3 goes up, so it is 100 minus 1, 99. So 99 into 10 raised power minus 8 joules. This is the value of W. Is that clear? Is that clear, people? Is that clear? Quickly let me know in the chats. Only bit of calculation here, nothing else. Did you get the same answer? Did you get the same answer, say it? Perfect, guys. Perfect. Now, before talking about internal energy and first law of thermodynamics, etc., etc. Before talking about that stuff, there are a few more things which you need to remember. I'm not going into the details of those things, but I want you guys to remember. I want you guys to remember them. Okay, I want you guys to remember them. My dear students, there is a term called as heat capacity. Heat capacity. Heat capacity is represented by what? It is represented by C. Heat capacity is represented by C. How do you define heat capacity? How do you define heat capacity? Heat capacity is simply defined as the amount of heat which is required to raise the temperature of a given mass of the substance by 1 degree, right? It is basically the amount of heat which is required to raise the temperature of a substance by 1 degree. The amount of heat which is required to raise the temperature of the substance by 1 degree. For example, understand. For example, this is object, it's a block, it's an object, right? It's an object. Let's say I have to increase the temperature of this object by 1 degree. I'll have to supply heat. The amount of heat which I have to supply, the amount of heat which is required to raise the temperature of this object by 1 degree, that is something which I'll be calling as heat capacity. That is something which I'll be calling as heat capacity. Now people try to understand. For example, in order to increase the temperature of this object by dT units, heat required was dQ. Let's say in order to raise the temperature of this particular object by dT units, right? Heat required was dQ. I'll say something like this. In order to raise the temperature by dT units, heat required is how much? Heat required is dQ. Heat required is dQ. This is something which I'm assuming. In order to raise the temperature of this object by dT, heat required is dQ. If I use the unitary method, in order to raise the temperature by 1 unit, how much heat is required? Heat required is equal to dQ upon dt. So what is this dQ upon dt? This is the amount of heat which is required to raise the temperature of that substance by 1 degree. And the amount of heat which is required to raise the temperature of the substance by 1 degree, that's called as heat capacity. So heat capacity C is equal to dQ upon dt. Right? Heat capacity C is equal to dQ upon dt. Perfect. Now guys, you can make its units as well. Over here in the numerator, it's heat, right? So joules per Kelvin, joules per degree centigrade, calories per Kelvin, calories per degree centigrade, whatever. Correct? Okay. A lot of units you can make over here. One thing which I already told you, heat capacity, is the example of extensive or intensive property. It is the example of extensive property. It is an example of extensive property. Now people, one thing which we have to realize over here, we got to know C is equal to dQ upon dt. So from this I can make a result. dQ is equal to C dt. If I integrate under the limits T1 to T2, over here I'll get a result Q is equal to C delta T, which is T2 minus T1. This result we'll use in the questions. Q is equal to C delta T. Where do I use? Where do I use this particular equation? Where do I use this particular equation? For example, my dear students, I'll tell you where do we use this particular equation. For example, this is the object that's given to me. Its heat capacity is given. Its heat capacity is given something, right? 10 joules per Kelvin, whatever, 50 joules per Kelvin, whatever. Heat capacity is given. Now, people, I want to increase the temperature of this object from 10 degree to 100 degree. I want to increase the temperature of this object whose heat capacity is given from 10 degree to 100 degree. I want to check how much total heat is required. How much total heat is required to raise the temperature of this object from 10 degree to 100 degree if its heat capacity is given. So this formula I'll use, C delta T, C T2 minus T1, right? Perfect. Now similarly, there is one more terminology, that is molar heat capacity. Have you heard? Or leave the molar heat capacity aside. Specific heat capacity. Specific heat capacity, which is represented by S. Specific heat capacity, which is represented by S. How do you define the specific heat capacity? Specific heat capacity is defined as heat capacity per unit mass of the substance. And C, you already know that is dQ upon dt. So it is dQ upon mdt. dQ upon mdt. Perfect. dQ upon mdt. Or you can make the result over here. dQ is equal to ms dt. Or if you integrate this equation under the limits T1 to T2, integral of dQ is Q, it becomes ms delta T, T2 minus T1. This is one more result to calculate the heat. This is one more result to calculate the heat. This is one more result to calculate the heat. Let me tell you the specific heat capacity, it is the intensive property. I hope you know. I've already told you whenever an extensive property is expressed per unit mass, extensive property expressed per unit mass becomes intensive. It becomes intensive. Yeah? Right, people? I hope I'm clear till here. I hope I'm clear till here. So this is one more way of calculating Q. We already know one formula to calculate Q. Q is equal to C delta T. If heat capacity of the object is given, then C delta T. If specific heat capacity is given, then MS delta T. Then this is the formula I'll use. Okay. Now we have got molar heat capacity. Now we have got molar heat capacity, which is represented by S. Sorry, which is represented by Cm. Molar heat capacity. How do you define molar heat capacity? It is defined as heat capacity per unit mole. Heat capacity per unit mole of the gas. Now people, you are done. C is nothing but dq upon dt. So dq upon n dt, right? dq upon n dt. Or from this particular equation, you can calculate dq. dq is equal to n Cm dt, or if you can integrate under the limits t1 to t2, so integral of dq becomes q. So q you can calculate from this result as well, n Cm delta t. n Cm delta t. Again, this molar heat capacity, it's also which property? It's also an intensive property. It is also an intensive property. So my point is there are different ways of calculating heat. Whenever you are supposed to calculate the heat absorbed by the system, calculate the heat released by the system, or calculate the heat exchanged between system and surroundings. So basically you're supposed to calculate Q, right? Whenever you get a question on heat exchange, between system and surroundings, Q, how many ways do we have to calculate Q? How many ways do we have to calculate Q? How many ways do we have? Number one, if C is given, if heat capacity is given, how do I calculate Q? Q is equal to C delta T, right? Number two, if Cm is given, if molar heat capacity is given, then how do we calculate Q? Q is equal to N Cm delta T, right? Similarly, if specific heat capacity of the system is given, then Q is equal to Ms delta T. Q is equal to Ms delta T. These are three ways by means of which we can calculate Q. Now guys, here you can further classify into two parts. At constant volume, if volume of the system is kept constant, over here I'm writing at constant pressure. At constant pressure. If volume of the system is kept constant, I'll write QV is equal to N CV delta T. Here I'll write QP is equal to N CP delta T. These are two very, very, very important results. What is the meaning of these results? Have a look. This QV is something which I call as, QV is what I call as heat exchanged between system and surroundings. Heat exchanged between system and surroundings at constant pressure. If your system is kept at constant pressure, at that point of time, how much heat is absorbed or released by the system? That is given by, constant volume. At constant volume. If your system is kept at constant volume, at that point of time, how much heat is absorbed or released by the system? That is given by this equation. Similarly, this is what I call as heat exchanged. Between system and surroundings at constant pressure. If your system is kept at constant pressure, at that point of time, the amount of heat absorbed or released by the system is given by this formula. QP is equal to NCP delta T. So basically, these two results are very important. What is CV? CV is what I call as molar heat capacity at constant volume. This CP I'll be calling as molar heat capacity at constant pressure. Right? Molar heat capacity at constant volume, molar heat capacity at constant pressure. Right, people? So these are the ways by means of which you can calculate Q. Sometimes they'll ask you, calculate the heat absorbed at constant volume, calculate the heat released at constant volume. That means QV you have to calculate. Calculate the heat absorbed or heat released at constant pressure. That means QP you have to calculate. Accordingly, you'll have to use the result. I'll show you its application in some time. Okay? Now, there are a few more things which you need to know. Okay? You must be knowing CP. It's always greater than CV. What is CP? Molar heat capacity at constant pressure. What is CV? Molar heat capacity at constant volume. CP is always greater than CV. Number one. CP minus CV is equal to R. Or how many moles of ideal gas? For 1 mole of ideal gas. Remember these results directly. Okay? There is one term which I'm defining. Poisson's ratio, gamma. Gamma is CP divided by CB. Since Cp is greater than Cv, so gamma value will be greater than 1. Right? Perfect. There is one more result which you need to know. Cv is equal to R divided by gamma minus 1. This is one more result which you need to remember. Cp minus Cv is equal to R. That's for 1 mole of ideal gas. If you'll be having 2 moles of ideal gas, it becomes 2R. 3 moles of ideal gas, 3R. N moles of ideal gas, NR. So remember, Cp minus Cv is equal to N times R. For what? For N moles of ideal gas. For N moles of ideal gas. Yes, for N moles of ideal gas. Right, people? For N moles of ideal gas. Now here, one more thing we can do over here. We got the relation between Cv and gamma here. We can get the relation between Cp and gamma as well. We can get the relation between Cp and gamma as well. Right? We can get the relation between Cp and gamma as well. Right, people? We can do that. You know, your gamma is equal to Cp by Cv. So I can write it as gamma is equal to. I can write as gamma is equal to Cp divided by. Instead of Cv, I'll write R divided by gamma minus 1. R divided by gamma minus 1. Right? So you got the result like this. The result will be like this. It will be Cp is equal to gamma R. Cp is equal to gamma R divided by gamma minus 1. This is the result which you'll be remembering, not this one. Cp is equal to gamma R divided by gamma minus 1. This is one more result which connects Cp with gamma. And this is something which you have to remember as well. Okay? Now guys, apart from all these things, there are a few more things which we have to remember. What are those things? Let me give you the results. Let me give you the results. For example, over here you have got 2 chemically non-reacting gases, 1 and 2. Let's say you have got 2 chemically non-reacting gases, 1 and 2. 2 chemically non-reacting gases, 1 and 2. Okay? Let's say number of moles of one is N1, this is N2. Cv for gas 1 is Cv1, this is Cv2, this is Cp1, this is Cp2. The mixture of gas which we got over here. The mixture of gas which we got over here. The mixture of gas which we got over here. Let's say you have to calculate Cv for the mixture. How do we calculate Cv for the mixture? N1 Cv1 plus N2 Cv2 divided by what? Divided by N1 plus N2. How do we calculate Cp for the mixture? How do we calculate Cp for the mixture? N1 Cp1 plus N2 Cp2 divided by what? Divided by N1 plus N2. How do we calculate gamma for the mixture? Gamma for the mixture is calculated as Cp mixture divided by Cv mixture. These are few results which are very important which you have to remember. I hope all these are clear. Okay, remember them directly. Okay. Now guys, one more table which I'll be giving you directly, then we'll go into the actual stuff. Right now, I'm just giving you the basic things which you have to remember first of all, before solving the question. Yeah? Before solving the questions. See guys, in case of a monoatomic gas, in case of the monoatomic gas, like helium, helium is monoatomic. In case of monoatomic gas, what is the value of Cv? What is the value of Cp? And what is the value of gamma? Let me tell you, Cv is nothing but 3 divided by 2R. Cp is 5 divided by 2R. Gamma is Cp by Cv, so this divided by this, which makes it 5 by 3. Which makes it 5 by 3. Number 1, these values you have to remember. These values you have to remember. These values you have to remember. Okay. Now, if you'll be having a diatomic gas, if you'll be having a diatomic gas, like what? Like O2, diatomic. Or if you have got triatomic linear gas, if you have got triatomic linear gas, like what? Like carbon dioxide, which is triatomic linear. It is Cv is 5 divided by 2R. It is Cp is 7 divided by 2R. And its gamma is this by this. So 7 by 5. 7 by 5. And by chance, if you have got triatomic non-linear gas, for example, you have got SO2. It is triatomic as well as non-linear. Triatomic as well as non-linear. Its Cv is 3R, Cp is 4R, right? And gamma is 4 by 3. 4 by 3, right? Now, people, can you let me know one thing? 5 by 3 is what? 1.66. This value is 1.4. This value is 1.33. Perfect. This value is 1.33. Now tell me, initially I start with monoatomic, then diatomic, then triatomic. On moving from top to bottom, what is happening to the atomicity of the gas? On moving from top to the bottom, atomicity is increasing. First diatomic, triatomic, etc. Atomicity is increasing. What is happening to the value of gamma? Gamma is decreasing. So can I generalize a statement over here? As the atomicity, atomicity means number of atoms in a molecule. As the atomicity of the gas increases, the value of gamma decreases. And these things, guys, Cp, Cv, and gamma values for these different types of gases will be frequently using everywhere in the chapter thermodynamics. Am I clear with this? Am I clear with this, guys? Yes? Am I clear with this? Right, people? I hope you remembered all the things which I gave you till now. Now comes the actual stuff. So basically your thermodynamics is starting from here. Till now, whatever I was telling you, right? That's all complete, basics and stuff which you need to remember. Degrees of freedom, you need not to remember here. I mean, we have got nothing to do with degrees of freedom. Do that in physics. Why do you need that in chemistry? From here, the show begins, yeah. From here, the show begins. Please do have some fun, sir. Yeah, sure. Sure. No, all the chapters cannot be completed today. I told you already there'll be 2 marathons, right? For class 11 physical chemistry. Half we'll do today, half we'll do in the next marathon. Yeah? Chemistry is fun. Let's wait for 2 minutes, then we'll start, okay? Let's take a short break for 2-3 minutes. Hair's secret. Like, what is good in this hair? Do you want to break for 10 minutes? Do you need a break for 10 minutes? Okay, let's take a break for 10 minutes and get back quickly. But get back, okay? From here, the chapter is starting. Huh? So the time now is 5:50. So break till 6 p.m. I would want everyone to be back on 6 p.m. at 6 p.m. Huh? Let's take a break for 10 minutes. Or let's keep it at 6:15. Wait, not 6:15. Sorry. Just a second. Let's get back at 6:10. I'll see you all at 6:10. Right? 6:10. But everyone has to be back because this is something which is super important in this chapter. See you. Are you guys back? Are you guys back with the positive energy? Yes. Are you all back? Are you all back? Guys, positive energy in the chats. Is everyone back? What's up? How are you all? Call up everyone, call up everyone. Let's get going. Perfect. Perfect, perfect, perfect. Cannot see properly. Perfect, then let's start with one more important topic, that's internal energy. Right? Internal energy. What this internal energy is exactly all about. My dear students, internal energy, which is represented either by U or E. Right? In some books, they represent internal energy by U or by E. Okay, what is internal energy? How do we define it? My dear students, internal energy is basically defined as the sum of all the kinetic and potential energy present in the system. Internal energy is basically defined as the sum of all the kinetic and potential energy present in the system. Now, what does it mean? Imagine that you have got a container, and in this container, just assume you have got a real gas molecule. These are, for example, your real gas molecule. Okay. Now, if I ask you a question, whether these real gas molecules will be in rest or motion, these real gas molecules definitely will be in motion, right? Translational motion, vibrational motion, rotational motion, right? So can I say basically these real gas molecules, they have got different types of kinetic energies, translational kinetic energy, vibrational kinetic energy, rotational kinetic energy, etc., etc. So there are different types of kinetic energies in the system. Number one. Number two, between the real gas molecules, there'll be interactions as well. Between the real gas molecules, there'll be interactions as well. And which energy comes into play due to interactions? Potential energy. Potential energy arises due to the interactions. So these real gas molecules which are there in the container, in short, can I say this real gas has got kinetic as well as potential energy. If I take the sum of all the kinetic and potential energy present in the system, the sum of all the kinetic and potential energy present in the system, that is something which I'll be calling as internal energy. So internal energy is basically the total energy present in the system. Internal energy is basically the total energy present in the system, right? Which is the sum of kinetic and potential. Perfect. Now, my dear students, for an ideal gas, if you talk about ideal gas, in case of ideal gas, there is no interaction between the molecules. In case of ideal gas, there is no interaction between the molecules. Therefore, potential energy in case of ideal gas will be zero. So in case of ideal gas, your internal energy is basically the total kinetic energy present in the system. In case of ideal gas, your internal energy is basically the total kinetic energy present in the system, right? Now, people, if I ask you, this internal energy, is it a state function or path function? This internal energy is absolutely a state function. If it is a state function, we shall be calculating change in the value of internal energy, which has to be U final minus U initial, right? If I talk about internal energy, what do you think? Is it going to be extensive or intensive? It is absolutely going to be an extensive property. Perfect. In case of the cyclic process, change in the value of internal energy, change in the value of internal energy, change in the value of a state function. In case of a cyclic process, that's always zero. Remember this thing as well. Okay. Now, people, two things which you need to remember. Internal energy for a real gas. Internal energy for a real gas depends on two parameters, volume and temperature. If the moles are fixed, okay, for a real gas, internal energy depends on two parameters, volume and temperature, for a fixed amount of moles. So if you change the volume of the real gas, internal energy will change. If you change the temperature of the real gas, internal energy will change. But in case of ideal gas, internal energy only and only depends on temperature for fixed amount of gas, right? This is valid for ideal gas. In case of the ideal gas, your internal energy, it only depends on temperature. Internal energy only depends upon temperature. In case of what? In case of ideal gas, right? I'm writing it again. Internal energy, it is a function of temperature only. For what? For an ideal gas. If the amount of gas in the container is fixed. Now, guys, what does it mean? What does it mean? It means something like this. Let's say you've got a container which contains fixed amount of ideal gas, If you change the temperature of the gas, its internal energy will change. If you change the temperature of the gas, its internal energy will change. How do we calculate change in internal energy due to change in temperature for an ideal gas? I'll give you the direct result. Delta U, or small change, du is equal to NCV dt. du is equal to NCV dt. It is valid only and only for the ideal gas. This is the ideal gas in the container. If you are changing its temperature by dt units, its internal energy will change by du units. That du is equal to NCV dt. Number one, right? Total change in internal energy for an ideal gas, delta U, that has to be NCV delta T. That has to be NCV delta T. And both these results, they are only valid for the ideal gases. They're only valid for the ideal gases, right? du is equal to NCV dt, delta U is equal to NCV delta T. Perfect. So if you are changing the temperature of this ideal gas from 10 degree to 20 degree, for example, what will be the change in internal energy, delta U? You can calculate from here. Number one. Number two. For an ideal gas undergoing an isothermal process. Isothermal process means temperature is constant. If temperature is constant, delta T has to be 0. If delta T is 0, that means delta U will be also 0. So remember, for an ideal gas which undergoes isothermal process, its delta U has to be 0. Right? This is the next point. Now, guys, look at this particular equation. du is equal to NCV dt. If I take 1 mole of ideal gas, for 1 mole of ideal gas, n is equal to 1, I can say Cv is equal to du upon dt. What is du upon dt? du upon dt gives you the slope of the tangent. At a point on internal energy versus temperature curve. Internal energy versus temperature curve. Okay, internal energy versus temperature curve. For example, I'm giving you a question like this. Let's say on this side I'm plotting internal energy. Let's say this is a hypothetical question. On this side I'm plotting temperature. Okay, and the curve which I'm giving you, let's say that's valid for 1 mole of ideal gas. For example, right? Hypothetical situation. This is the graph which we have. I'm taking 2 points here. This is point A, this is point B. Now we have to check at which point, A or B, where is the CV value more? Where will be the CV value more? What I'll be doing? I'll be extending this line. After the extension is done, I'll be drawing the tangent here. I'll be drawing one more tangent here. Perfect. After drawing the tangents, I'll measure this angle. Let's call this as theta A. Let's call this as theta B. Now tell me, which angle is more? I'll say theta A is more than theta B. If theta is more than theta B, that means slope of this tangent is more. Wherever the slope is more, CV value is more. So CV value will be more at A than that of B. So this sort of equation can be asked. Yeah? This sort of equation can be asked. I believe it's clear. I believe it's clear. Yeah? Perfectly done. Now, my dear students, let's have a look on few more things. Let's have a look on few more things. There is something called as first law of thermodynamics. There is something called as first law of thermodynamics. Okay? If you look at the statement, first law of thermodynamics, it is an energy conservation principle. It is an energy conservation principle. As per first law of thermodynamics, when the state of the system changes, there is the change in the internal energy of the system. When the state of the system changes, there will be change in the internal energy of the system. And that change in the internal energy, it can be brought about in two ways. Number one, when heat is absorbed or released by the system, when work is done by the system or on the system. Let's try to understand what it means. Let's try to understand what it means. First of all, I want you guys to remember this. It is the energy conservation principle, and you know, when the state of the system changes, there will be definitely change in its internal energy. There will be change in the internal energy of the system. And that change in the internal energy of the system can be brought about in two ways. Number one, when heat is absorbed or released by the system. Number two, when work is done on the system or by the system. What does it mean? Let's try to check it. Let's try to check it. See, guys. For example, this is the container which I have. And over here, you have got a piston. This is a piston. This is the ideal gas here in the container. Okay, this is the ideal gas. This ideal gas, the system is right now present at its initial state. The system is right now present at its initial state. Let's assume it's total energy. Total energy present in the system. I mean the internal energy of the system. That's U1. That is U1. For example, what am I doing? I'm supplying some Q amount of heat to this system. I'm supplying some Q amount of heat to this system. Now, if I ask you, what will be the total energy of the system now? I have supplied some Q amount of heat to the system. So the total energy of the system now will be U1 plus Q. It will be U1 plus Q, right? My dear students, let's say I'm bringing this piston down. Let's say I'm bringing this piston down. When I'm bringing this piston down, what am I doing? Compression. Whenever there is compression, work is done on the system. Let's say I have done some W amount of work on the system. Let's say I have done some W amount of work on the system. And for example, whatever amount of work I'm doing on the system, that is stored in the gas. So what will be the energy now? U1 plus Q plus W. I'm assuming this is the final state of the system. If this is the final state of the system, then this has to be the final value of internal energy of the system. If you take U1 on that side, it's U2 minus U1. U2 minus U1 is delta U, and delta U is nothing but Q plus W. This is the result which you have to remember. This is the result which you need to remember. Delta U is equal to Q plus W. Delta U is equal to Q plus W. Okay, delta U is equal to Q plus W. Perfect. This is the result which we have to remember. Delta U is equal to Q plus W. First law of thermodynamics. First law of thermodynamics. Now people try to understand. Try to understand. For example, one simple question, which is just a standard question, right? By means of which you'll understand this first law. The question is, a system expands. System means your ideal gas. Expands from 5 liters to 10 liters. So initial volume of the gas is 5 liters. Final volume of the gas is 10 liters. Expansion is happening against a constant external pressure. Expansion of the gas is happening against a constant external pressure of 2 atm. If it absorbs 800 joules of heat during the expansion of the gas, system is absorbing heat. When heat is absorbed, Q value is positive. When heat is absorbed, Q value is positive, right? During the process. Calculate the value of delta U. Calculate the value of delta U. We have to calculate delta U. Okay. Right now, few minutes back only, I gave you the first law, and first law says that your delta U is nothing but Q plus W. Okay, Q plus W. You just tell me one thing. Is the process reversible or irreversible? Is the process reversible or irreversible? Just tell me that. Is the process reversible or irreversible? Just tell me that. Expansion is happening against constant external pressure. Constant external pressure means whenever it is mentioned that external pressure is constant, remember the process is irreversible. Okay, it's irreversible. If it is irreversible, how do we calculate work done in case of irreversible processes? It is simply minus P external delta V, which is V2 minus V1. So minus, what is P external? P external is 2 atm. V2 minus V1. V2 minus V1, that comes out to be 5. So the value is minus 10 atm liter. But I'll convert this in joules, minus 10. 1 atm liter, I told you already, 101.3 joules. So the value comes out to be minus 1013 joules. This is the value of W, right? What is the value of Q? What is the value of Q? Q is plus 800 joules, right? So delta U is nothing but plus 800 joules. W is minus 1013 joules, right? The value will be minus 213 joules. This is the value of delta U which I was supposed to calculate. Is it clear? Is it clear, people? Is it clear? So this sort of equation, I believe you can easily solve. Okay. Similarly, one more type of question. Can you do it on your own? Check it out quick. Will you be able to do it on your own? Check it out carefully. Again, you have to use delta U is equal to Q plus W. Delta U is given, Q is given, P external is given, delta V you have to calculate, change in volume, right? Yes, Harini, you can watch it. It's a simple question, guys. As far as I remember, its answer will be, I think, 2 liters. Yeah? You just check it by using the same first law of thermodynamics. Nothing else. Okay, now comes one more thing, that is enthalpy. Enthalpy. Yeah? When is the second part of the marathon? Next week. Next week, okay? I'll let you know. I'll let you know in the Telegram. My dear students, now comes your enthalpy. What is enthalpy? It is represented first of all by H. How this enthalpy function was introduced? How this enthalpy function was introduced? Let's get to know. See, guys. See how this enthalpy function was introduced. How this enthalpy term was introduced. You know, your delta U is equal to Q plus W. You know that, right? Delta U I can write as U2 minus U1 is equal to Q plus W is equal to Q plus W. W is minus P delta V, V2 minus V1. Okay. If I write the same equation at constant pressure, it becomes QP at constant pressure if I write the same equation. So here I can write U2 minus U1 is equal to QP minus PV2 plus PV1. Okay. If I take it on this side, it's going to be U2 plus PV2. U2 plus PV2 minus U1 plus PV1. U1 plus PV1 is equal to QP. My dear students, do you see 2 similar terms here? U plus PV as well as U plus PV. It is just this term, U plus PV. It's written at final state. This is written at initial state. Otherwise, the terms are same. U plus PV, U plus PV. Right? U plus PV, U plus PV. Both the sides. Yeah? This U plus PV only we call as H. In mathematics, what do? We say let y is equal to 5x square plus 4x plus something something. Right? Perfect. Just to reduce the calculations, etc., etc. Over here, U plus PV, U plus PV. This U plus PV only I'm calling as H. So how do I define enthalpy? Enthalpy is the sum of internal energy and the pressure volume work. Right? If you need to define enthalpy, it is defined as the sum of internal energy and the PV work. Okay? So people, this U2 plus PV2, can I write it simply now as H2? This U1 plus PV1, H1 is equal to QP. H2 minus H1 is nothing but delta H, and delta H is equal to QP. Now, this is something which is very important. What is meant by this? Delta H is equal to QP. Delta H is equal to QP. It means that enthalpy change. It means that enthalpy change is defined as the total heat absorbed or released by the system. Absorbed or released by the system at constant pressure. At constant pressure, whatever will be the amount of heat absorbed or released by the system. If you have got the system, if you have got the ideal gas, right, which is kept at constant pressure, whatever heat will be absorbed or released by this ideal gas, which is kept at constant pressure, that actually gives you what? That gives you the enthalpy change. That gives you the enthalpy change of the system. So remember, enthalpy change of the system is nothing but the heat absorbed or released by the system when the system is kept at constant pressure. Yeah? When the system is kept at constant pressure. Am I clear? Am I clear, people? Again, if I talk about enthalpy, the way we talked about internal energy, again, if I talk about enthalpy, let me tell you, it is a state function. Enthalpy is a state function. If it is a state function, change in enthalpy has to be equal to H final minus H initial, right? Again, enthalpy is an extensive property. It is an extensive property. Why is it an extensive property? Because you know, H is equal to U plus PV. U is extensive, P is extensive, V is extensive, right? So H automatically becomes extensive. Okay? I told you the reverse thing. I had to say it is a state function. Just a second. I gave you the wrong logic here, sorry. I don't know, where was I? I'm telling you enthalpy is a state function. Why is it a state function? Because enthalpy is the state function, because enthalpy is equal to U plus PV. U is a state function, P is state function, as well as V is state function. Okay? Perfect? Right, people? So enthalpy is a state function. Now, enthalpy is extensive as well. Enthalpy is an extensive property as well, because its value changes when you change the amount of substance present in the system. Its value changes when you change the amount of substance present in the system. For a cyclic process, delta H has to be, zero. Okay? Perfect. Now, similarly, enthalpy for fixed amount of gas is the function of pressure and temperature for a real gas. For a real gas, enthalpy depends on two parameters, pressure and temperature. If you change the pressure of the gas, enthalpy of the gas will change. If you change the temperature of the gas, enthalpy of the gas will change. But only valid for real gas. In case of the ideal gas, enthalpy is only the function of temperature. Right? For a fixed amount of gas. So basically, let me tell you one thing. Internal energy gives you the total energy present in the system. And enthalpy gives us the idea about the heat content present in the system. Okay, these are two things. One is internal energy, one is enthalpy. Internal energy gives us the idea about total energy present in the system. Enthalpy gives me the idea about the heat content present in the system. It gives me the idea about the heat content present in the system. Okay, heat content present in the system. So, for example, imagine that you have got an ideal gas in the container. Enthalpy of the ideal gas only depends on temperature. So if you change the temperature of this ideal gas, its enthalpy will change. Right? Its enthalpy will change. Now, if I'm changing the temperature of this ideal gas from T1 to T2, what will be the total change in its enthalpy? What will be the total change in the enthalpy? Remember, guys, remember one thing. Your dH, small change in enthalpy, is nothing but N Cp dt for an ideal gas. And total change in enthalpy delta H is nothing but N Cp delta T for an ideal gas. These are the results by means of which you can calculate the enthalpy change of an ideal gas when you change the temperature. So when you change the temperature of the ideal gas, its enthalpy will change. How do we calculate that change in enthalpy? With the help of this result. I'll show you the questions in some time. Right? Perfect. Now people, one more thing. For an ideal gas undergoing isothermal process. For an ideal gas undergoing isothermal process. In isothermal process, temperature is constant. If temperature is constant, delta T has to be 0. If delta T is 0, your delta H automatically becomes 0. So whenever the ideal gas undergoes isothermal process, its delta H has to be 0. 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 I hope this is clear. Now, similarly, people, one more thing. One more thing. dH is equal to NCP dt. If I'll be having 1 mole of an ideal gas. If I'll be having 1 mole of an ideal gas, N is equal to 1. If N is equal to 1, Cp is equal to what? Cp is equal to dH upon dt. What is dH upon dt? Graphically, it is the slope of the tangent at a point. Slope of tangent at a point on enthalpy versus temperature curve. On enthalpy versus temperature curve. Now, for example, one hypothetical question. If I'm plotting a graph between enthalpy versus temperature, and this graph is, for example, for 1 mole of ideal gas. It is for 1 mole of ideal gas. I'm marking 2 points here, A and B. Can you let me know where will be the Cp value more? Can you let me know where will be the Cp value more? Quickly. Can you let me know where will be the Cp value more? Cp value. Where will be the Cp value more? A or B? How you guys are going to do it? Is this color visible? No. Let me use a different color today. I think this is visible. What I'll be doing at this point, I'll be drawing a tangent. And at this point, I'll be drawing a tangent. I have drawn 2 tangents. Let's say this is theta A, this is theta B. Now, which tangent has more slope? At A, tangent has more slope, right? At A, tangent has more slope. More the slope, more the Cp value. So I'll say Cp at A will be definitely greater than that of Cp at B. Okay? Am I clear, people? Yes, Wasim sir showing off different colors. All right. Is it clear, guys? Is it clear? Is it clear? Okay, one thing. I don't want to go into the details, but one thing I would want to tell you. If you remember long back, like 1 hour back, when I taught you the heat capacities, I gave you 2 results there. QV is equal to, one was NCV delta T and one was QP. QP is equal to NCP delta T. Perfect. I gave you these 2 results long back when I taught you heat capacities. But now you got to know your NCV delta T is basically delta U. Your NCP delta is basically delta H for the ideal gas, right? So basically the questions can be asked in different formats. Either they'll ask the question like this. Calculate the heat absorbed or released at constant volume. That means you have to calculate delta U for the ideal gas, which is NCV delta T. They can ask you calculate the heat absorbed or released at constant pressure. That means they're asking you to calculate delta H for the gas. And delta H is what? For the ideal gas, it is NCP delta T, nothing else. Either they'll be asking you the questions directly, calculate delta U or delta H, or they can ask you the question in terms of heat exchange as well. Calculate the heat absorbed, released at constant pressure or at constant volume. If it is constant pressure, that means delta H. If it is constant volume, that means delta U. Okay? Perfect. Let's try to do one question by means of which you will get the idea of what kind of question can be asked. Okay, one simple question. Calculate the delta U and delta H, for example, in joules. Let's say you have to calculate both in joules. Look at it. Look at it, people. Look at this question. Vanshika, I did not teach entropy yet. Just wait. These are two different things, entropy and enthalpy. Can you give it a try? Can you give it a try? It's a simple question, guys. As per the question, you have got 10 decimeter cube of helium. 1 decimeter cube is 1 liter. So basically, you have got 10 liters of helium. 10 liters of helium. Helium is monoatomic. And this gas is present at STP. This gas is present at STP. Right? That means temperature of this gas is right now 0 degrees centigrade. Right? 273 Kelvin. Perfect. Now, as per the question, the gas which is there in the container, you are changing its temperature. You are heating it up till how much? Till 100 degrees centigrade. Till 373 Kelvin. That means initial temperature of the gas was 273. Final temperature of the gas is 373. Yes. So basically, as per the question, you had 10 liters of helium. You are heating it. You are increasing its temperature. You are increasing its temperature from 273 Kelvin to 373 Kelvin. Since you know, in case of ideal gas, internal energy as well as enthalpy, they are temperature dependent. So if you are changing the temperature, there will be change in the internal energy as well as enthalpy of this ideal gas. Now that's what I'm supposed to calculate. Calculate the change in internal energy and calculate the change in enthalpy of the ideal gas. These two terms I'm supposed to calculate. Right? These two terms I'm supposed to calculate. First of all, how do we calculate delta U for the ideal gas? NCV delta T, which is T2 minus T1. How do we calculate delta H? NCP delta T, T2 minus T1. Now guys, helium, since helium is monoatomic, if it is monoatomic, its CV is nothing but 3 by 2R. Its CP is nothing but 5 by 2R. It is monoatomic. Correct? It is monoatomic. Now at the same time, we had 10 liters of helium at STP. Can you tell me how many moles of helium were there? Given volume divided by 22.4. So these many moles of gas we have in the container. So N value we know. N value is 10 divided by 22.4. What is CV value? T divided by 2. And R is nothing but 8.314 joules per Kelvin per mole, because we have to calculate delta U, delta H in joules. T2 minus T1. T2 minus T1 will come out to be 100. So solve this. Answer will be in joules. Similarly, N is 10 divided by 22.4. CP is 5 by 2. R value is 8.314. T2 minus T1 is 100. Right? Solve this and this will come in joules. So this is how you are going to get delta U as well as delta H. Am I clear? Okay, perfect. I hope this sort of a question you can easily solve from now on. Now guys, there is one more important topic from which questions have been frequently asked. Frequently, I would say. That is the relation between delta H and delta U. Relation between delta H and delta U. This is one very, very, very important topic. A relation between delta H and delta U. I won't be deriving things, I'll be just giving you the results. And I'll show you how to apply them. That's all. Okay? That's all. That's all. See guys. First of all, as you know, your H is equal to U plus PV. H is equal to U plus PV. You know it. Correct? If I multiply throughout by D, it becomes DH is equal to DU plus D of PV. If I integrate throughout, it becomes delta H is equal to delta U plus delta of PV. This is the general result that relates delta H with delta U. This is the general result that relates delta H with delta U. Delta H is equal to delta U plus delta of PV. Okay. Now, my dear students, if in the question, pressure of the gas, pressure of the system is given as constant. If the pressure of the system is constant, then you will write delta H is equal to delta U plus. If pressure is constant, P comes to the front, then it becomes P delta V. Delta V is V2 minus V1. This is the equation which you'll be using if pressure of the system is given constant. If volume of the system is kept constant as per the equation, if volume of the system is kept constant, then take this V out. Your formula becomes delta H is equal to delta U plus V delta P. V delta P. This is used when volume is constant. Similarly, my dear students, if pressure and volume both are changing as per the question, if pressure and volume of the system is changing, which formula do I use? I'll be using delta H is equal to delta U plus, I'll be simply writing P2 V2 minus P1 V1. P2 V2 minus P1 V1. Okay, P2 V2 minus P1 V1. Right? For example, you have got, let's say you have got a homogeneous gaseous phase reaction. Let's say you have got a homogeneous gaseous phase reaction, which is carried out at constant temperature. Carried out at constant temperature. Let's say the reaction is like this. N1A gas plus N2B gas. It gives N3C gas plus N4D gas. This is your homogeneous gaseous phase reaction. Okay? My dear students, for this particular reaction, remember, delta H will be equal to delta U plus delta NGRT. Delta NGRT. What is delta NG here? What is delta NG for this reaction? Delta NG means number of moles of gaseous products minus number of moles of gaseous reactants. So delta NG is equal to number of moles of gaseous products. Number of moles of gaseous products. This is gaseous product, this is gaseous product. So N3 plus N4 gives you the number of moles of gaseous product minus number of moles of gaseous reactants. This is gaseous reactant, this is gaseous reactant. Their moles are N1 plus N2. So minus N1 plus N2. These are certain results which you need to remember. And with the help of these particular results, you can solve the questions wherein you have to relate delta H with delta U. Am I clear? Am I clear? Am I clear, people? Am I clear, people, with this? Dark mode is going to happen in some time. Okay, let's try to utilize all these formulas. Let's see what kind of different questions can be asked. Okay. Let's start with this question. It's an asked question. Look at the question carefully. Look at the question carefully. 1 mole of ideal gas undergoes a change in state. 1 mole of ideal gas undergoes a change in state. 2 atm 3 liters. So you have got the ideal gas whose initial pressure was 2 atm and its volume was 3 liters. Let's say the ideal gas was present at its initial state. Okay, pressure of the gas was 2 atm, its volume was 3 liters. Now, as per the equation, we are changing the state of the gas. The final state parameters of the gas are 2 atm, 7 liters. Now the gas, for example, is present at its final state. So look at the things which are given. Volume of the gas initially was 3 liters. Now the volume of the gas is 7 liters. That means the state parameter is changing, right? And when the value of state parameter changes, the state of the system automatically changes. So basically, the gas is undergoing a change in state. But if you look carefully, during the change in state, is the pressure of the gas changing? No, pressure is remaining constant. Pressure is remaining constant, right? So we identified during the change in the state, P is constant. If P is constant, then which formula do we need to use? Delta H is equal to delta U plus P delta V. Plus P delta V, right? As per the question, your delta H is given as 30 atm liter. I mean, delta U is given as 30 atm liter. Pressure is 2 atm. V2 minus V1. V2 minus V1. 7 minus 3 is 4. So this is atm, this is liter. So this also comes in atm liter. So the value comes out to be 38 atm liter. This is the value of delta H, which we are supposed to calculate. Perfect. Now you can convert this into joules as well. Multiply this 38 with 101.3. The answer will come in joules. I hope I'm clear with this. Yeah? I hope I'm clear with this. This is the first step of the question that can be asked. Number one. Number two. Look at this particular question. Look at this particular question. Which of the following is correct for the following exothermic reaction carried out at constant pressure? You know, your reactions are mainly carried out at constant temperature, and with constant temperature, you have kept pressure constant as well. So first of all, this is the reaction that's given to me. As per the question, the reaction is exothermic. Now you tell me, if the reaction is exothermic, heat is absorbed or released? Released. Whenever heat is released by the system, Q value is taken to be positive or negative? Negative, right? Over here, Q is positive. This cannot be the answer. Done? Number one. Number two. The reaction is carried out at constant pressure temperature. You know, your PV is equal to what? nRT. So pressure temperature constant, R is constant, volume is directly proportional to moles. If moles are increasing, volume will increase. If moles are decreasing, volume will decrease. Now try to understand. On the reactant side, how many gaseous moles do we have? 3 plus 1, 4. On the product side, how many gaseous moles do we have? 1 plus 1, 2. So when this process is happening, are the gaseous moles increasing or decreasing? When the process is happening, are the gaseous moles increasing or decreasing? Gaseous moles are decreasing. Therefore, volume will decrease. Decrease in the volume of the system. Decrease in the volume of the system is what you call as compression. Whenever there is compression, work is done on the system. And whenever work is done on the system, W value is taken to be positive. W positive. W has to be positive. Over here, they are mentioned W negative. So this cannot be the answer. Okay. Now, can you let me know the delta Ng for the reaction? Number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactants, which is 2 plus 3, 3 plus 1, 4. The value comes out to be minus 2. So delta Ng is minus 2. If delta Ng is minus 2, you know, delta H is equal delta U plus delta Ng RT. So it becomes like this. So your delta U becomes equal delta H plus 2 RT. So from this particular equation, is delta U equal delta H? No. I'll say delta U is greater than delta H. Delta U, from this particular equation, you can see delta U is greater than delta H by this much of amount. Delta U is greater than delta H. So this cannot be the answer. Only B is the answer, right? Am I clear? Am I clear, people? Quick. Okay. I believe it's clear. Moving ahead. Okay, this is one more common question which is asked. Look at the question carefully. Guys. Calculate delta U when 2 moles of liquid water vaporizes at 100 degrees centigrade. So you are vaporizing liquid water. What does that mean? So you are converting H2O liquid into what? You're converting H2O liquid into H2O gas. Right? Delta H vaporization is given to us as 40.66 kilojoules per mole. What do we have to calculate? We have to calculate delta U during the process. Delta H is given, delta U we are supposed to calculate. Yeah? First thing, guys, can you let me know delta Ng for this reaction? Number of moles of gaseous product, which is 1, minus number of moles of gaseous reactant. This is not gaseous reactant, so 0. So delta Ng is 1. Number 1. Number 2. You know delta H will be equal to delta U plus delta Ng RT, right? I need to calculate delta U. So delta U is equal to delta H minus delta Ng RT. Okay. Delta U is equal. What is delta H? 40.66 kilojoules. 40.66 kilojoules minus delta Ng is 1. R value is 8.314 joules per Kelvin per mole. Joules. Temperature is how much? 100 degree, 373 Kelvin. Since I use the value of R as 8.314 joules, but this term is in kilojoules, so this term has to be in kilojoules as well. I'll be dividing this term with 1000, then only it will come in kilojoules. Perfect? Right? So my dear students, after solving this particular equation, what you'll be getting? You'll be getting the value of delta U as 37.5. 37.5. Is there any option as 37.5? Yes, but That's not going to be the answer. This is not going to be the answer. Why? This is the value of delta U. This is the value of delta U for the vaporization of 1 mole of liquid water. We are vaporizing 1 mole of liquid water here. We are vaporizing 1 mole of liquid water. But as per the question, we have to vaporize 2 moles of liquid water. This is the value of delta U for the vaporization of 1 mole of liquid water. Therefore, for the vaporization of 2 moles of liquid water, you have to multiply this by 2. When you multiply this by 2, the answer comes out to be 75.1 kilojoules. Am I clear with this? Am I clear with this, people? Am I clear with this? Perfect. Perfectly done. Guys, all the things are clear till here? Say it in the chats once. Are all the things clear? Perfect. Now, guys, let's have a look on different types of processes. First of all, I have given you the idea about the isochoric process. What is an isochoric process? In which volume remains constant. If volume is constant, delta V is 0. So work done in case of isochoric process will be 0. Perfect. So if I use the first law of thermodynamics here, delta U is equal to Q plus W. But since volume is constant, isochoric, so W is 0. So delta U is equal to Q, and I'll be just writing it QB. What is the meaning of this equation? Is this equation valid everywhere? No. This equation is only valid for isochoric processes when volume is kept constant. So at constant volume, basically, at constant volume, whatever amount of heat will be absorbed by the gas. At constant volume, whatever amount of heat will be absorbed by the gas, that entire amount of heat is utilized. Increase the internal energy of the gas. Guys, it's simple. See, if Q value is positive, that means delta U is positive. Delta U positive means internal energy increasing. So at constant volume, remember, at constant volume, whatever amount of heat is absorbed by the gas, that entire amount of heat is utilized to increase the internal energy of the gas. Okay? Perfect? Right? I hope this is clear. W value in case of isochoric process, always remember this is 0. Because volume of the system does not change. If volume does not change, delta V is 0. If delta V is 0, W is 0. Okay? Perfect. If W is 0, right? I hope this is clear. Number 1. Number 2 here, that you all must be knowing. Pressure volume curve, how it looks like. Pressure volume curve, how it looks like. It's a straight line like this, and this straight line is what you call as isochore. It's what you call as isochore. Okay? Now, when you talk about isobaric processes, in case of isobaric process, what do we have? In case of isobaric processes, pressure is constant, you know it. Pressure of the system is kept constant. Delta P is 0, right? Perfect. Delta U is nothing but Q plus W. Here I'll write QP. At constant pressure. At constant pressure, delta U is equal to Q plus W. How do we calculate work done in case of the isobaric processes? How do we calculate work? The first result you already know. That is minus P delta V. Perfect. Or you can use this as well for the reactions. Minus delta Ng RT. And particularly this particular result is used when a reaction is carried out in an open vessel. When a reaction is carried out in an open vessel. Because when the reaction is carried out in the open vessel, we consider it as isobaric in nature. And if it is isobaric, then this is the result which we'll be using. Okay? Perfect. Right, guys? Now, let me show you certain, or before showing you the questions, tell me what will be the PV curve here. If you talk about PV curve, it will be like this, isobar. It will be isobar. For example, I'm giving you certain questions. Let me see if you can solve them or not. For example, this is the question. For example, this is the question. 1 mole of aluminium is dropped in an aqueous solution in an open container. Open container means isobaric, containing HCl. If 95 calories of heat is released means Q is minus 95 calories. Heat is released, right? Calculate W, delta U, delta H. Calculate W, delta U, delta H. First of all, it's isobaric. So W has to be equal to minus delta NGRT. Minus delta NGRT. Delta Ng is equal. Delta Ng is equal. Number of moles of gaseous product, which is 3 by 2. This is not gaseous. Minus number of moles of gaseous reactant. There is no gaseous reactant. So your delta Ng is just 3 by 2. So W, if I calculate from here, minus delta Ng is 3 by 2. R value I'll be taking in calories, for example, which is 2. Temperature is given to me as how much? 300 Kelvin. Perfect. So this 2 got cancelled. So W comes out be minus 900 calories. This is the value of W. Number 1. So W you got. Okay, W you got. What is the amount of heat released at constant pressure? Right? It is 95 calories. Now, since W you got, and you got this QP. What is QP? QP is basically heat absorbed or released at constant pressure. You know already, QP is nothing but delta H. I've already told you. What is QP? QP is basically delta H. QP is basically delta H. So, delta H also you calculated. QP is delta H, QV is delta V. Sorry, QP is delta H, QV is delta U. Okay? So guys, these two terms we got. Now delta U we have to calculate. What is delta U? If I use first law, delta U is equal to Q plus W. Right? Since the process isobaric, so I'll write QP. So delta U has to be equal to what is QP? QP is minus 95. W value is minus 900. The value comes out to be minus 995 calories. This is the value of what? This is the value of delta U over here. I believe I'm clear. I believe I'm clear. Yes? Perfect. Let's try to solve one more question from the same concept. Let's try to solve one more question. Let me see if we can solve this or not. This is the question. Just add one thing at 300 Kelvin in an open container. In an open container. Can you solve this one? My dear students, whenever it's mentioned that reaction is happening in an open vessel, take pressure constant always. Okay? Take pressure constant always. Work done during the decomposition of 5 moles of this PCl5. So first of all, what is the delta Ng for this reaction? Delta Ng is equal to 1 plus 1, 2, 2 minus 1, 1. So delta Ng is 1. Delta Ng is 1. How do we calculate W? Minus delta Ng RT. Right? Delta Ng is 1. R value in calories is 2. Temperature is 300. The value comes out to be 600 calories. But this is the value of W for the decomposition of 1 mole of PCl5. This is the value of W for the decomposition of 1 mole of PCl5. Right? This is the value of W for the decomposition of 1 mole of PCl5. But as per the equation, we have to decompose 5 moles of PCl5. So the value of W for the decomposition of 5 moles of PCl5 is equal to 600 multiplied with 5. The value will be 3000 calories. This is the final answer of the question. This is the value of W for the decomposition of 1 mole of PCl5. And this is the value of W for the decomposition of 5 moles of PCl5. I hope I'm clear. I hope I'm clear. Right? Yeah? Perfectly done. Now, let's talk about the isothermal processes. Let's talk about isothermal processes. My dear students, what do you have to remember in case of isothermal processes? First of all, we have got the ideal gas which is undergoing isothermal process. Isothermal process means temperature constant. Temperature constant means delta T is equal to 0. Delta T is 0 means delta U is equal to Q plus W. Or wait. Delta T is 0. You know, your delta U for the ideal gas is nothing but NCV delta T. If delta T is 0, that means delta U is 0 as well. You know it already. You know it already. Now, as per the first law, delta U is equal to Q plus W. For the isothermal process, delta U is 0. So Q is nothing but minus W. This particular equation, Q is equal to minus W, is it valid everywhere? No. It is only valid for the ideal gas undergoing isothermal process. Right? Q is equal to minus W. Now, my dear students, from this particular equation, Q is equal to minus W, we can generalize a lot of things. From this particular equation, which is valid for isothermal process, we can predict a lot of things. We can depict a lot of things. Now, what all things can we depict from here? Yeah? Hema, what are you saying exactly? The Phoenix batch complete in 7 months. Is there other batch? Like what? Okay. One more thing, guys. We have got the ideal gas undergoing isothermal process. Its delta H will be also 0, you know, because delta T is 0. Delta H is also 0 because delta H for the ideal gas is NCP delta T. Already that is discussed. I've told you that. So look at this particular expression. Look at this particular expression. Understand. W value can be positive or negative, right? W can be positive or negative. These are the two things which can happen. W can be either positive or negative. W negative means expansion. W positive means compression. Okay? Perfect. If W is negative, negative makes it positive. Therefore, Q value is positive. Therefore, Q value is positive. If W is positive, negative makes it negative. So, Q is negative. Q negative means heat is released by the system. Q positive means heat is absorbed by the system. Basically, here I can generalize two statements. If you look carefully, I can generalize two statements. I can say, during isothermal expansion of an ideal gas. I can say, during isothermal expansion of an ideal gas. During isothermal expansion of an ideal gas, heat is absorbed by the gas. Heat is absorbed by the gas. And similarly, during isothermal compression of an ideal gas, heat is released by the gas. Heat is released by the gas. These are the two statements which are important, guys. Okay? During isothermal expansion of an ideal gas, heat is absorbed by the gas. During isothermal compression of an ideal gas, heat is released by the gas. Two important statements. Okay? Perfect. Perfect, guys. Now, the main point. How do we calculate work done in case of isothermal processes? Right? How do we calculate work done in case of isothermal processes? My dear students, you know we have got two types of process basically. One is reversible, one is irreversible. So on one side, I'm writing a reversible isothermal process. A reversible isothermal process. On another side, I'm writing irreversible isothermal process. Irreversible isothermal process. The point is, how do we calculate work done in reversible isothermal and irreversible isothermal? How do we calculate work done in both? First thing, if you remember, in case of reversible process, how do we calculate work done? W reversible is equal to minus integral V1 to V2. This is P gas multiplied by dV. Do you remember that? Perfect. So W reversible will be equal to minus integral V1 to V2. What is P? P is nothing but nRT divided by V multiplied by dV. If you do the integration, etc., what you'll be getting? Minus nRT will come out. It is going to be ln of V2 divided by V1. Ln of V2 divided by V1. Or you can write it like this. Minus nRT ln of, instead of V2 by V1, I can write P1 divided by P2. I can write P1 divided by P2. This is how you calculate work done in case of a reversible isothermal process. Or my dear students, you can write it like this. W reversible is equal. Convert this in logarithmic form. It'll be minus 2.303 nRT. It's going to be log of V2 by V1. Or minus 2.303 nRT. It's going to be log of P1 by P2. These are the expressions which are to be used to calculate work done in case of a reversible isothermal process. Reversible isothermal process. Now, what about irreversible? What about irreversible isothermal process? How do we calculate work done in irreversible isothermal process? W irreversible. You already know it is nothing but minus P external, V2 minus V1. This is the first result which you'll be using. Or sometimes you'll be using this one as well. W irreversible is equal to minus P external. Instead of V2, I can write nRT divided by P2 minus, instead of V1, I can write nRT divided by P1. These are the two expressions which can be used to calculate work done in case of irreversible isothermal process. Reversible isothermal work done, irreversible isothermal work done. Remember them. Remember these expressions. Now, if you remember these expressions, you can easily solve the questions. For example, look at this question. Look at this question, guys. Can you solve this? Can you solve this question? Can you solve it? See guys, as per the question, calculate Q, W, delta U, delta H. When 2 moles of ideal gas are expanded reversibly and isothermally. Ideal gas undergoing isothermal process. So delta U as well as delta H both have to be 0. Right? Initial pressure of the gas is given as 10 atm. Final pressure of the gas is given as 5 atm. Right? 5 atm. Temperature is kept 27 degrees centigrade. Right? We have got 2 moles of ideal gas which is undergoing isothermal process. Is it isothermal reversible? Yes, it's isothermal reversible. Right? It is isothermal reversible. How do we calculate work done in isothermal reversible processes? It is minus nRT ln of P1 by P2. Correct? Minus. What is N value? N value is 2. R value taken calories, for example, that is 2. Temperature, how much? Temperature, 27 degree means 300 Kelvin. Ln of P1 by P2. 10 by 5 is 2. Ln of 2. Ln of 2 is how much? 0.7. Right? 0.7. How much this value comes out be? Do I have to calculate in calories? Yes. N is 2, R is 2, temperature is 27 degrees centigrade, 300 Kelvin, ln of P1 divided by P2. So this is 2, 2, 4, 4, 3, 12. 12 into 0.7 comes out be minus 840. Minus 840 calories. So you got the W as well. You got delta U, you got delta H. Right? You got W as well. And since the process isothermal, in case of isothermal process, Q is equal to minus W. Right? W already calculated. So Q value comes out be plus 840 calories. So these were the things which we were supposed to calculate. This Q, this is W, and delta U, delta H. These were the 4 parameters which were supposed to be calculated. I hope this is clear. Yes? Am I clear, people? Am I clear? Look at one more question. Look at this particular question. Let's see what the question is all about. You read the question first of all. Read the question. Quickly. 2 liters of N2 gas at 0 degree and 5 atm are exploded isothermally against a constant external pressure. It is mentioned that external pressure is constant, so process irreversible. Process irreversible isothermal. Right? Process is irreversible isothermal. Calculate how much heat will be absorbed or released. Calculate how much heat will be absorbed or released. First of all, you have got 2 liters of N2 gas. 2 liters of N2 gas. Kept at a pressure of how much? 5 atm. Now the gas is exploded. Let's say the final volume of the gas is V2. As per the equation, the final pressure of the gas is how much? 1 atm. Expansion is happening against constant external pressure. How much is the constant external pressure? That is also 1 atm. P external is 1 atm. P external is 1 atm. The process is irreversible. And at the same time, it's mentioned that the process is isothermal. The process is irreversible isothermal. The process is irreversible isothermal. Okay? Irreversible isothermal. Since the process isothermal, so it has to follow Boyle's law. It has to follow Boyle's law. Boyle's law says that P1 V1 is equal to P2 V2. Correct? What is P1? P1 is 5. What is V1? 2. What is P2? 1. What is V2? You can calculate from here. So V2 is nothing but 10 liters. So you got to know the V2. That is 10 liters. Correct? Since the process is irreversible isothermal, if the process is irreversible isothermal, so W irreversible has to be equal to simply minus P external V2 minus V1, right? Which will be minus, what is P external? 1 atm. What is V2? 10 minus 2, that's 8. The value comes out to be minus 8 atm liter, which can be written as approximately minus 808 joules. This is the value of W. But am I supposed to calculate W or Q? I'm supposed to calculate Q. And you know, my dear students, in case of isothermal processes, Q is equal to minus W. So it has to be plus 808 joules. Plus 808 joules. Right? So these sort of questions can be asked from the isothermal process, be it reversible or irreversible. Okay? Perfect, guys? Yeah? All right. Now, moving ahead. There is something called as adiabatic process as well. Adiabatic process. What are adiabatic processes? You know it already. In case of adiabatic process, Q value is 0. There's no heat exchange between system surroundings. Q value is 0. If Q value is 0, you know delta U is equal to Q plus W. So therefore, delta U will be equal to W only. This equation is valid for adiabatic processes. Delta U is equal to W. Adiabatic. Okay? Adiabatic. Now, here I can generalize few statements. See guys, the value of W can be either positive or the value of W can be here negative. Now you tell me. If the value of W is negative, that means the gas is undergoing expansion. Over here, the gas is undergoing compression. Okay? If W is negative, that means delta U is negative. If W is negative, that means delta U is negative. Delta U negative means internal energy is decreasing. Delta U negative means internal energy of the gas is decreasing. And you know, internal energy is directly proportional to temperature, right? If internal energy decreases, that means temperature of the system increases. Sorry, decreases. They are directly proportional. Similarly, W is positive, which means that delta U is positive. If delta U is positive, it means that internal energy increases. If internal energy increases, that means temperature of the system increases. So guys, here you can generalize two statements. During adiabatic expansion of an ideal gas, temperature of the gas decreases. During adiabatic expansion of an ideal gas, temperature of the gas decreases. During adiabatic compression of an ideal gas, temperature of the gas increases. Two statements we need to remember here. During adiabatic expansion of an ideal gas, during adiabatic expansion of an ideal gas, temperature of the gas decreases. Similarly, my dear students, during adiabatic compression, of an ideal gas, temperature of the system, temperature of the gas increases. Temperature of the gas increases. Okay? Are these two statements clear, guys? Whenever the ideal gas undergoes adiabatic expansion, its temperature will be decreasing with time. Whenever the ideal gas undergoes adiabatic compression, its temperature will be increasing with time. Its temperature will be increasing with time. Right? Perfect. Now, guys, here also, there are two things. How do we calculate work done in reversible adiabatic and how do we calculate work done in irreversible adiabatic? That's the point here. How do we calculate work done in reversible adiabatic and how do we calculate work done in irreversible adiabatic? See, those are the two important things. Work done in reversible adiabatic process and work done in irreversible adiabatic process. Work done in reversible adiabatic, work done in irreversible adiabatic. How do we do it? How do we do it? See, guys. First of all, in case of your adiabatic process, Q is 0. In case of your adiabatic process, Q is 0. So as per first law, W is equal to delta U. So W is equal to delta U. And delta U for the ideal gas is nothing. That is NCV T2 minus T1. This is the first result which can be used to calculate work done in reversible adiabatic processes. Or there can be few more results generated. Work done in case of a reversible adiabatic will be equal to N. CV I'll write as R divided by gamma minus 1. And T2 minus T1 can be written as delta T. This can be one more result, by means of which you can calculate work done in case of reversible adiabatic, or W reversible is equal to NR. This is nRT2 minus nRT1. nRT2 is P2V2, nRT1 is P1V1, divided by what? Divided by gamma minus 1. These are the three expressions by means of which we can calculate work done in case of reversible adiabatic processes. In case of reversible adiabatic processes. Three expressions you have to remember, by means of which we can calculate work done in reversible adiabatic processes. Now, what about irreversible? Irreversible, already you know, W irreversible is equal to minus P external, V2 minus V1. This can be the first expression. The second one, W irreversible is equal to minus P external. What is V2? V2 can be written as nRT2 divided by P2. V1 can be written as nRT1 divided by P1. Out of these two expressions, you can use any one and get the work done in case of irreversible adiabatic processes. In case of irreversible adiabatic processes. Okay? These are the formulas by means of which we can calculate work done. Right? Right, people? Now, before showing you the question, there are two more things asked as well from adiabatic part. From adiabatic part, you will be asked. See, guys, one thing you already know. Whenever the ideal gas undergoes adiabatic expansion, its temperature decreases. When the ideal gas undergoes adiabatic compression, its temperature increases. Right? So during expansion and compression, during adiabatic expansion or adiabatic compression, temperature of the system, temperature of the gas changes, in short. Right? Now, guys, how do we calculate the final temperature? How do we calculate the final temperature of the gas in case of a reversible adiabatic process? Similarly, how do we calculate the final temperature? How do we calculate final temperature of the gas in case of irreversible adiabatic process? In case of irreversible adiabatic process. Calculation of final temperature of the gas in case of reversible adiabatic and in case of irreversible adiabatic. Just a second, guys. All right. In case of reversible adiabatic process, how do we calculate the final temperature? The general equation I'll be using, T1 V1 raised power gamma minus 1 is equal to T2 V2 raised power gamma minus 1. This is one equation by means of which we can calculate final temperature T2 of the ideal gas, which will be undergoing adiabatic process, which will be undergoing reversible adiabatic process. The second one, T1 raised power 1 minus gamma, T1 raised power gamma is equal to T2 raised power 1 minus gamma, T2 raised power gamma. This is one more expression with the help of which you can calculate final temperature T2 here. So when the ideal gas will be undergoing a reversible adiabatic process, these are the expressions by means of which you can calculate final temperature of the ideal gas. Okay? Now, in case of irreversible adiabatic, how do we calculate final temperature? Let me give you the expression, then I'll show you the questions directly. First of all, adiabatic Q is 0. Q0 means delta U is equal to W. And over here, I'm talking about irreversible. Delta U is nothing but NCV T2 minus T1, right? W irreversible is what? Minus P external V2 minus V1. So this can be the first equation used to calculate final temperature T2 of the ideal gas, right? Or you can convert it into different form as well. You can say N. CV is nothing but R divided by gamma minus 1. And this is T2 minus T1 is equal to minus P external. V2 can be written as NR T2 divided by P2. V1 can be written as NR T1 divided by P1. So NR cancelled. So I'll be getting the final result as T2 minus T1 divided by gamma minus 1 is equal to minus P external. It is going to be T2 divided by P2 minus T1 divided by P1, right? So two expressions we have here to calculate the final temperature T2 of the ideal gas which undergoes irreversible adiabatic process. Okay? So first of all, you have to identify whether the process is reversible or irreversible. Accordingly, you'll be using the results. I hope I'm clear to everyone. I hope I'm clear to everyone. Let's try to solve certain questions so that it becomes clear to you. See guys, the first question. It's an asked question too. Can you give it a try? Can you give it a try quickly? Quickly, people. Done? Yes, Visma, you can do that. You can do that. This series will be very much helpful. As per the question, 1 mole of a monoatomic gas. So how many moles of the gas do we have? 1 mole. The gas is monoatomic. If it is monoatomic, its CV has to be T divided by 2R. Perfect. Expands adiabatically. Initial temperature is capital T. Initial temperature is capital T. Against a constant external pressure. Constant external pressure of 1 atm. If external pressure is constant, that means the process is irreversible. Irreversible. From 1 liter to 2 liters. Initial volume of the gas was 1 liter. Final volume of the gas is 2 liters. What am I supposed to calculate? Final temperature of the gas. Final temperature of the gas. Since guys, the process is irreversible. If the process is irreversible, I'll be using the expression which I gave you a few minutes back. NCV T2 minus T1 is equal to minus P external V2 minus V1. Right? Now N value is 1. CV value is 3 divided by 2R. 3 divided by 2R. T2 we have to calculate. T1 is capital T is equal to minus P external is 1. V2 is 2 and this is 1. Correct? Now from here you can calculate T2 and I believe T2 will come as T minus 2 divided by 3R. This is the final temperature of the gas which I was supposed to calculate. This is the final temperature of the gas which I was supposed to calculate. See, Hania gave the answer T divided by 2 raised power 2 by 3. See, this is the mistake. That will be one of the options there. That will be one of the options there. If it was mentioned that the process is reversible adiabatic, then your answer was correct. Then your answer was correct. Then you would have used, then at that point of time, you should have used this particular formula. T1 V1, I mean this one, right? T1 is capital T. V1 is 1. 1 raised per anything is 1. This is T2. V2 is how much? 2 raised per gamma minus 1. Gamma for monatomic gas will be how much? 5 by 3. 5 by 3 minus 1 is 2 by 3. So at that point, your T2 would have been T divided by 2 raised per 2 by 3. But this is the final temperature of the gas if the gas was undergoing a reversible adiabatic. But in the question, it's not reversible, it's irreversible adiabatic. So your answer should be this one. Okay? Correct? I hope it's clear. Guys, just if in the question they have mentioned that external pressure is constant external pressure, that process is irreversible. That's it. Okay, that process is irreversible. Let's try to solve one more question. Give this question a try. Give this question a try, people. A sample of fluorocarbon was allowed to expand reversibly and adiabatically to twice of its volume. I think it will take us 1 hour more. Okay, maximum 1 hour more. Okay, a sample of fluorocarbon was allowed to expand reversibly and adiabatically. The process reversible and adiabatic to twice of its volume. If the initial volume is V, so the final volume has to be 2 times V. During the expansion, the temperature dropped from initial temperature of the gas is given as 400 Kelvin. Final temperature of the gas is given as 100 Kelvin. Assuming ideal gas conditions, calculate CV for the gas. We are supposed to calculate CV. CV is nothing but R divided by gamma minus 1. Right? CV is nothing but R divided by gamma minus 1. So basically, I need to calculate gamma first of all. Since the process is reversible and adiabatic, the process is reversible and adiabatically. So in case of reversible adiabatic, I can use this equation. T1 V1 raised per gamma minus 1 is equal to T2 V2 raised per gamma minus 1. Okay, what is T1? Check it out. T1 is 400. What is V1? V1 is V raised per gamma minus 1 is equal. What is T2? 100. What is V2? 2 times V raised per gamma minus 1. So 00 cancel. V per gamma minus 1, V per gamma minus 1 cancel. So 2 raised per gamma minus 1 is 4. 4 is nothing but 2 ka square. So gamma minus 1 is 2. You got to know gamma minus 1 2. If gamma minus 1 is 2, so CV is R divided by 2. Right? This is something which I was supposed to calculate. Isn't it simple, people? Isn't it simple? Yes? So you should be able to solve this sort of a question as well if it comes. All right. Okay, have you heard about something called as free expansion? Free expansion. Free expansion. Yeah? What is free expansion? You know, expansion of the gas in vacuum, or you will say expansion against zero external pressure. Expansion against zero external pressure. Expansion against zero external pressure. What it means? For example, this is the container which we have, and in this container you have kept an ideal gas, let's say. Okay? So over here, on the piston, there'll be 2 pressures. One is pressure of gas, and one is P external, right? Assume right now P gas and P external, they're equal. If P gas and P external are equal, the piston won't be moving at all. It'll be stick at one position. If suddenly P external becomes 0, the piston will suddenly go out. If the piston suddenly goes out, the volume of the container increases. Volume of the gas increases. Increase in the volume is something which you call as expansion. So over here, I would say at that point of time, expansion of the gas is happening against zero external pressure. And expansion of the gas against zero external pressure. Expansion of the gas against zero external pressure. Or you can say expansion in vacuum. You can say expansion in vacuum is something which is what you call as free expansion. Which is what you call as free expansion. Right? Perfect. My dear students, free expansion, right? Expansion again, zero external pressure. So suddenly if you make P external 0, the piston will go out fast, right? So this process is irreversible in nature. It is irreversible in nature. Number one. Number two, since external pressure is 0, how do we calculate work done in irreversible processes? W irreversible is equal to minus P external delta V. If P external is 0, so W value has to be 0. W value has to be 0. Perfect. So in case of free expansion, W value is 0. Perfect. During free expansion, W value is 0. Now the same free expansion, you can, further divide it into two categories. Let's see if you know it or not. The same free expansion you can divide into two categories. The first one I'll be calling as adiabatic free expansion. Adiabatic free expansion of an ideal gas. Second one is isothermal free expansion of an ideal gas. Isothermal free expansion of an ideal gas. Adiabatic free expansion of an ideal gas, and second one is isothermal free expansion of an ideal gas. The gas has to be ideal, okay? Now guys understand. First of all, I'm mentioning that free expansion. In free expansion, W is 0. In adiabatic, Q is 0. If I use the first law, delta U is equal to Q plus W. So delta U is 0. Delta U is 0 means NCV delta T has to be 0. If NCV delta T has to be 0, that means delta T has to be 0. Delta T will be 0 only if temperature of the gas is constant. Temperature of the gas is constant is in case of what? Isothermal. So can I say an adiabatic free expansion of an ideal gas is isothermal as well? An adiabatic free expansion of what? An adiabatic free expansion of an ideal gas is isothermal as well. Is isothermal as well. Okay, this is the statement which you need to remember. Now, my dear students, if you look at the next one, isothermal free expansion. First of all, free expansion means W is equal to 0. Isothermal means delta U is equal to 0. Right? So as per first law, delta U is equal to Q plus W. That means Q value has to be 0. Q is equal to 0 means adiabatic. So again, I can generalize the statement. I can say an isothermal free expansion. An isothermal free expansion of an ideal gas. Is adiabatic as well. Is adiabatic as well. Am I clear with this? So these can be the two statements which can be asked, right? Two statements can be asked. Perfect, guys? There is one last topic of the today's session. See, guys, one thing I'll tell you. There will be the second marathon of physical chemistry class 11th as well, in which we shall be doing thermochemistry, atomic structure, and equilibrium. These three will be done in the second marathon of physical chemistry. Okay? These three will be done in the second marathon of physical chemistry. There is one last topic left, that is cyclic process. Okay, let's complete the cyclic process and we are done for the day. In thermochemistry only, I'll be doing Gibbs free energy entropy. In thermochemistry part, I'll be doing heats of reactions, entropy, Gibbs free energy, then atomic structure and equilibrium. That will be done in the second marathon. Okay, so here, let's talk about something called a cyclic process. Let's see what kind of question can be asked from the cyclic process. Okay, let's see. Cyclic process. So first of all, as per the name is concerned, you already know in case of cyclic process, the initial state and the final state of the system is same. Initial state and final state of the system is same. right? Change in the value of any state function for a cyclic process, it has to be 0. It has to be 0, right? So can I say delta U net as well as delta H net in case of cyclic process has to be 0? Correct? Now, delta U net will be equal to, as per first law, Q net plus W net. So Q net plus W net has to be 0. So in case of cyclic process, I would say Q net is equal to minus times W net. This is valid for the cyclic process. Q net is equal to minus times W net. The first thing which you need to know. The first thing which you need to know. Okay, number 1. For example, I'm making a cyclic process over here. Let's say this is pressure, this is volume. Pressure versus volume. We are starting, let's say, from point A. Point A. From A to B we are going. Then from B to C we are going. Then from C to A we are going. Perfect. So, can I say the system is returning to its initial state after going through a lot of steps? Yes. How many steps? 1, 2, 3. 1, 2, 3. Right? 1, 2, 3. Now, my dear students, understand one thing. If I write Q net, what is Q net? It is the net heat absorbed or released during the cyclic process. Net heat absorbed or released during the cyclic process. Q net has to be nothing but, it will be heat absorbed or released during the process AB, heat absorbed or released during the process BC, heat absorbed or released during the process CA. Similarly, W net. W net is going to be work done during the process AB plus work done during the process BC plus work done during the process CA. Work done during the process CA. Okay? Now, one more thing. If they ask you, calculate the magnitude of net work done. Calculate the magnitude of net work done. Magnitude of net work done. How you are going to do that? It's always equal to area enclosed by the loop. Area enclosed by the loop. This area you have to calculate, right? It will give you the magnitude of net work done. And at the same time, if the cycle is clockwise, W net sign will be negative. If the cycle is anti-clockwise, W net will be positive. These are few things which you have to remember. That's all. That's all. Few things which you need to remember. That's it. Okay? In case of cyclic processes. For example, let's try to solve a question so that you understand it properly. See guys, one basic question we have. We are given with the cyclic process. We have to calculate net work done. Net work done. So first of all, I'll calculate magnitude of net work, which will be area enclosed by the loop. Area enclosed by the loop means area, this area of the triangle, which is half of base into height. Base is V1 to 3V1. That means 2V1. And from here to here, it's going to be 5P1. So the value is going to be 5 times P1V1. This is the magnitude of net work done. Now, the cycle is clockwise. If the cycle is clockwise, so write the W net with the sign. It has to be minus times 5P1V1. Right? These sort of basic questions can be asked. Done and dusted, right? These sort of basic questions can be asked. For example, what is this question all about? Let's see. 1 mole of ideal gas. 1 mole of ideal monoatomic gas. So N is 1. It is monoatomic as well. So Cb is equal to 3 by 2R. Right? Cp will be equal to 5 by 2R because the gas is monoatomic. Perfect. Is taken through the cycle. Given, calculate QAB and QCA. QAB we have to calculate, QCA we have to calculate. So QAB, during the process A to B, calculate the amount of heat absorbed or released, and during the process C to A, calculate the heat absorbed or released. First of all, if you analyze the AB process, AB process, volume is constant, so it's isochoric. It is isochoric. So amount of heat absorbed or released during the process AB, what does that mean? It is basically amount of heat absorbed or released at constant volume, right? That will be NCV T2 minus T1. and CV T2 minus T1. What is N? 1. CV is 3 by 2 R. 3 by 2 R. Let's say I am taking everything in calories. 3 by 2 R. T2 minus T1. A to B. This is initial, this is final. So final temperature minus initial temperature. Final is 600, initial is 300. 600 minus 300 comes out to be 300, right? So 2 to cancel. The value comes out to be 900 calories. So QAB is equal to 900 calories. Now similarly, QCA, heat absorbed or released during the process CA. This CA process, as you can see, it's isobaric. Isobaric. That means heat absorbed or released at constant pressure we have to calculate. It has to be equal to NCP T2 minus T1. NCP T2 minus T1, right? What is N? N is 1. What is CP? CP is 5 by 2 R T2 minus T1. CA, this was initial, this is final. So final temperature minus initial. So 300 minus 450 means minus 150. Correct? So 2 gets cancelled. The value will be minus 750 calories. Perfect. These were the two things which I was supposed to calculate. These were the two things which I was supposed to calculate. Yes? Perfect. Perfect, guys. I hope all these things are clear. I hope all these things are clear to you. Right, guys? Okay. There is one more small topic which is left here. That is efficiency of the cyclic process. That is efficiency of a cyclic process. Just a second. Efficiency of the cyclic process. How do we calculate efficiency of the cyclic process? It's a simple 5-minute topic. Efficiency of the cyclic process, area enclosed by the loop. Area enclosed by the loop means this area. This is the area enclosed by the loop. Divided by area under the curve. Divided by area under the curve. What is the area under the curve? Area under the curve is this whole area. Right? So first you have to calculate area enclosed by the loop. Then you have to calculate area under the complete curve. Then multiply by 100. You'll be getting the efficiency of the cyclic process. For example, see, let me give the proper naming to everything. This A, B, C. Let's call this point as D. Let's call this point as E. Okay? So percentage efficiency. Percentage efficiency is equal to area enclosed by the loop means area ABCA. Right? Perfect. Means this area ABCA. Area under the curve means ADEC. Area ADEC. Multiplied by what? Multiplied by 100. So percentage efficiency is equal. Area ABCA. ABCA means area of this triangle, which is half of base. Base is from here to here, 4 liters. Height from here to here, 1. Perfect. Divided by. This is a trapezium. This is a trapezium. Trapezium means it is half of sum of parallel sides. Sum of parallel sides, which is going to be 2 plus 1 into height. From here to here, it's 4 liters multiplied by 100. Now we can solve this. It's done, right? This term cancel. 2 plus 1, 3, 3, 4, 12. So 4 divided by 12 is 1 by 3. 1 by 3 multiplied by 100 is 33%. So 33% is the efficiency of this cyclic process, right? I mean, you just need to know the area enclosed by the loop divided by area under the curve. Divide them up, multiply by 100. That's all. Okay? Perfect, guys. I hope all these things are super clear. Okay? Perfect. Perfect, guys. All right, in the next marathon, what exactly are we going to do? in the next marathon of your physical chemistry, we are going to do thermochemistry, including entropy and Gibbs free energy, number 1. Number 2, atomic structure. And number 3, we shall be doing the equilibrium. We shall be doing the equilibrium. These are the 3 chapters which I have planned in the upcoming week, right? So basically what I had planned in the today's session, I'll be doing atomic structure instead of thermodynamics, so that 3 chapters will get completed properly, right? Venki, you can, I mean, I don't know about that, but I would rather tell you to write the test on priority. Okay? Perfect, guys. I think this much is enough. Sir, छुट्टी चाहिए. हाँ, छुट्टी हो गई अब. We are done. We are done for the today. We are done for the day. Yeah? We are done for the day. PDF also I'll send. I hope all the things are clear. Yeah? Yavar Manzoor is here. Yavar Manzoor. Do attend the tomorrow session, guys. That is class 12th organic. You used to tell me all the time. Class 2 complete, class 12th organic, right? HSP sir is going to take a marathon on that. So do join that session as well. Which topics come under thermochemistry? Heats of reactions, enthalpy of reaction, enthalpy of formation, enthalpy of neutralization, etc., etc. Right? Perfect. I'll send you the PDF for sure. Okay. Hello guys, with this then, I'll be taking a leave. Okay, do let me know in the comment section of this particular video whether you liked the session. And I would request every one of you to comment on this particular session, right? Those comments which will make me happy, yeah? Chalo, take care guys. See you.